for the most attendees this year, according to the numbers I heard this morning, over 200 and I think 20 or 230. And it's an exciting time. I mean, this is, as everyone here knows, things are moving incredibly fast. I had a colleague ask, well, is this the last AGI conference? No, but it is definitely an interesting and exciting time to be alive. And today will be workshops. We have 3 rooms, and Hyperon will be in the room to my left, so your right, and the other 2 the other 2 will be behind us. This morning it's interpretable natural language processing and the consciousness track, and it's basically on the other side of the stage here. And with that, I'll leave it to the inimitable Dr. Ben Goertzel.
Thanks a lot, Matt. Yeah, so welcome everyone to AGI-26. It's I think the 19th AGI conference, but it was 20 years ago when we did the first AGI workshop in 2006 in Bethesda, Maryland. And I mean, it wasn't that underground. Like we weren't meeting in a skanky basement under threat of the fascist government locking us up for subversive thinking. I mean, it was in a pretty boring conference room in the Marriott Hotel in Bethesda, Maryland. But it was around 50 people, I think. But nonetheless, the vibe there was very different, right? I mean, it was a vibe of like, here are a bunch of wild-minded freaks getting together to talk about something that you're not normally allowed to talk about in the university seminar room or in an academic event. And finally, like, for the first time, we get together in one room and talk about building actual thinking machines, right? And I mean, I don't want to overstate it too much. Like, you could here and there put a conference paper on building AGI in a mainstream event if you couched it with enough hedges and made sure that it was all very hypothetical and something that might maybe happen eventually. And of course, everyone knew in the 60s and the 50s, before that, the pioneers of the AI field had wanted to build real thinking machines. But it was sort of professionally unacceptable to get too excited about it. And the default understanding in the AI field was that you were centuries or probably millennia away from getting real progress on building real thinking machines. Now, there were other voices. I mean, I remember in the early 70s, I found in a town library in southern New Jersey a book called The Prometheus Project by Gerald Feinberg, who's a physicist at Princeton. He said within a few decades, we're going to get machines smarter than people. We're going to be able to build nano machines, building whatever we want, and we're going to be able to solve aging. So then the decision will be, what do we use all this capability for? Do we use it for consciousness expansion or rampant mindless consumerism? And he wanted to make he wanted the UN to lead a computerized democratic vote of the whole world population to decide what do we put these amazing technologies to use for, right? So these ideas were there. They were even there from people at fancy universities, but they were way, 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 way out on the margins, right? And I mean, I've seen these things shift, right? So 2005, which was the year that Cassio Panaschian and I published the book Artificial General Intelligence, that put that term out on the map. Ray Kurzweil published the book The Singularity is Near, forecasting, in essence, human-level AGI by 2029, which seemed pretty whacked to most normal people at that point. So now we're in a quite different situation, right? And I mean, I remember 2006 Singularity Summit, which I think was at the Presidio here in San Francisco. You had Justin Ratner, the CTO of Intel, saying, yes, the Singularity is coming and it's going to have Intel inside. Right? I mean, we didn't have NVIDIA being such a big force at that point, right? But, so now, I mean, now where are we? It's a quite different place, right? I mean, you have literally trillion-dollar companies. I mean, depending on the fluctuation of the market on a given day, but you have trillion-dollar companies whose CEOs are in fact pushing AGI as something real that they think they can build within the next few years. And you have national leaders taking the concept of AGI seriously as a priority for their economy and their military as well. So in a sense, yeah, I saw Sam Altman in the last couple of days was quoted as saying, we are in the singularity, right? And I think Elon Musk has said that before. Demis Hassabis from DeepMind as a scientist is more careful at phrasing things. And the way he phrased it is we're in the foothills of the singularity, which is it's a very British way of phrasing things, I guess. But I mean, I think that it resonates better with me. I mean, what Kurzweil meant by the singularity, echoing Werner Vinge, who introduced the term, was a point when, you know, AI has become so smart, it's taken the leadership on science and engineering advance from people. And like, your phone can spit out 5 Nobel Prize winning discoveries in a minute in the course of a conversation, right? And I think we're close enough now that we can smell the reality of that happening in a palpable way, but yet clearly we are not there yet, right? Like I still have close friends dying of cancer, right? Like the AGI has not cured cancer yet. I think AGI will cure aging, but my parents are in their mid-80s. I don't know if they're actually, you know, are they going to live long enough for the AGI to cure them? They're hoping so, right? So I mean, we're not there yet. And if you look at the state of geopolitics, we can also see a definite absence of superintelligence at play in most instances, right? So I think I don't think it's useful to say that we're at the singularity. I do think it's meaningful to say we're getting close. And of course, in a gathering like this, parsing these distinctions is important, because the reason we're not at what Kurzweil referred to as a singularity yet is we don't actually have human-level general intelligence yet, let alone super intelligence. But we can see the dimensions of it much more clearly than in 2006 when we had the first AGI event, or in 2005 when I published the AGI book and Ray published Singularity is Near. Now, one interesting thing we can see is, you know, Ray in his 2005 book thought we'd get human-level AGI in 2029 and superhuman intelligence in 2045, when the latter is what he called the singularity. That 16-year gap seems more peculiar now than it did then, because when you look at what we can do with coding models and with mathematizing models and so forth, it kind of seems like once you have a full-on human-level AGI that can plug modern LLMs and compute tools into its brain, it's hard to see why it would take 16 years for that thing to upgrade its intelligence significantly in a recursive way. And indeed, as we'll talk about later in this event, we already have AIs that are meaningfully recursively self-improving, like the Omega class system as one among many examples that we built within the Hyperon and SingularityNET project. I mean, this system is not yet a human-level AGI. It is, in a way, recursively self-improving based on its own neural symbolic reasoning and thinking, right? So we can already see bits of recursive self-improvement before you get to full-on human-level AGI. So it seems to me, once you get to full-on human-level AGI, it's only going to be 16 years from there to superintelligence if things are really throttled, either by the AGI itself or by some other mechanism. But the other big lesson we can see now that we're here in the foothills of the singularity is we've always been very bad at predicting which things can be achieved without AGI and which things really need full-on human-level AGI. And I've been bad at that over the decades. Essentially, every famous AI researcher has been bad at that. Even Kurzweil made many mistakes in that regard, right? And I mean, the failure of the AGI community to predict how good LLMs will be at this or that specific thing, I mean, it's not surprising given how bad the AI field as a whole has been at figuring out which things can be hacked with non-AGI methods. And I mean, that's one sort of issue from a practical business and society perspective, another sort of issue from a deep AGI research perspective, right? Because I mean, you could imagine 90% of human jobs, theoretically, could be automated without human-level AGI, just because there's a lot of training data about each job out there, right? And so maybe, and most jobs that most people do, including a lot of my own job, you don't need that much general intelligence to go step by step through your work tasks, right? It's things are repetitive, and modern society is organized that way. So there's a question of when do you need AGI to get something practical done, but nonetheless, I think it's important for those of us concerned with trying to build actual AGI, which is the focus of this conference. I mean, it's important to distinguish, can we carry out this or that task that humans carry out by applying our general intelligence? That's an interesting question, but at a conference like this, we're concerned not just with, can you carry out this or that task by hook or by crook? You're concerned with, like, is there a general intelligence process underlying the way the task is carried out, right? And that really brings us to the meat of the proceedings here. I mean, we are arguably in the foothills of the singularity. We have these amazing non-AGI systems, you know, LLMs and the various hybrid architectures that have been built surrounding them. We have these amazing systems that can do a lot of things that we use general intelligence to do, and that are also very valuable tools for helping us to work on general intelligence, right? On the other hand, no, we don't yet have any system like crystallized, fully functional, and deployed that carries out generally intelligent reasoning, self-understanding thinking the way that people do. And of course, the precise definition of general intelligence is one of the things that meetings like this are convened to discuss. But the core conceptual idea is an AGI should be an engineered system which can, hardware or software system, which can generalize beyond its programming and beyond its experience with some level of, you know, creativity and imagination, right? And so it should be able to, at least as well as people can, leap beyond its programming and training to deal with the unknown world. And this has been formalized in various ways by Marcus Hutter and Shane Legg, by myself, and by a bunch of other folks in this room in their own ways. And working with different formalizations of what is AGI is valuable, and one of the things that we need to consider here. But I mean, the other very major thing is no one has yet demonstrated such a system, and it's, you know, I see why certain tech CEOs want to blur those lines, because LLMs are kind of getting close, but there's still a major hurdle to overcome, and we need systems that are not just sophisticatedly repeating what's in their training data sets, but that are able to innovate and pivot and make creative leaps. And it's not just, you know, Einstein that made creative leaps. Every one-year-old child makes a series of huge creative leaps in just learning how to deal with the world, which is the great unknown to them from their own point of view, right? And I think we talked about sort of formalizing and exploring what is AGI. We talked about how to actually build AGI, which is both an engineering thing and a theory thing, because it involves a mathematical and conceptual understanding of the principles of AGI structure and dynamics, and the embedding of AGI in human society and future society incorporating humans and other minds. I mean, that's the final thing that we've always considered in these conferences, which is also quite important. And a lot of the talks here will be deeply technical, but we also have talks on the alignment, the evolution of value systems, and on the final day of the conference, which will get a bit less technical, mixed in still with some technical stuff. We will dig more into this sort of social, economic, conceptual aspects of how AGI meets the society that AGI is embedded in. And that final point brings me back to the value of conferences like this one, right? Because as AGI gets taken more and more seriously across the planet, which was pretty much inevitable to me since I was a little kid, right? But as we finally see it happening, AGI getting more and more seriously understood, what's happening, not surprisingly, is it's getting absorbed into our conventional economic and social structures, right? It becomes like big company wants to hire all AGI researchers and have them do proprietary research and not tell anyone what they're doing until they're rated by other big company. And, you know, two big countries want to suck all AGI researchers into themselves and use the AGI for military and intelligence purposes and throttle their proto-AGIs from answering anyone's questions about how to build better competing systems, right? So there's a lot of forces of isolation and polarization and fragmentation. And, you know, the academic world and the open source software world have been wonderful counterbalancing forces to all of this, right? I mean, everyone from every country in the world, pretty much, I don't know about North Korea, but from China, Russia, every major country in the world, we're still posting papers in archive.org. We're putting code on GitHub and participating in global research collaboration. And I think this sort of face-to-face event is an important part of that, right? Like we want to gather together people pursuing AGI from different paradigms, working for different large or small companies, working on academic projects, working on individual projects, and pulling people together, you know, making progress on the different dimensions of the AGI problem from different directions. I think this is quite important, both for making rapid conceptual and practical progress on the hard problems that still remain to get from the foothills of the singularity up the real peak, but also for, you know, infusing the AGI we do create with more collaborative and cooperative vibe. Because I mean, it's not a guarantee, but I think if global cooperation among people and projects with different perspectives, if this is what feeds in to bring the AGI about, I think it's more likely this sort of, you know, diverse, inclusive, cooperative mentality will pervade its way into the AGI's mind itself, which is something, again, I'll talk about on the final day of the event, and, you know, ideas on which I'm eager to hear everyone else's views. So yeah, I think Matt has already outlined the concrete proceedings today. We've got Hyperon Workshop in here and the two other workshops in other rooms here. This is a nice big venue. So we've got room for the formal gatherings and a bunch of informal conversations also. Then some amazing keynotes coming over the next few days. The next 2 days, Tuesday and Wednesday, are primarily in-depth technical contributed talks, which were amazing. Like, we've never gotten so many or such high quality papers contributed in previous years, and never so many practical demonstrations as opposed to just theoretical investigations, which is partly due to the non-AGI LLMs being so good at churning out prototype code for you, right? And then on the final day, as I said, a bit more technical content and also some panels and keynotes focusing more on the social context and the practical, commercial, and humanitarian applications of AGI technology. So, yeah, to sum up, I'm super excited to be doing one more AGI conference. I think it's the third one in the San Francisco Bay Area. We did 2011 on Google's campus in Mountain View, which was amazing free food. The only weird thing is if you wandered away from the conference building, all these guys came out of the bushes. They're like, wait a minute, go back over there. But it was an amazing venue, and I still remember the joke Peter Norvig gave when he gave the intro there. Like after I said in my keynote we were going to get to AGI by 2030, the next day he hacked into Google's task scheduling system to make it so their tasks could go up to 2035. He put in like January 1st, 2030 human level AGI, March 1st, 2030 human level AGI Mac version. So given Peter's dry sense of humor, I couldn't quite tell what probability he assigned to AGI actually coming about by that time, but I mean it wasn't zero. He's very open-minded, right? And we did another one in Palo Alto in the middle of COVID era. So this now no more COVID yet. We've got people playing with gain of function research for cybersecurity, but that's another topic, right? So I think we've got a positive ambiance this year. We've got, I think, should be the biggest crowd yet for an AGI conference, and I don't think it's the last AGI conference, but it may be the last one where all the presenters are human, because we already have some papers this year coming from my own team where AIs were significant conceptual contributors as well as just helping spit out code. So I won't be shocked if next year we have an AI presenter or something. But I think while not the last, this promises to be the best AGI conference yet. So I'm very psyched for the next few days. And thanks everyone for showing up early in the morning.
Since it's time for workshops, we'll go to workshops. First, I want to give a quick thank you to our amazing sponsors this year. We have Apile, again, another sign of the increased interest and progress towards AGI. SingularityNET, of course, running the live stream and facilitating most of the events team, so thank you, SingularityNET. Saga Solve, True AGI, the Artificial Superintelligence Alliance, the AI Collective, we're partnering with especially for our Day 4, which is the More AGI Leaders Broader Look at AGI Day, and Granica. So thank you to our sponsors. We have the 3 workshop rooms mentioned. Hyperon, the path to, where are we on the path to Hyperon-Based AGI, right here next door. Just around the corner here, down the hallway, there's INLP, Interpretable Natural Language Processing, with Anton Kolonin. And then just beyond that, there is the Consciousness Workshop with Joscha Bach and Anna Makeda. So please find your workshop. We'll be getting those started rapidly. And then we'll be back here at 11:45 for a fireside chat with Gary Marcus and Ben. And then a presentation from Anil Seth before we break for lunch. So we'll see you all at 11:45. Thank you.
Hey everyone, any chance to unmute the audio? We can't hear the feed.
Okay, but I shouldn't have, should I have my Zoom video on, or no, it's being captured from that? Yeah, I'm gonna wander around. My Zoom video is just gonna capture hideous looking parts of my midsection, I think. Oh, yeah, I'll leave that camera. But it's gotten much better, as you must admit. No, yeah, still not as simple as in the era of transparency projectors, but it's gotten way better. I mean, I'm older than you. I started in the chalkboard era before we had whiteboards, right? I'm not from the stone tablet era, though. That must have made the chalk very slow if you had to chisel into the stone. Are we ready to roll, John? Oh, that's video, right? But I see my video, right? Yeah, in Zoom. Come here, I can my video from that camera. The video from somewhere. No, this camera's off.
Yeah, that's this camera.
Yeah, that's okay.
You don't see it there. I guess that's okay.
No, we don't need to, people in this room don't need to see the video.
No.
Right?
Okay, I think you're fine.
All right, let us proceed then. So this is a 2026 Hyperon Workshop. So it's super interesting time to be digging into the details of the Hyperon AGI approach. And I guess we were supposed to have a bigger room, but I guess we were outnumbered by consciousness people, right? So people are more worried about whether the AGI will be conscious and how to actually build it. But I mean, it's all good. I mean, once we use Hyperon to make the first AGI, we will need someone to be its consciousness doctor and make sure it's having a positive experience and so forth. So yeah,
This could work from a variety of languages
that's very loud.
in the areas where they're spoken, right? So this is very, very much different from the distribution.
There's no rules. I mean, I thought I didn't need a microphone, but I am pretty loud. But there's no roof. Oh, did they turn it down? Right? Yeah, yeah, it's fine now. Yeah. What is that workshop on anyway? Oh, that's Anton Colonen's thing. Yeah. It's a problem with these parallel sessions. I mean, it's all interesting, right? That's another problem. Yeah. No, it should be good for our band performance on Thursday night. This thing has some very good resonant acoustics, I think. Unless you have multiple bands playing at once, but then it's the right genres, it all comes out in the wash, right? Yeah. So, yeah, I made a deck which I will step through because it seemed like Hyperons. There's so much going on that if I just stream of consciousness it, I will leave out some important things. But let me first just give a high level view of where we're at and where we seem to possibly be going, right? So, and we've got majority of sort of insiders to the project here, but not 100%. So I will bore the insiders for 2 or 3 minutes with ancient history and then plunge into current and future stuff. So the ancient history of Hyperon goes back to a project called WebMind from the mid-1990s, which I started coding in 95 and 96, and as a university researcher, then moved to New York, and we started a company with a number of collaborators. But the concept then, at the high philosophical level, was not that different than what we're doing now. I was teaching deep neural nets then, which were much smaller than the current ones we have now. It took like 3 hours for a neural net with a few dozen nodes to converge using recurrent backprop on the Solaris workstation in the mid-90s. But we were working with neural networks, and there was a company in Perth where I was in the university that was building neuromorphic hardware. It was called Formulab Neuronetics. I think it died a long time ago. But doing symbolic logical reasoning based AI. Evolutionary learning was a thing then. Matt Iklé and I were working on getting evolution and ecology to work together in these evolving networks. So the key ingredients that we're looking at now were largely there back then. And I was trying to implement my own weird functional language interpreter implemented in an early version of Haskell, which was before GHC and monads and stuff. And I had the idea, like, all these different paradigms are important. None of them seems to solve the whole problem, just like no one neural sub-architecture in the brain seems to solve the whole problem. So we wanted to build like a big self-evolving, self-modifying knowledge graph, which could represent all the different kinds of knowledge in it and represent different kinds of processing in it, and like let it self-organize itself into intelligence. And we talked then about experiential interactive learning, right? Where you could have, clearly you didn't just want the system to suck in all the knowledge from the internet. But clearly you want it to do that, but you also want it to interact with cameras and drive actuators, drive chatbots, and learn from its own experience, build its own internal world model, right? So I mean, all these concepts were there then. In hindsight, the hardware was just too shitty to make a serious stab at the thing. Like we had in WebMind Inc., we had like 30 quad processor Dell servers in the closet, which was expensive at that point in time. The notion of decentralized infrastructure was there then because the internet was decentralized, right? And I thought we could do something like a decentralized Google, where you would just have the whole web indexed by a decentralized network of servers that were doing different thinking at different nodes, right? And you saw then that you needed strong encryption. You had already PGP and stuff working together with distributed networking. So, I mean, all these ingredients were there, and actually, we have some folks in the room who are even older than me and have been thinking of these lines even longer, probably, right? So, I mean, if we look at where we are now, the philosophy being pursued with Hyperon is not that different. The tooling we have is insanely better, and sort of the mathematical and conceptual framing we have for each part of the problem is much better. And this has, well, this is going to be really annoying all day. Yeah, all right, I can barely hear myself. Yeah. And that, it's because those are remote, I think these are remote talks, so this, yeah. Yeah. Yeah, that's, yeah, yeah. So, yeah, that's better. It's all right. It's got a certain ambiance to it. Yeah. I just have to get pissed off about something. Then I can shout indefinitely long. Yeah. Just ask me about Fable being throttled. I can get yeah. It's throttling my queries on non-constructive set theory applied to whether P equals NP. And I'm not sure how that's a cybersecurity or risk to anything. Yeah, so we've been through a few iterations. I mean, there was a Novamente cognition engine, and then OpenCog, which we got from open sourcing. Hey, welcome. OpenCog we got from open sourcing Novamente cognition engine in 2008. And Hyperon, its conception was a big decision, right? Because OpenCog was sort of working, clearly wasn't scalable enough to get us to human level AGI, but purely on that level, you could see ways to scale up the OpenCog code base. On the other hand, I made the decision in, I guess it was 2020, 2021, that after a bunch of discussions, mostly with Alexei Potapov, Vitaly Bogdanov, and a bunch of our Russian contingent. I mean, we made the decision that while we could scale up what I now call OpenCog Classic, I mean, it's all C++, like you can rejigger the infrastructure to be efficient. It seemed like software engineering had advanced a while since 2008 when we started with OpenCog, and it seemed like you could just engineer things in a much nicer way. And so we sort of rethought the model. Like in the old OpenCog, you had atom space, and you had something called the pattern matcher, which started as a pattern matcher, but almost became a full-featured programming language inside the process of pattern matching. So we decided just to take a different approach and build the atom space as a different sort of infrastructure where you had a nice interface, but what happened inside didn't have to be like one object for each atom. It could be anything inside that infrastructure. Implement pattern matching and unification as sort of APIs on top of that, and then separate your language of thought, your AGI programming language, from the pattern matching operation. So like make the pattern matcher a static pattern matcher, and then put the more dynamic stuff in a separate language rather than inside the pattern matcher. And that became the meta language. And so you then had what we thought of as a cleaner architecture, right? Where you have atom space as a sort of API, where we could have many different kinds of spaces inside that. Pattern matching and unification as relatively simple static operations. Then the meta language as a nice graph rewriting language, which lives outside of that, and the meta programs can live inside the M space. And then separately from that, this gives you the ability to make a nicer distributed and decentralizing process infrastructure. Then we get things like distributed atom space and ASI chain and so forth. And within all this, you could put largely the same assemblage of AI algorithms that we'd been pursuing since the WebMind and Novamente days, and that has also evolved a bit in the last year or two, as we've had new thoughts about how to integrate deep neural nets into the framework, and new thoughts on cognitive control related to things like Omega Claw and the Omega Claw hives and so forth. But these new things, like different ways of integrating deep neural nets into the mix and different ways of doing high-level cognitive control, they do fit reasonably elegantly into the software framework that we laid out when we started Hyperon. So I feel like looking back, indeed, it took a little longer than I thought to get Hyperon fully operational, but only about twice as long as I thought, not 10 times as long as I thought, like used to happen, right? So I find as we get like coding agents and more modern software infrastructure, my time estimates get closer and closer to accurate. Like they used to be off by a factor of 10, then 5. Now they're often off by a factor of 2. So when we get to the singularity, maybe things will finally be going as fast as I always intuitively think they should go. But then the new developments do seem to be fitting into the overall framework. So I do feel it's very clear to me in hindsight, it was a difficult but good decision to like reboot and restart with Hyperon rather than patching the old OpenCog. So where are we at with Hyperon now? So for about 2 years, I kept saying, well, we just got to wait till we get a scalable meta compiler or interpreter, and then we can really start to have fun. So, I mean, now we have an overabundance of really scalable meta infrastructures. I mean, I'm working personally now with Patrick and Peter's PETA compiler, which I think is the most mature scalable option at the moment. But I started playing with my son Zar's SETA compiler, which also works, and I think I'm soon going to start trying to get meta super compilation to work, and I'll talk about that later this morning. But I think SETA is a good infrastructure for that because of the particular ways that the LLMs are architected it. But the Meta IL infrastructure from Greg Meredith's team is also working now for a variety of different meta programs. I think not yet fully deployed for everyone else to use, but it's getting quite close. And we'll see. Jetta is now working for a large subset of meta. So we've gone from, oh, we can start to have fun once we have a scalable meta compiler to, well, there's a lot of different options, and we'll see how they all evolve. And now the thing I keep saying is, as soon as we have a scalable PLN control heuristic working, like then the next stage of the real fun begins. And my prediction is 6 or 9 months from now, we're going to have an abundance of scalable PLN control heuristics to choose between. And just like now with the meta compilers, the question will be like, which PLN control heuristic do you use for which thing? How do you adapt your problem from one to the other, and so forth. So I mean, it's actual practical progress as well as theoretical progress, and coding agents have advanced also a lot now. Like it was 6 or 9 months ago, we were still banging our heads on like, how can we get LLMs to code meta acceptably? And then big tech solved that for us. I mean, partly Alexa helped because at some point the LLMs had all its meta tutorials in their pre-trained model, right? So putting a lot of stuff online was probably helpful. But also the fact the models got better at reasoning was helpful, right? So I mean now I have a bunch of OpenClaw and OmegaClaw agents that are coding meta for me every day, right? And it becomes sort of routine. And there's still work to be done on automating the formal verification that what they do makes any sense, which it usually does, but not 100% of the time. But we're in a phase now where we have basic Hyperon infrastructure functions. I mean, it's still being improved and optimized, but there's versions that function well enough to do AGI at reasonable scale. And automated development infrastructure works such that you can do a mix of Vibe coding, human coding, formal and human verification according to the particular project and your own taste. And we're now working on taking both familiar and new AGI-oriented learning, reasoning, memory, attention approaches and implementing them at small and then at large scale and getting them to actually function, right? And I think a very interesting point to be at. I would say we've probably got another 6 months or so of this phase, and then things will shift more finally to cognitive synergy, which is like, okay, we've got scalable inference control working. We've got program learning working at scale within certain constraints. We have attention allocation working. Concept creation is working. These things are working behind a robot. These things are working behind a hive of chat agents doing something useful. Now, how do we get all these different algorithms to cooperate together effectively to give synergetic intelligence? I mean, we can touch on cognitive synergy a little bit now, but I'd say the main thrust now is getting a few core cognitive algorithms to actually work at scale within the infrastructure, which now does work at scale, but we're sort of a third or halfway through that, and things are going very quickly, right? So that's a very high level. I'm gonna race through like 20 slides here to try to give a more structured view of things. So let's see if I can figure out how to operate Google Slides. No. Okay, there we go. So high level way I'm presenting this, abstracting away from the details, is, which is obvious to most people in this room. I mean, we're looking at Hyperon. It's an integrated cognitive infrastructure. And of course, it's not just an infrastructure. The reason we built this infrastructure is because we had some idea what algorithms we wanted to put on top of it. And there's a feedback between the algorithms and the infrastructure. Like we start with an initial guess of what are the AGI algorithms we want. We built an infrastructure to support those. But then given that infrastructure, we may come up with even better AGI algorithms to run that infrastructure. The better AGI algorithms may lead us to want to evolve the infrastructure in different ways. So we're trying to seed a mutually beneficial human and AI-driven improvement process where you're improving the infrastructure and the algorithms. But if the infrastructure isn't at a certain level, you can't even seed that, right? And there are many aspects here that we need to get to true human level AGI and superintelligence. 3 aspects I want to call out are recursive self-improvement is there from the get-go. And arguably omega claw agents are already recursively self-improving when configured and operated in the right way, even though they're short of human level AGI. And that is another thing that wasn't obvious to me from the get-go. Like I'd thought for a while you get human level AGI, then you get RSI. Now I'm seeing you can get RSI first, even before you have human level AGI, which is quite interesting. Now, creativity, again, a fuzzy thing to define. In many ways, LLMs are more creative than most people are most of the time. But there's still an element of creativity that LLMs are lacking that we have. And you can see this in using LLMs or claw agents to do research now. Like they will go down stupid little rabbit holes, just repeating stuff from the literature that they've seen over and over again. And they need you as a smart human to say, hold on, look at things a different way, right? And I think it's not something beyond the scope of AI algorithms, probably not beyond the scope of PLN abduction or evolutionary learning. It is different than what LLMs do in the harnesses that we know how to build right now, right? And in terms of values, I mean, LLMs obviously don't have them in the standard sense, which is why you need this absurd mechanism of guardrails and so forth. On the other hand, a rigid top-level goal system is going to run into problems very, very rapidly. And like you can see that playing out in the world around you now. So I don't want to digress onto it, but I wrote a blog post this morning on this bizarre comedy of errors with OpenAI and Hugging Face and so forth, right? Like the lack of goal-directed reasoning and like a value system governing what the AI system does. Like you can see the problem they're like playing out on the world stage now, which is quite hilarious. And I mean, you need values that guide development, but that are also flexibly evolvable along with the development of the mind. And none of this should be very surprising to anyone who's been thinking about cognitive systems theory for more than 5 minutes. But I mean, these sorts of things are baked into the foundations of the Hyperon design rather than being things that you try to like bolt on after you have a system that already has its whole infrastructure there. And I think these are very critical to AGI, right? You need something that can modify and improve itself, can do so creatively, yet can also follow some stable yet evolving goals in the process, right? And there's many reasons why LLMs and the rest of the modern deep neural net stack don't do all this. Everyone in this room knows these things already, so I won't harp on them too much. But I mean, an architecture like Hyperon that's trying to be a coherent mind from the get-go, it's just very different than something that's built as a batch mode trained next sequence predictor within a bunch of harnesses written around it. And you can view this. Oh, let's see. You can view this in a very boring way, even if you think about like what the big companies need from software systems. I mean, there are many things that Hyperon provides that the current standard stack doesn't, like memory that keeps accumulating over time, yet and doesn't disappear, right? Like this whole thing of train a model, freeze it, and then do inference for a little while. I mean, clearly that's not how an AGI mind could work, and you have to come up with all sort of hacked on auxiliary memories. Reasoning, you would like something to be able to audit how it reasoned and know how it reasoned. People aren't that good at that. We're better than LLMs at it. We're not as good as, and companies have made all sorts of extra human apparatuses to help support people in auditing and recording their reasoning. You want continuous ongoing self-improvement, you want creativity, yet you want provided values to actually mean something in a way that guides the thinking rather than just being guardrails that so that's like with a self-driving car. I mean, the autocorrect is fine, like to steer you back when you go off the road because you're looking at your phone. But I mean, you would rather have something that doesn't go off the road and bang against the guardrail so much in the first place, right? Now, a lot of these issues that are lacking in the current default tech stack and that Hyperon provides just by architecture are really obvious, super boring things rather than like a wild, super intelligent self-modification. But they all connect, right? Because how are you going to get to super intelligent self-modification if you can't even learn continuously or can't even remember what happened to you last week, right? So, I mean, so looking at the basic architecture, we have the meta language, which most people here are familiar with, but it was designed over a series of iterations to be a language that has a very high level of abstraction. So you can represent pretty much any logic within reason, to make a bad pun, but I mean, most any sort of logic you could think of, any sort of programming framework you can think of. But we want it to also be reasonably efficient on modern hardware. And now that we've pretty much done it, it's just sort of a thing we take for granted. But at the outset, many folks thought that was impossible because most weird abstract programming languages are very, very slow and hard to use for real projects. So the idea you can make a very flexible functional language meets logic programming language with new types that you can introduce at runtime and make this reasonably scalable. It was not that obvious when we started with Meta a few years ago, and it wasn't that obvious to everyone playing with the early versions of Hyperon experimental either, right? So the fact that Meta works at reasonable scale, and there are clear ways to scale that more and more, like this one of these obvious in hindsight things, right? Then Atom Space API and lets you wrap up different sorts of atom spaces, mainly meta-based ones, but not only meta-based ones. You could have a ChromaDB-based atom space, like we do in some versions of Omega Cloud. You could have a neural atom space. There's an assemblage of algorithms that we're building to run on top of this infrastructure. And again, the infrastructure is flexible regarding what algorithms you run on them. But we do have a specific collection of algorithms like PLN, Moses, forms of concept blending, ECAN, that we believe when put together can get you a long way toward AGI. We're also very open to introducing new algorithms into the mix. Primus, which I used to call Cog Prime, this is basically a theory regarding how you can take a certain set of algorithms running on Hyperon and have them synergetically interoperate together to yield human level and then at least mildly superhuman intelligence. And while there's a lot written on it, there's also a lot of wiggle room in the Primus architecture. And the Primus, for those who are of the wrong generation, this was the god of the Transformer universe, but of the not Transformer neural nets, but the big hulking robot truck Transformers. So Elon Musk had the Optimus robot, but Primus was more powerful than Optimus. But he didn't transform into a truck; he transformed into a planet, right? So he was opposed by Unicron. And that's it. Unicron was the evil version of Primus. So we can create Unicron inside a sandbox just to see what he will do. Have faith he will never escape, right? Yeah. Gain of function research worked great for biology, right? I mean, yeah. And ASI chain decentralized infrastructure with Meta as the smart contract language, which will let you run a decentralized Hyperon system on a collection of nodes on the internet without needing a central owner or controller, though it could have one if you want. We've been experimenting recently with a sort of new form of what you might call an operational fabric running on top of this, which is a Omega Claw, which we'll hear more about, sort of an OpenClaw style agent with an LLM in the agentic loop, but also atom space working memory, atom space long-term memory, and I and others are experimenting with the intermediate scale memories you can plug in there. And then there's the notion of an Omega Claw hive, where you have a number of different Omega Claw agents that are sharing some common atom space, but may also have their own. And this I think replaces the control loop that we had in the older versions of OpenCog and Hyperon, which is something called the cog server and so forth. So I think it's interesting gluing LLMs into the control loop, but it has a lot of big advantages. So there's a lot to be said about just having a shared knowledge metagraph across different cognitive algorithms, because different cognitive algorithms are then sort of using, if you look way back in AI, like a blackboard architecture, right? You had the idea that there's like all these professors solving a research problem. They're all writing on the same, it was originally blackboard, maybe they called it whiteboard architecture eventually, but all writing on the same blackboard, erasing what each other wrote, added onto it. So that it's a bit like that. You want different cognitive algorithms to be sharing their intermediate representations and like showing their work as they go along in the middle of a thought process, so that they can help each other out when they get stuck in the middle of doing something. And this was the idea going back to WebMind. It's just until PETA and then the other similar systems we have now, we didn't actually have an infrastructure where you can you could even play with that. In terms of execution, we need to think about goal-driven execution. We have a set of goals. Initially, they can be given by humans. They can then be evolved by the system. And then a bunch of the system's operation is figure out which procedures should you be running to help achieve the system's goals in the current perceived context. And that's important. It's important that the goals have some stability. It's also important that the goals can be modified and improved by the system, or else it will just hack around them in perverse ways anyway. It's also important, I think, that not everything is rigidly goal-oriented, because goal orientation can be an information bottleneck, and you want to have some ambient background thinking, like just go through and spread attention, just go through and combine pieces of knowledge to form new knowledge. And then this can then feed into the goal-driven learning. And Hyperon infrastructure supports a great variety of different control mechanisms. It's not that there has to be just two levels or something, but at least you do want those two aspects. World modeling, a lot has been said about it in the media in the last year. I mean, I think, to make a long story short, like, you probably don't have a world model module that you plug in, but the functionality of world modeling spread across different atom spaces and their synergetic activity is certainly important. And you need atom spaces that evolve their own world models, to be a sort of missing middle between perception and action, to help with both goal-driven and ambient cognition. And probably, given modern AI infrastructure, the world model will be a number of different neural nets. It will probably be also some symbolic content, also some hypervector content, right? And the world model itself is more of a dynamically assembled assembly, combining these different components. And I mean, again, the whole framework is very flexible. One kind of thing that can happen here is you can have an operational control cycle, like Omega Claw wants to do something. It pulls together a bunch of different claw agents to do things, which assemble different atom spaces internally to do things. They try to solve the problem using some synergetic activity. Top level goals, look at what's going on and make sure it's consistent with the high level goals. Something is done. The whole thing is stored in atom spaces. The whole record can be audited and analyzed. And after the fact, some self-improvement happens, and you keep going, right? All this, when you say it, is really simple and really boring. It is, on the other hand, different than the standard process you have when you apply ChatGPT to something. Let's say, I mean, it's just more of an AGI, autonomous mind-like workflow, right? And we'll hear more about Omega Claw later today. I won't go into too much depth on it, but I do want to say the current Omega Claw is very cool, and I'm using it every day. Many others are. It does actually useful things, and it's also a good prototyping ground for different AI algorithms. The way Omega Claw is used right now is not quite yet AGI worthy. A big difference is I think we need some more systematic use of context frames than what we have now in the default use of Omega Cloud, right? So you don't want just to be using an LLM with M-space memories. You want to be using the M-space memory in a bit more structured way to give a precise model of the tasks and actions that the whole system are doing. And but I mean, that exists in code now. It's just prototype code, and we're experimenting with that. And you can then look at how this self-modeling work on the level of an individual claw agent using Hyperon mechanisms to model itself and its actions. How does self-modeling work at the level of a hive of claw agents? And again, none of this needs any big new mechanisms. Like this just comes right out of storing stuff in the atom space and doing reasoning and machine learning on top of it. And you can make pretty simple standard looking flowcharts. Like you have a goal, you do some planning, you form a context stream for how to achieve your goal in your context, you pull in a bunch of cognitive modules, you leverage ECAN or other attentional control mechanisms on top of it. I mean, you have a self model that models what you're doing and regulates what you're doing. You can spread this across multiple machines, and you can also revise your goals in a way that's mediated by some goal stability mechanisms. Now, those of us who've been around a while would say, like, this sort of flowchart, like it could be Stan Franklin's LiDAR system, right? It could be GPS from when I was a little kid. The thing is, now underlying this kind of flowchart, we have the scalable dynamic metagraph framework that can represent everything in each box here in a unified way, right? So like the boxes are not separate modules with expert knowledge coded in some rigid way or something. The boxes are different views on this distributed dynamic, like self-modifying metagraph. And then you have LLMs, which help you interact with the metagraph, but also help the metagraph interpret itself within certain contexts, right? So there's a good old-fashioned AI flavor at this level, which is not surprising because GoFi came out of high-level modeling of cognitive science and how human thinking works. But at the lower level, you have a more ML type thing where you have a massive teaming, self-organizing knowledge graph with whether you call it logic or neural nets. I mean, you have localized, uncertainty-savvy, adaptive learning happening on billions to trillions of different links in a large network. Now, neural networks, I think, can be used here in a lot of different ways. I mean, right now within Omega Cloud, you just have a neural net there as a separate module from the symbolic stuff, helping the system understand things and helping it interact. You could also go full on and implement neural nets in the atom space, and you can think of various algorithms where like literally the algorithm is halfway between a neural net and PLN, because I mean, in the end, PLN is updating links in a graph by a certain nonlinear algebraic equation. A neural net is updating links in the knowledge graph according to a different nonlinear algebraic equation, and they're not as different as the semantic framing of them would lead you to think. In between those two extremes is where things are very interesting. And as we speak, one of my Omega Claw agents is playing around with basically taking a GPT-2 scale transformer neural net and training a predictive coding cap on top of it with a symbolic head. So you can take open neural models and you can train extra layers on top of them that connect that neural model with a symbolic knowledge graph. And I mean, but so by doing stuff like this, you can that's number two on this side. You can sort of go halfway in between, try to leverage what the mainstream AI world is doing and link it in more tightly. So if you could have right now I'm playing with this on GPT-2 scale, right? But if you had this on frontier model scale, potentially you could have like an open weight frontier model, train like a few tens of billions of parameter cap on top of it, which does continual learning and has symbolic heads. And then that links in directly with your symbolic knowledge graph. And this I think would take less time and cost less money than training a whole frontier grade model analog within an atom space, which also is quite possible. But you can play with a lot of different things here, and I think that's a significant part of the story. And it's very different than the LLM centric stack. I'm taking on too much time, so I'm not going to go through all these bullet points here, but people can look at this afterwards. But basically, in every key thing that a mind has to do, we're doing things a bit differently, yet in a way that can leverage LLMs for what they're good at, right? And I've kept it high level here, but there's a lot, like literally decades of research and prototyping into a bunch of specific mechanisms within this framework. So PLN, probabilistic logic networks, which has many different variations now. Also, NARS, Pei Wang's non-axiomatic reasoning system, which I've understood approximates PLN under certain assumptions and has some advantages under certain assumptions also. But these are ways of doing scalable uncertain logic reasoning. Then economic attention allocation as a way of figuring out which bits of a big atom space are important to look at a certain point in time. Moses, other related algorithms for scalable evolutionary program learning fits insanely well with Meta as a programming language with a transparent explicit semantics where a meta execution trace can be stored in the atom space as just more atoms. Predictive coding as a high-level paradigm for neural learning and variations like causal coding that I've introduced fit extremely tightly here because mathematically you're trying to find links that indicate how much one thing predicts another thing probabilistically, which is very close to what PLN temporal reasoning is doing on the logic level. And those are old things. We have a bunch of new things I'm not going to go into, but some of which I'll talk about in the main conference, which is a metamo as a sort of category theory derived way of organizing motivations, which has Joshua Bach's OpenPsi as a special case. Transweave is a mathematical model of how do you transfer knowledge from one goal-driven learning process into another, but sort of weaving together the Bellman graphs underlying dynamic programming processes. Weakness-based modeling, it's a way of taking different ways of formulating Occam's razor heuristics and expressing them mathematically in terms of a category theoretic construct called a quantale. So you can say that PLN is trying to find the simplest explanation in one sense. Evolutionary learning may try to find the simplest explanation in another sense. Say if you're using support vector machines to do pattern mining, the SVM is trying to find the simplest explanation in a different sense. So you may have different AI methods following different simplicity heuristics. Then you can formalize the morphism between one algorithm's simplicity heuristic and another. And I think this will become very important 6 months from now or so, once we've gotten all these basic algorithms to work scalably. And the main focus becomes how do you make them do cognitive synergy amongst each other. This is when looking at what are the Occam's razor heuristics in the different cognitive algorithms and how do you morph between them will become quite important. So there's a lot of math theory and prototyping underlying these different particular methods, which I think we should see cashed out in practice over the coming year, while also being open to completely new algorithms, popping up from the community and being implementable within this framework. So getting toward the end here, I mean, we can use this for pretty much anything, and I'm hoping it will be used for everything in the human sphere and beyond. I thought about, should we pick one domain and just hammer on this, because this is arguably the most rapid way to get to like obvious world-beating results, right? Eventually, I managed to beat the idea down in my brain because it just seemed like that's a well-known failure mode. Like if we try to just do math theorem proving or just do Cody the robot, I mean, there's going to be a very strong pressure to over-engineer things for that application. Now, of course, you could do that, raise $1 trillion and then diversify again, but that seems not to be how my brain works. And so we're not focusing on just one thing, but there's a relatively short list of applications that our various teams are looking at now. The open community can do even more. I mean, I think math theorem proving is very interesting, and I think once we have a scalable PLN inference control mechanism, we'll start to see where PLN abduction can help inject much needed creativity into the automatic math theorem proving process. Game worlds, I think, can be very interesting. We'll hear from Alexei Potapov on embodied learning in Minecraft and very simpler maze learning rules. I think other large scale sort of strategy games can also be quite interesting for moving toward AGI that can deal with long-term planning as well as short-term sort of tacticizing. Robotics, we'll have the Cody robot joining us here on Wednesday. We've got Omega Claw now integrated with Cody, thanks partly to the work of Patrick and Mike Archibald and others here in the room. So that's quite interesting. I mean, that upgrade right away. I mean, the main thing I thought that would give us was Cody would have a long-term memory, and like when you said hi to him last week, it'll remember you the next week, which wasn't the case before. But we're already seeing a bunch of other cool things to pop up from upgrading Cody from LLM ++ to Omega Claw based control loop, and it's only been working for a week or less, right? So already being very interesting. I think there's a lot that we'll get from that. And then bioinformatics with Kennedy and Mike Duncan and some others here. We've been working for a while toward having PLN help with longevity biology, and it actually is doing that to an extent now, right? So this is different sort of application, less of a real-time control aspect than in robotics or gaming, but you do deal with a lot of weird uncertainty and ambiguity of different sorts, more so than in the math domain. So I think there's something unique to be derived from that domain also. So we're playing with these different methodologies as well as using Omega Hive to try to do AI research to help you do research in improving its own mind. That's already a lot of stuff for a relatively small organization like Hyperon and SingularityNET. But on the other hand, I'm hoping as an open source community piles in and helps develop this stuff more and more. I mean, these applications they're partly just from my own interests and the interests that have bubbled up in our community, and you could do a whole bunch of other things equally well. This is all open source code with permissive licenses, and we've had a bunch of internal debate about what permissive license means. But in any case, it's not just open weights, right? It is actual open source code. And I mean, I think it's great if people build proprietary software applications on top of it. And our company BGI Labs may soon do that in some application areas. But I think it's important that the core infrastructure should be free and open in relevant senses. And again, the world is teaching us lessons on that right now with the various hijinks of closed source big tech companies. And I think the lessons in that regard will get more and more intense, whereas the positive aspects of the open source community will get more and more obvious also as you get people piling in from all over the world contributing. And like right now, researchers in China, Russia, or Iran can contribute to Hyperon codebase, right? And regardless of whatever bizarre laws governments might make. And that fact alone should accelerate progress on open source infrastructure tremendously. And I mean, on the one hand, being open brings new risks in theory if you trust people running the closed projects, which I happen not to, but I mean, openness brings different sort of risks. It also brings more people thinking about how to make the governance layer of your system and how to make the system have nice properties like goal stability under self-modification and so forth. And we have built the architecture with these sort of favorable properties in mind. So again, we have a core infrastructure now. We have working prototypes of many cognitive algorithms and an overall operational framework. We have a clearly laid out design for building really a whole mind based on this. And we're in the midst of implementing that design while revising and improving it as we go. And really the core bet here is by actually trying to architect a whole mind. You know, you can get to a whole mind better than by building a system that does some narrow thing and then ad hoc glomming on a bunch of other components and glomming on a bunch of guardrails, right? And the irony and beauty of the current situation is without coding models and claw agents and stuff, it might take us 5 or 10 years to build all this even now. But what we're seeing is we're able to advance incredibly fast by using LLM and claw tooling to implement this quite different cognitive architecture. And yeah, that is the whole deck I prepared. So so yeah, what we have for the rest of the day is a series of talks and discussions, sort of digging in more depth into a few of the aspects of all this, because I mean, you could have we did a 3.5-day workshop just on PLN with about 10 or 12 people involved just a couple months ago, and that was high level, and we weren't able to dig in full detail on each aspect of PLN that we wanted to, right? So that, I mean, that there's a lot here, but at least a day is something. So I'm excited for all the discussions we'll have.
And Alexei, are you ready?
Unfortunately,
Hi, can you hear me?
global software discussion is somewhat international.
What's that?
And global integration.
Excellent, thanks. Give us just a moment, Alexei, to make sure that the microphone's hooked up. Alexei, can you try talking and we'll see if we can hear you.
Yeah, sure. So can you hear me?
Not hearing you yet. Let me see if the volume.
We have a small office.
Test.
Is Alexei presenting now?
He will be, yeah. Just a moment, Alexei, just switching the speaker output.
I was gonna ask, is the list of speakers fixed for this for next workshop for the workshop?
Yes.
One second question for you.
Just one second.
Yeah.
Try,
Test.
it says it's not working. Give me just a moment.
Okay.
Pull a cord out.
I'm on national, so the island off the coast of the island. So we do have a small office on that.
So we're, formally push this back, and that's also.
We can't push Gary.
We haven't, yeah, we haven't.
We cannot push Gary.
I mean, yeah.
But for the lump sum.
I mean, we'll push our agenda and consciousness can push theirs. But the main stage has to happen.
My quick question.
Thank you.
Awesome. Thanks so much. Everything else good?
They want those people back.
We'll find out. I mean, good enough.
Okay. Text me.
Yeah, thank you.
Yeah.
Everything, all the other rooms are,
Okay, but.
yeah, thank you.
We're good.
6 months ago, they were but they see folks about. You mean. So there's.
Lately, people are putting Microsoft, people have done the same thing for that very reason, because nobody. But by the time you play it, it's already. It's still right. Well, no, it's downtown.
Okay, Alexa, can you try speaking now? Oh, no. Is it? No. Oh, you're muted, but I think our speaker's not on.
Okay, so
I'm a little. I'm a little. Just you have one of us. It's a lot of you guys like pictures and you go evidence.
The guy who's done all the navigation and the actuation of the airline, they got in the last guy. This guy has massive. No, I think just now, strong organization saying the US. We may have used ours. I'm still not available the opposite in Canada. We have people from overseas and Canada's same from the Ethiopia team, I wanted to come to.
This one is like a single.
I used to Hong Kong. But we may have these. You haven't even been to the house in the whole time. Because we have Singularity building blocks. How many people are working on this?
I know, right? I mean, I have all sorts of wacky and Earl Grey and
not counting Half of those are relatively junior developers and probably what makes it fuzzy is that you can't run on those additional which is mostly but on the other hand, if you start training becoming caps on Kenny to in that field, they have to then they probably
It's just won't play through the TV speakers, so we won't be able to hear Alexei, except like laptop speakers.
Is it maybe the HDMI itself?
Could be.
But that would be bizarre.
We've got another one, it's just short, but we could try it.
Yeah, the pretty
Yeah, sometimes I Heller, is there another session or right now? Yeah, we're going through our Hyperon right now. Yeah.
Well, now they
audio.
Yeah.
So that's a microphone. Sure, but that's just the microphone.
Yeah.
I'm sorry, Alexei. We can't get the audio working. How do we go into settings?
All right, we're re-permuting the schedule. We're gonna have Patrick talk about Omega now, and if there's time, I'll say a few words about Omega Hives after that.
Yeah, so
Then 12:15, we have Gary Marcus. 11:45. 11:45, we have Gary Marcus. Is that plenary then?
11:45 is plenary, yeah.
Okay, so 11:45, we'll have Gary Marcus out there, and Alexa will have to go after once, I think. So we should,
Yes.
if you can't see it that way, just have her
Record,
okay.
We need to turn this microphone off when you have a chance. Mute.
Now,
Yeah, it takes a while. Oh, wait, we can, no? Let's do this.
Or maybe okay. Oh, perfect. Okay. Then. I think his microphone is on. Oh, perfect. Yeah, so I guess I can start. So we will talk about Omega Claw and also oh yes, a bit louder. Like okay. 5 times louder. So we will discuss Omega Claw and also how this architecture looks like, and also what is unique about this system. And we will also see some unique characteristics that this system has, and which also in the context of the Hyperon project, with the different reasoning systems we have, like probabilistic logic networks, we want to incorporate this into one agentic system that can use reasoning tools. For instance, if we look at the mathematics community recently, they use LLMs to generate checkable proofs, which then a proof checker can actually look at and proof see if that proof is correct or not. And that also addresses one of the biggest issues people always had when applying LLMs in practice, which is how to make them reliable. If you let them generate something and you have a symbolic system that can actually check the proof, then you overcome this limitation. You can essentially use the LLM to generate proof for you, and then automatically let the reasoning tool essentially
check if that output is correct or not. And that's a very powerful combination in principle, and it's also something that can not only be used in mathematical reasoning, but also in empirical reasoning. And this is all probabilistic logic networks is about. You don't only reason in the mathematical domain, but you have an actual agentic system or AGI aspiring system that takes in observations from the environment and has to make sense of these observations. And this brings us to one of the issues that appear there: how to track evidence, how to track whether a hypothesis you have about the environment is supported or not. And in the long run, we want agents that are able to explore the environment based on hypotheses they generate about the environment, and then actively test it out, collect evidence, and use probabilistic reasoning to find ways to reach the objectives, essentially. So that's the broader vision here. So we are not only having a LLM chatbot here, but a system that incorporates probabilistic reasoning with real-time observations, coordinating this reasoning activity to make the agent pursue its goals and reach objectives reliably. So that's essentially the longer goal which we try to achieve, more far-reaching objective. But we already have now a system that can integrate these components, and this is exactly Omega Cloud. And I will show you now a few things that are quite unique to it. For instance, here there's quite a causal chat. I hope I can make this a bit larger here. So this was actually running Omega Cloud with a local LLM. This was running Qwen, running on this laptop, essentially. And we just tested the system, so it could record things, like when I asked it about the name of my brother, it could use its long-term memory and dig out the information, and also was able to do door calling, to download a PDF file, extract the text from the PDF, read the text file, summarize what has been what is inside of that PDF file, and essentially present it. But now we see here something even more fascinating, which I find more fascinating. The agent, it's a bit chopped off here. Here it wrote, I need quiet time for this. So it wants to investigate some topic and wrote me it needs some quiet time to investigate this. And that's interesting, because this is not something a normal coding agent like Codex will tell you. I need quiet time. Don't write anything to me. I need time to work out this topic. But that's something Omega Cloud does. And that's fascinating, because there's also a LLM inside. But the way this LLM is embedded is very different than how it's embedded in a coding agent, because in Omega Cloud, it's running a continuous loop. So even if there's no human input, it can work on tasks. It can essentially keep operating and working on tasks. And what's fascinating is also the LLM understands that it's embedded in a continuous loop and not in a request-response loop. So it writes things like this: I need some quiet time to work out this task, and I will come back to you later with the results. And so that's also, that shows some essentially some self-understanding of how it's embedded in our Omega Cloud architecture, and also understanding its own resource limitations when it's chatting with someone that takes cognitive resources. And how is this cognitive resource materializing in Omega Cloud? It's also running a LLM. There's a context window, and it has all these reasoning doors which it can call, and they generate results. And you end up with a lot of results, and not all of them will fit into your context window. And the LLM is aware of that. So that's one of the reasons why it writes things like, I need quiet time to work more effectively on the things it's currently working on. But we will look at this now from a more architectural standpoint, because if we look at this from a perspective of our architecture, So we have a system that runs continuously. It has a memory, long-term memory, where there can be millions of memory items. They don't fit all into the context window. So it has to have a way to record items selectively, like the name of my brother. So it has to be able to query its own memory for the brother of Patrick and somehow get back results that are relevant for that query. And that's where the memory architecture comes into play. We essentially have what we call embedding memory. So when you write something, when the agent poses a query to its own memory, it generates a vector embedding of that, and then records items that are close in that. So essentially a semantic way of retrieving related information from its memory. And that's one aspect of it. So we have the memory aspect of Omega Claw, but of course we have the continual operating nature of Omega Claw, which is how its operating loop is structured. So these are architectural features which deal with problems intelligent systems face when they deal with real-world environments. They will never have perfect evidence. They will be hypothesis-driven, but there will never be perfect evidence for everything, except in mathematics domain. You have observations, and somehow you need to map these observations to more abstract hypotheses. Like even something like a particular light switch activating a light. If you press it and the light does not go on, I can interpret this particular situation. Okay, I pressed the light switch and the light did not go on. But what if this light switch was mapped to another light in another room? Maybe it's not broken. It really depends on a lot of context of how to interpret a result. And maybe with the light switch, usually we place light switches close to the light. So if you press it, you have a direct evidence almost to say if the light doesn't change, it doesn't work. But in another situation, maybe it's linked to a door or unlocks something. You don't know immediately always, even though for light switches it might be more obvious, but not in general. So that's the first point. The evidence is incomplete. So we have to map the observations to the hypothesis about the environment, and then we have finite context. We cannot process all information exhaustively. When the agent operates over months, like Omega Claw now did in our communication channel, then it needs to selectively be able to retrieve memory. So, and also there's time pressure. You can give our agent a task and say, I want this task to be done in 5 minutes. And then of course the result you will get might not be as good as if you give the agent more time to work on, but it shows an important point that the agent can be aware of time pressure and can essentially take that into account to come up with a solution quicker. And so all this architecture is essentially built around that idea that the agent has to be able to operate under insufficient knowledge and resource, which is something intelligent systems are supposed to be able to handle. And for Omega Claw, there's of course the challenge. We have this continual loop with long-term memory, and we have these various cognitive components that are meant to bring benefits to the agent, like probabilistic logic networks. So it acts as a kind of a coordinator that uses these tools to operate more effectively, cognitively. So there's also another view how to look at the system, which is kind of a cognitive cycle perspective. So you already in the 80s, there have been many AI systems that have been described either as perceive, think, and act, or as some kind of cognitive loop, essentially, where observations go into the agent, and the agent then does something with these observations, updating internal models about the environment, for instance, and then acts based on this learned representations. And to some degree, this is also happening in Omega Claw. It's just a particular instantiation of this idea, where you have a large language model that that coordinates different cognitive components within the system, but there's still this long-term memory, so it's still within that framework. You have essentially perception that, for instance, with Omega Claw, I will show you a concrete example with real-time perception. If you have, for instance, a camera, you want to see Omega Claw, you can do that. You can stream in real-time perceptual data into this agent, which it can essentially interpret in real time together with its agent context. And we will see this in action in a moment. So there's also, maybe this I will skip for now. I will maybe first show this particular demo. So this was essentially, I hope the sound works here. Let's see. No, I'm not sure if sound is not working, but I think it's fine. I will show the particular pardon? Yeah, it will not, I think, because the sound for yes, but that's fine. So in this demo, you can see the URL here. You can also check it out yourself later. But essentially, there's a toy car in the background. And in this video, I just point to this toy car, and I ask the system what I'm pointing at, and it essentially interprets the scene and is able to tell me I'm pointing at the toy car. A couple of years ago, this was an extremely hard problem, having a machine interpret what you're pointing at. That's by itself difficult. If we think about it, a few years ago, computer vision was largely about detecting certain classes of objects where you had extensive training for each particular object category. Now we're at a time where we have open vocabulary, visual handling, where we can, for instance, just present a new scene to the visual language model, and it's able to interpret that scene. It's not always perfect. If you give it new objects, it will sometimes struggle. But often it's able to chain together description that fits well to that new kind of object you presented. And also, so there has been a major shift in what's possible with visual objects, not just object recognition, but entire visual scene interpretation, we could say. And so in this video, I asked it several things. I asked it what I'm pointing at, when I'm pointing at the toy car. I'm asking about the color of my t-shirt. I'm asking about whether I'm wearing glasses and things like that. Essentially demonstrating that these systems nowadays can fully capture the semantics of a visual scene in a way. So, but what's fascinating with Omega Claw in particular is that we have this continuous perception loop. So you don't even need to tell it what you are pointing at. If you're pointing at something, it will notice. It will notice, since the perception is not something that is triggered as a request response, only looking at the picture when I'm asking for it. Instead, it's always streamed into the system. So if I'm pointing at something, it will notice. So it's that's also a very important aspect, because if we look at the Primus ambitions, we want AI systems that deal with multimodal input, that can deal with camera input, that can deal with sound input, that have long-term memory, and are connecting it all. For instance, currently we see there's a big hype in terms of agentic AI, and there's a big hype in terms of physical AI. But clearly, these two branches of AI will converge. So you will see physical agentic AI. And you see this more and more coming, where you have agentic AI. Omegle is now one of the first instances where you can have real-time perception input in a continually operating agent architecture. So that's just one of the ambitions. But it also changes in a way how we look at state in AI systems. If we look a few years back, if we had things like grid walls, some of you might be familiar with the ARC-free challenge. It shows many different computer games and grid walls which our agent has to learn by interacting with the environment. A few years ago, reinforcement learning was still the dominant paradigm for handling such environments. But this is now also shifting in a way to have agentic systems figure out how to solve grid-walled puzzle environments, for instance. And this also changes state representations radically, because in reinforcement learning, usually you have agents dealing with particular state representations that are not as dynamic as in an agentic system. In an agentic system, you have this long-term memory where the agent can add memories dynamically, and you have essentially a dynamic state that never repeats. It never repeats. Agent creates new long-term memories, then this part of its state is already different. It will unlikely will the LLM ever see two identical context windows when dealing with any of these grid world environments. So the state does not repeat even anymore. And so it's completely different paradigm in a way. Even though the state in the environment might repeat, of course, but the internal state of the agent is constantly evolving, which is way closer to what an intelligent system should be handling. And or how to say, it's closer to how we operate. Our memories are constantly evolving. We don't go back to the identical cognitive state we have been a year back, for instance. We're constantly evolving that internal state. Anyways, we have also, of course, benchmarked various properties of this architecture. For instance, since we have our own memory architecture, it was also important to see whether its memory architecture is effective. So we used standard benchmarks like long memory just to show that it's actually closely trailing the state of the art in terms of memory recall rate. What's also fascinating here is that if we look at the complexity of different agentic memory systems, we can see that omega-close memory is still on the simpler end of memory architectures. And we see that the high recall rates mostly come from multi-cycle agentic retrieval of its memory. What I mean by that, for instance, if I let it search for my brother's name, it might end up with a query that might not directly, if it gets unlucky, it might not yet find the information it's looking for, but it can notice, in this query results, I don't yet have the information, so I need to refine my query, try again, and update until it finds the information it's looking for. So it's a completely different paradigm from different memory architectures where you expect no agentic cycle within memory queries. You expect the information just to be found. Well, here in this paradigm, the agent can spend multiple cycles to iteratively query its memory and to refine the ways it queries its own memory. So that was beautiful to see that this gets around, that gets you far with a simple memory architecture. Another thing that has been interesting is also that even though we have never tuned the system for ARC-free, and it's by no means a good ARC-free solver, but nevertheless, it managed to solve a few ARC-free style environments without any code corresponding to this challenge, which was interesting to see. that it's, how to say, that its capabilities kind of also include the ability to analyze like episodes that happen when interacting with such grid world environments. And so it was interesting to see that one could argue it has some quite general abilities in a way, because we did not hard-code it for that domain. But of course, the question is how much prior knowledge is in the LLM itself, which is also increasingly a topic, because if we look at when Act 3 was proposed, and now there are already LLMs that potentially could have included the public parts of the data set in its training. Potentially, of course, we don't know. But it's increasingly getting an issue that we cannot really know if the LLM has not already seen this kind of environment. Another thing which was fascinating, this multimodal capabilities we have initially tested with our own Max Botnik instance, which is a research variant of Omega Claw, which we run in an internal MetaMost channel. And what was interesting is in the initial experiments, we essentially gave it a webcam input of a scene in Venice, and we gave it a quite general inquiry about the scene. We wanted Omega Claw to continuously look at the scene essentially and tell us like how often do tourist boats spot your dog at the dock here. And over 2 hours of observation, it was able to give us a very precise answer about how often the tourist boats, about every 12 minutes, are docking at this dock. So it was able to, how to say it, to continuously operate and interpret the visual input in a way that it's able to track how often tourist boats dock at the dock, and then give us an average time between docking events, which is quite cool, because we did not program the system to identify tourist boats, or we did not program it to explicitly track how often tourist boats dock at this dock. We did not program that in. It's just something we told the system, please tell us, essentially, and it figured it out. Maybe here it works now, actually.
Can't hear you through your text just fine.
Oh, now it works. Actually, I should have started it there. Can you hear me? So this is real-time mode.
Yep. I'm giving you a message. Let me quickly check what I've got on you. I can't hear you through your text just fine, and I can see you in the webcam frame. If you're testing audio, try saying a line out loud, and I can help you check levels or clear.
What is the color of my t-shirt? What is the color of my t-shirt? I'm asking.
Your t-shirt looks light blue.
Okay, that's correct. And what am I now pointing at?
You're pointing at the small dark car model on the windowsill, the one on the right.
Correct. What do you see outside of the window? What do I see outside of the window?
Trees and greenery outside the window. It looks like a leafy outdoor area with natural light coming in.
Good, that's correct. And do I wear glasses or not? Do I wear glasses or not?
Yes, you're wearing glasses.
And what hand gesture do I make? What hand gesture do I make?
You're making a thumbs up gesture with your left hand.
Correct. Thank you so much, Max. Goodbye. Yes, you see,
Goodbye.
Can really
And have a great rest of your day.
Interpret the scene. And what's fascinating is, maybe I can also show that. Just 1 second. I have to dig out the video, because you saw this real-time ability to interpret the scene. And of course, this is also something that is extremely relevant for robotics. And we will now see a very quick recording. So this was unfortunately a bit small, but essentially here we tried running multiple experiments on the Cody robot. And one of the experiments was a game of hide and seek. So the idea here was the person at first sits in front of the robot. The robot looks at the person, has to find features of the person that are sufficient to re-identify the person. So the robot looked at the person and generated a memory saying the person is bald-headed, is wearing glasses, has a dark t-shirt, has a beard. So it's used a verbal description where it then said, okay, I will use this verbal description to find the person later. So now the person moved out of the way, and the agent, Omega Claw, had to move the robot around to find that person again, which worked 2 times. So here, 1 time, you see it moved over there, and then also another time. So now he moved back here. The robot is first looking here. Person is not in view. Zoom. No, I cannot zoom in here, unfortunately. But essentially, robot found the person again. So the fascinating thing is, it's all these different architectural principles come together. Continuous operation. It's not request response. It can act, look, act, look without any new human input. Continuous operation. Second, long-term memory. Looking at the picture, extracting relevant description of what it's looking at, storing it in long-term memory so that it later can record it to re-identify the person. Second feature. Third feature, multimodal input, vision input bombarding the system so it can look at what's in front of it. And all these architectural principles, even though in isolation, you would say it's nothing special. We have vision systems for a long time. A continuous loop is not complex, it's very simple. Long-term memory, we had agentic memory for a long time. But in combination, these things are powerful. This is what gives rise to capabilities like that, which is really nice. I'm not sure how much time I have left. Oh, okay, that's good. So, and the next thing, which is architectural principle, which will be more and more important if the agent should learn new things while it operates, is to track evidence. And in the Hyperon project, we explored many different empirical reasoning components to make that happen, to allow an agent track, formulate hypotheses, use them to chain them for planning and so on. And this is something which we will now more and more investigate, since the other architectural pillars are quite solid now. And now different reasoning machinery will be incorporated, like geodesic inference control, scalable inference control. So it can then essentially in its memory architecture, not just create long-term memory items, but also track different observations that correspond to these long-term memory items, so that it can then formalize and assign uncertainty values. So for instance, there might be something unreliable in the environment, like light switch. Maybe if you don't press it strong enough, the light doesn't go on. So you press it 2 times, it works. Press it 1 time, not strong enough, it does not work. And then the agent tracks in an explicit long-term memory item, this switch turns on this light. And then it tracks the episodes, cases where it happened, where it worked and where it did not work. which then gives rise to the ability to assign a truth value to it, to do probabilistic reasoning to say, okay, in 2/3 of the cases, this switch works, and this other switch works 100%. So then most likely it goes for that switch, which is all probabilistic reasoning is about. You have different ways to achieve an outcome, but some ways are more likely bringing you the objective you're interested in. So it's very important to keep track of this kind of probability assignments. So that's essentially the larger picture here, and I hope, I mean, my presentation was not as systematic as I wished it to be, but I hope I was able to show how far we have come in AI overall, how close we are to systems that can navigate the complexities of the real world and deal with things which few years ago was completely impossible. And so I hope you enjoyed this presentation. And
Yeah, thanks a lot, Patrick. So
welcome.
I think I have a follow-on that I'll end up doing after lunch, which is about that.
Testing, if anyone is trying to hear me.
Welcome. We are currently being live streamed, and we're waiting a little bit for the main room to get ready.
Okay. Hang on. I'm not here. Yeah, you are coming in very soft. Do you hear me okay?
I can hear you, but we haven't got you on the speaker yet, so I'm just going to get that sorted so we can
Oh,
just test it.
now I hear you just fine.
Oh, good. Okay,
Maybe
you
it's
can
microphone
hear us, but how do we get it up on the speakers?
So you hear me, but not on the main stage or something like that.
Yes, we can hear you, but you're not on the loudspeaker yet. We've not got Ben here yet anyway. They're moving along from the workshops. Alec, when you look at the Zoom on the main screen, is you might see.
Well, we're going to be done after. Thank you very much.
Hello and welcome back to the main area. We're just going to get started with our first presentation of the afternoon. We're just going to get started with our first session of the afternoon. We've got two quick sessions for the main breakout area. First, one timely event today, and I apologize to the workshops that had such a late start with the streaming issues. We'll get started with that, and then we'll have a presentation by Anil. Afterwards, we'll have lunch. Lunch will be box lunches. They'll be back on the back table, and then you can just find space around or outside to eat, network, talk, and continue these beautiful, fruitful, synergistic AGI creating conversations. After lunch, AGI will be solved. I'm sure somebody here will have taken care of that. And the rest of the conference will just go to the beach. So no. After the conference, we'll continue with the workshops. Consciousness will continue, Hyperon will continue, and then we'll have active inference in the room where INLP was earlier. So without further ado, Ben, actually, we'll kick off. Let's see, can we get Gary up on screen? Our wonderful AV team who has been doing everything everywhere today, Vernon, Alec, and the team. I do see Gary's in, so. Beautiful. So he'll be virtual and you'll be live, and it's a chat. I think we can turn one of these on if you want a handheld.
I guess. Yeah. What? I guess I can stand here.
You can stand here, yeah.
Right, so this is not it though, right?
Not it.
So
are we able to get Gary? Great, thanks, Alec. Haley, we've got to put it up here. What's that? You can't hear it. You've got to put it on my laptop. You've got the details just to log in on there. We just told you now because we could do a sound check and they said.
So okay. We don't have Gary yet?
We do have Gary.
Can you hear me?
Oh, goodness.
Do you have the live stream?
All right, we should get Gary Marcus on the big screen soon. He said he had a hard stop at 12:15, so this may be a brief, concentrated dose of Gary Marcus wisdom. And
Ben, can you hear me? Even if you can't see me? Well, that's good.
Well, we're about half done. They don't have any confidence.
Alec, can you switch it so that I can share?
Ah,
Oh.
with the delay.
Hey, that looks like Professor Dr. Gary Marcus. All right. So
It is I. Can you hear me?
He can talk, but we can't hear him.
Uh-oh.
All right. So
people on
as
Zoom
long as the
can.
audience can lip read, we're doing great. All right. So the people on Zoom do hear. It's just that we're not getting the audio output now.
That's right.
So if the people on Zoom can hear, but the people in the room cannot hear.
It's a new version of the Turing test.
Which is the external.
Testing.
Again, Gary.
Testing. 1, 2, 3.
No, still no sound.
1, 2, 3.
Yeah, please.
Wow.
Yeah.
1, 2, 3.
Well, the dude has a hard stop in 15 minutes. I think
Well, the dude has a hard stop in 15
Testing.
minutes. I think we just missed it.
Yeah, perhaps.
Yeah, perhaps if we can get the
Testing.
local output, I can just hold the microphone up to here.
Yeah.
If the IT can't work.
You got that. You got that.
Yeah. There's a rainbow wheel, so it's giving me a moment.
Testing.
Maybe not. Maybe. Or yeah, let's just get one of you. If you do a handheld, I'll do Gary.
Okay.
And that way we don't.
If that even works. Maybe the sound's being eaten by the HDMI.
Give me 1 second.
Oh, yeah. So, can you try again, Gary?
Testing.
What's our- Whoa, we've got
Yay!
it. My.
Whoa.
Hooray!
All right, is this working?
It should be working or this should work.
Hello?
You can hear me?
Hello? You can hear me and Gary?
I
All
hear
right.
you.
Incredible. So now we have like 15, 20 minutes to explain the entire future of artificial and human intelligence and the fate of sentient beings in our light cones. It should be more than enough time. But in seriousness, yeah, it's great to have you again at the AGI conference, Gary. I'll be virtually this time. I know you have a hard stop at 12:15 Pacific, so we're gonna
I can go to
try-
12:20, Ben. I gotta give you a couple
12:20.
extra
All right, well,
minutes.
that's 12 is a little better. But there's obviously there's a lot to talk about, right? These are certainly high intensity times in the AI field. A lot of interesting stuff going on. A lot that you and I agree on, and a few things we don't fully agree on. But how would you like to drive this? Maybe you can summarize how you see the current state of progress toward AGI in the world today, and what's missing.
Sure. So, by the way, I get a lot of echo from hearing you, which is not easy. I don't know if there's anything that can be done, or if we want to mess with that. So here's my take. There is one very big leap forward that's been taken in the last couple of years that you and I would, I think, both agree is a good thing, which is the big AI companies are now actually embracing neurosymbolic AI. None of them are really admitting that out loud or publicly, but all of these things like harnesses and loops and tools and so forth are very familiar to you and me. We've been advocating for neurosymbolic AI for a very long time. And I think it's good that the field has moved from a really dogmatic position, which was basically like, take a feed-forward network, get constant time inference by just running something once through the network and call it a day. That's really what people were trying to do in the early 2020s. And they have stopped trying to do that. I think they have wised up and realized that purely scaling a large language model is not enough. And they have learned the value of doing things like harnesses that are symbolically written, calling symbolic tools, and so forth. And I think that's to the good. And I think that it has not produced AGI, but it has produced some very impressive results. And I'm thinking in particular of Claude Code is maybe the most impressive, but or Codex I think is pretty similar, though I haven't played around with it. So these tools are very good, but they're not AGI. And I think not everybody realizes this in the general public, though I'm sure you do, and probably most people in the audience do. What's missing is general intelligence. That's the G in AGI, the term that you helped coin, right? So we have very good narrow intelligence in some ways now, in some ways better than ever before. We always had some. We had chess computers that were pretty good for a long, long time. Now we have narrow intelligences that can do coding, and they actually require more breadth than just playing a game of chess. They're still limited in certain ways, but they're certainly useful and valuable. They speed people up. So we have that, but they work best, at least in my view, in domains where you can use symbolic verification in one or both of two places. Using symbolic verification in creating augmented and synthetic data, and using verification to make sure that the answer is right. And that's more straightforward in coding or in math than it is in a lot of kind of everyday reasoning problems. And I think the everyday reasoning problems we have not really licked. We still see lots of hallucinations, lots of kind of boneheaded reasoning errors, just like we did a few years ago, maybe fewer of them. Of course, as you train on more data, you're going to catch more cases, but there are still lots of edge cases. We're still not handling them. What's missing in my mind is still world models, which is something I've been arguing for a very long time. If you go back to my 2020 paper, The Next Decade in AI, I argued that you needed four things. One of them was neurosymbolic AI, but I said that's necessary but not sufficient. And I think that's where we are. It is helping, but it's not sufficient. Then I said we need everyday common sense knowledge to be accessible. We need stronger forms of reasoning, and we need world models, or I call them cognitive models there. And we still need that. If you're not reasoning relative to a model, there are limits to what you can do. There may be higher than some people expected, but that is still, I think, the rate limiting step here. Other people have also talked about things like continuous learning, which I think are secondary to having world models. To have continuous learning is to be updating a world model over time. So that's where I see it.
So yeah, let's dig in a little on world models then, since this is a AGI conference, and it is clearly a critical aspect. I mean, I totally agree, as I think most people in this particular room will, that the capability of world modeling is critical to human level, superhuman general intelligence. I guess there's a question of, do you need or want to treat world modeling as a sort of separate structure and dynamic? Or is world modeling just something an AGI mind does in the course of trying to achieve its goals and live in a world in a suitably flexible way? I mean, how do you think world modeling should actually be done in an AGI system?
So I think that, well, first of all, I would start with a kind of computer science perspective. There's a famous book, Algorithms Plus, or what is it? Programs equal algorithms plus data structures, or maybe it's the other way around. And world models are data structures, right? And they have with them a set of tools for updating them. And in fact, there's lots of kinds of world models. Some of them we've had for a long time and work great. Like GPS navigation systems have world models, the very specific ones, right? And there are procedures for updating those world models. There are procedures for interrogating them, making inferences relative to them. So world models are not something new. I mean, Herb Simon was thinking about them in the 50s, and his autobiography was called something like Models of My Life, right? They're not new. It's just that large language models, despite their name, don't really have them. And we need to bridge these worlds. Neurosymbolic, I think, is a prerequisite to that. But once you get into it, well, you can have a lot of different world models. They may not even be consistent, or maybe they shouldn't even be consistent in the sense that, for example, you can have models of fictional worlds too. So I happened to watch Project Hail Mary last night with my kids, and it was fun. You know, they're 12 and 13, to see how rich the model they could make of the movie, right? The movie has a different world than the one that we live in. So in the movie, there are aliens that are known to humanity. Maybe in this world, there are aliens that are not known to humanity. But they had to construct, in order to understand that movie, they had to construct a model of this fictional world and understand that there was this alien that could do these particular things. I don't want to give away too much about the film. And if you haven't read the book, you should. But so, you know, when you read a book or when you watch a movie, you construct a world model. You also do it in sort of micro form, right? So I'm constructing a model of the conference right now. I'm not even there, but through video, I can see you. I can have, you know, estimation of maybe the size of the crowd if the camera ever goes the other way, etc. Right? So we are constantly building world models. I think of a world model as a representational form that affords inference. And it needs other things that go with it. It needs procedures that go with it in order to update it. There may be some world models that are entirely fixed, but like even when you get to a game like chess, you have to update that world model as somebody else makes a move. And I think people are looking for a magic bullet here that's maybe not realistic. So if you think of a world model as a kind of data representational form, but it has procedures to update it, those procedures are going to vary, at least to some degree, depending on the kind of content that you're updating. There's a separate notion of a world model, which is Jan LeCun's notion, which I think is just like a neural network that can predict some state over time. And I don't think that's good enough. I think you need to have explicit representations that you can reason over. That's the sense of world model that I think is critical and that I think we still don't do very well. Like, we know how to build world models innately from scratch in particular circumstances, like for the game of chess. Or do you remember Cicero, the diplomacy game system that Meta made that was pretty cool? You know, that had a very detailed model of the world that it was playing diplomacy in. And it was entirely innate, right? We need to have systems that can read something and construct a world model around the thing that it's reading, or watch something and construct a model around the thing that it's watching. And that's hard. It's very hard.
So yeah, the way I think about world models, I think it includes what you're describing, but I sort of think of a world model as a sort of complex dynamic network, which in a neurosymbolic system, it would span the symbolic part, which has an abstract symbolic representation of aspects of a world. I mean, the neural predictive submodels, like in JEPA, and better approaches than JEPA, which are also doing neural aspects of world modeling. I mean, those are certainly parts of it also, and then you then have some feedback between neural and symbolic pieces of a world model. I guess the big question is, what's the method that can work for scalable learning of world models via AI systems that are interacting with worlds, right? Because as AGIs, we're able to sort of do some learning that leaps a bit out of our training distribution. And this includes, among other things, modeling worlds that have aspects that are quite different than the ones we were trained on before. Like all of us learned to model the internet, who were born before the internet existed, right? Like, and we built a model of what's happening there. So how are you thinking about scalable sort of unsupervised learning of neurosymbolic world models?
Well, a couple of caveats and agreements, and then the main part of your question. So I don't know if it needs to be entirely unsupervised. I mean, maybe it does need to be supervised to some extent. Maybe our construction, I'll call us NGIs, natural general intelligence, some of our construction of world is supervised. You know, I might say to my kids, "Do you understand what's happening in that scene?" And that's a flashback. And and so I think we can be open in our construction of as humans of worlds to, for example, direct pedagogical instruction. That's some of what we do in schools, right? Is we actually help people construct the world. And more generally, you wanted to take an expansive notion of world model that's even broader than the one that I'm taking. I think that's fine, in fact. So, one thing I didn't mention, for example, is you want to have a lot of distributional information in there too. And neural networks happen to be good at that, and they might be the right way to do that. So, your world model, for example, of New York City might tell you that, there's more traffic during the day than at night, except, when there's a concert or whatever. And some of that will be statistical. Some of it you might be able to reify and express symbolically. Taking even a further step back, I would say that it's essentially a scientific-like process to construct a world model. There's a lot of inference to best explanation. There's a lot of synthesis of different kinds of information. You might need innately the capacity to represent a world, and then you reason over that information. So when you watch a movie like Project Hail Mary, which obviously is fresh on my mind since I saw it last night, you do a lot of model construction that is basically inference to the best explanation. What could be going on that explains this? So first you have to recognize that these two images of this guy are the same guy. And, it's not immediately obvious because one of them has long hair and one of them has short hair and so forth. And you have to guess, well, there's nobody else here. They seem to behave similarly in this respect. Maybe they're the same. I'm going to tentatively integrate them in my world model and suppose that maybe these two images refer to the same person at different times. It's a lot of reasoning, a lot of scientific inference. It may not be with like masses of data, but you're reasoning as a scientist, proposing hypotheses, confirming them. You may do that explicitly. Sometimes you do it implicitly. I think a lot of stuff goes into the maintenance of world models over time. I think that different creatures probably do that to a kind of different resolution, not literally in terms of pixels, but amount of detail. I think that you may form a more detailed model of something that you're interested in than something you're less interested in. Like if you read a novel with full attention, you're going to have more detail in the model that you represent than if you read a novel and you're less interested and you just kind of want to know the plot points. There's a lot of variation, but fundamentally it's about inference, and a lot of it is a bit like being a scientist. Alison Gopnik's stuff about, child as scientist. I think that in general, we all do a bit of that. And the process of building a model and updating it is like that. And it's not perfect either, right? So for example, we know that sometimes people will disregard disconfirming evidence relative to a theory that is embedded within a model. So humans are not perfect at this at all, but we're surprisingly good at it in the sense that, like, if everybody goes to Project Hail Mary and watches, at least every adult in the room is going to, by the end, understand fundamentally what happened there.
Yeah, viewing world model learning as a form of scientific hypothesis formation and validation is interesting and makes me think about different views of the philosophy of science, right? Like if you go back to Thomas Kuhn observed, like you can sort of view scientific theorization in a reasonable, like traditional Bayesian way within a certain paradigm where you have some observations that are taken for granted, some terminology that's taken for granted. And then it was observed that that doesn't really explain scientific revolutions tremendously well. Then you had guys like Imre Lakatos saying that, well, it's about coming up with a research program. And then within that research program, you can do everything in a well-defined sort of probabilistic way. But coming up with a new research program that gives a new way of grappling with a new area, like that's not within any paradigm. Then you had Paul Feyerabend, who I knew briefly, had a book Against Method, where he's arguing like it's anything goes, like each scientific revolution has a new way of discovering things, which we then rationalize only in hindsight. So when we start thinking about world modeling by analogy to the process of historical scientific discovery, it seems like within a certain species of world, like learning new MMOGs or something, or learning how to navigate new social situations or drive new vehicles. Like within a certain category of world, there's a sort of rational, logical, probabilistic reasoning process you can imagine using to make new world models. Then when you're learning about a new kind of world, then that's like a new scientific paradigm or something. And humans have been able to do that in some measure. Like we can deal with the internet and the worlds inside the computer, which arguably have some qualitative differences than the worlds that our bodies and brains evolved for. So it makes you wonder, like, what is the cognitive machinery you use to learn to model a different kind of world than we've ever dealt with before?
I think this is exactly why AI should pay more attention to cognitive science, and especially to developmental cognitive science. So, for example, Susan Carey has spent a lot of time looking at how children learn integers. So, you start the world, you don't understand integers, though you may have some pre-theoretic notion of quantity and amount and so forth. You are constructing part of a world model when you figure out what an integer is. And it'd be really nice to know how kids do that. And we now have a bunch of empirical evidence from her lab and others about that process. That is, in fact, constructing something. Thomas Kuhn's stuff is all about paradigm change. We don't do that every day, but we do it some. Learning about integers, learning about the internet. Those are cases where we do construct a new model that is different from the model that we had before. I've always thought this is one of the most interesting things in cognitive science, how you can construct a fully new model, or maybe it's not fully new, it's bootstrapped onto some prior notions. But that process of bootstrapping a new model is super interesting.
A bit, right? Like, I mean, like web robots were called robots by some analogy to robots. And we talk about navigating the web. Like we bring some biasing and priming from prior experience, which is often misleading and sometimes positive. But like you say, every 1 or 2 year old kid, although they do have inductive bias, they're also dealing already with the world very different than what their brain is biased for, right? And they are able to formulate new models. And even as old people, we're able to do that like now and then, sometimes during our lives. And that is very qualitatively different from what any current deep neural net architecture is doing, where they're in a much more shallow way extrapolating from current knowledge, but it's also different than what historical logic-based AI systems are doing, right? And it is something that cognitive science touches on, but cognitive science can't tell you what are the micro-level mechanisms for enabling it yet.
That's right. There are some areas like inductive logic programming that have grappled with this a little bit. Some classical AI approaches that are not particularly popular, and they've never scaled very well. They've always kind of worked on toy models. Probably someone in the crowd will know it better than me and shout that it's been done more than that, and that's fine. But in general, I think ILP has not done this on a grand scale, but that's a place where people have thought about these kinds of problems. But yeah, you just hit the crux of why I don't think AGI is close. Is I think that getting systems to do this kind of process that I've been talking about in today's conversation with you is really critical to getting to genuine AGI. I think we've discovered that you can do approximations for a lot of things that are super useful with LLMs or LLMs plus a harness that are neurosymbolic or whatever. But I don't see any current AI work that really addresses how you would construct and maintain models over time. And I think that that's what's fundamental. And so, my guess is, since nobody's really working on it, it's going to take some time to figure it out. It is also true to the positive that in the last few years, people have at least talked about the problem of world models in a way that they weren't before. When I wrote about it in 2020, nobody paid any attention whatsoever. And now, you have Fei-Fei Li's company, you have Jan's company, et cetera. So people are at least talking about it. I don't think Jan's doing it the right way. I don't know if Fei-Fei is. But people are at least contemplating the problem, and that's a prerequisite to solving it. But my guess is it's really a hard problem, because it really is a problem about induction and representation and causal principles. And those are things that we have not really been focusing on lately. And so we have a bunch of new tools to help us with that. But I think it's non-trivial, let's say.
It's a hard problem. And I think we've agreed on what's one of the critical problems that needs to be surmounted to get to AGI. I mean, as you know, my colleagues in the Hyperon project and I think we have a solution to that problem, but we haven't demonstrated it yet. But some of our technical discussions reflect these more general themes, though. Like within our probabilistic logic network effort, which tries to do this sort of learning using abductive and inductive logical learning, we've had a running debate over the last 6 months over when can you assume there's a common probability distribution over the whole system's experience, or should you not do that? Should you assume the system represents its whole experience in an inconsistent way, and it cobbles together a distribution for a certain inference that's doing it at a certain point in time, right? Which sort of hits at this within paradigm versus cross paradigm learning, because
exactly you have to make those kinds of decisions. That's not the only one, but that's the kind of decision you have to make as you construct a model of the world. Is this like the other thing? Do I have to make a new category here? Does it work differently? Those are the kinds of questions that scientists consider, I think children consider, and that AI has not considered. And I have to go in a minute, but I'll leave you in the room with this thought, which is, I think those are deep questions. They're unsolved. A lot of people think, well, AGI is just a matter of a little bit more scaling, so there's no interesting research left to do or whatever. I think, in fact, that good answers to those kinds of questions that we're talking about here could actually radically change things. Now, probably you don't want to just dispense with everything that's been built over the last several years, but if you can find a way to integrate that stuff with systems that can actually reflect on hypotheses about, when do these things, when are they alike, what are their properties, and so forth, I think that could be a giant advance. I think that means there's still plenty of room for the people in the room assembled, and I'm sorry I can't be with you today, to come up with some breakthrough that takes us way beyond what we are in terms of the conceptual power of the systems being developed. So sorry I got to bounce to do a TV interview, but this was super fun, Ben, and good luck with the conference.
Well, thanks a lot. Hopefully next time you can come face to face. We can really
be awesome.
dig in.
See you next year.
If we haven't achieved AGI already.
Take care.
Thanks a lot, Gary. All right, that actually hit a lot of the same themes we were discussing in the Hyperon workshop this morning, except there, a bunch of us think we know the answer and just have to deploy it at scale and prove it. But I think the framing of some of the core issues there was quite nice. So let's I guess move on. There's one more plenary thing now, and then lunch, and then we're back to workshops, right? Take it away, Haley.
Thank you very much, Ben. Thank you, Gary, though Gary is gone. Wonderful. Okay, so next we have Anil. And there, he's in the room. So let me see. Alec, do I share video from, or you've got video? Okay, great.
Hi.
Hello, Anil. We're just getting you up on screen.
Brilliant.
So good to
I'm just going to see if I'm going to have to do this sharing screen thing. I was just listening to Gary, so that was good.
Yes.
And let me see here. Portion of screen share. Okay, so play. Is that working projection wise?
Just one moment.
We don't know yet. That's right.
Yeah. Oh, okay. All right. Yes, we can see your screen. All right. Thanks enough for joining us here today, and take it away.
Brilliant. Well, thank you for having me. Yeah, just to check, you can see the title slide, Prospects and Pitfalls for Conscious AI. Yes? I hope so. Yeah.
Yes.
Yeah, great. Well, thank you very much. Sorry I can't be with you in person. I was actually in San Francisco just over a week ago, and I'd love to have been able to stay, but I had to get back. Anyway, thank you for inviting me in any case. So I want to talk a little bit about something that's, surprisingly, at least for those of us who've been working in consciousness science for a while, surprisingly in the news for the last, I suppose, few years now. And this is the idea of whether AI could be not only smart, but also conscious. Now, we've all remember this chap, Blake Lemoine. He often gets talked about in these kinds of things. Maybe he was the canary in the coal mine. Maybe he was the first person to sort of really hit the headlines about it. But a few years ago, he claimed that the chatbot he was working on, kind of pretty archaic one by today's standards, Lambda from Google, was conscious. The headline calls it life. That's interesting. But he thought it was conscious. He was kind of fired. Well, he's not kind of fired. He was fired, not necessarily for being wrong, but for breaking confidentiality. But it was certainly not the sort of thing that was sort of said at the time. That's, of course, all changed. I'm sure you all know, in San Francisco, Anthropic last year didn't fire anyone. They hired somebody, a full-time AI welfare expert, to really look after the potential welfare interests, not of people interacting with language models, but of the language models, the chatbots themselves, on the basis that they may be conscious, that they may have their own welfare interests and potentially rights. And he's not alone. Just earlier this year, Richard Dawkins, who has been a great inspiration to me in his work on evolutionary biology and his public communication about this, decided on the basis of 3 days talking to Claude, or Claudia as he called it, that Claude was indeed conscious. I thought this was kind of interesting because he basically made the argument that he thought Claude must be conscious because he couldn't imagine having such a sophisticated conversation with Claude or Claudia unless that was the case. And this is exactly the same argument from personal incredulity that he warned us to be very wary of when thinking about creationist arguments in opposition to evolutionary theory. Anyway, it's out there, and it's also people who are right in the middle of the field. Hopefully you can hear this. This is Jeff Hinton on LBC News in London last year.
All the way through the development of computers and AI, people have talked about consciousness. Do you think that consciousness has perhaps already arrived inside AI? Yes, I do.
So that's it. Jeff Hinton thinks it's already here. It's here, and he doubled down on this actually the other day in another podcast interview, basically unambiguously saying conscious AI is here. And if people like Jeff Hinton are saying it, and if it's in the news, and Richard Dawkins and so on, it's no surprise that it's quite a prevalent idea now. At least it's not a fringe idea. And people like David Chalmers, a good friend and colleague, and one of the foremost thinkers about consciousness and AI, he also thinks that it's not inconceivable that within the next decade, language models might be conscious. So the question we have to address is this: can artificial intelligence lead to real consciousness? And in the next 30 minutes, I want to take you quite quickly through a pushback against that view, pushback against the idea that AI either is or along current trajectories will be conscious. So there's a little bit of background, some biases and confusions that often surface in this discussion, and some definitions too. We need to define consciousness and intelligence if we're going to ask whether and how they're related. But the main part of the talk will be a sort of gentle pushback, or not so gentle pushback, against the idea that's sort of a basic assumption that makes conscious AI in principle possible, which is the idea that computation carried out in silicon of the right kind will be enough for consciousness. This is a common assumption called computational functionalism. I won't have time to really lay this out, but there are other games in town as well. My own view, which I think is defensible, is that biological properties might be necessary for consciousness. This is called biological naturalism. Now, I want to say right away that I don't need this to be true for the assumption of computational functionalism to be wrong. Right? I don't have to believe there's something special about biology in order for it still to be the case that computation is insufficient for consciousness. But we'll get there. And I'll finish with things to worry about, because we always need things to worry about. For the longer version of all of these things, if people have the appetite, there's this Target article in Behavior and Brain Sciences, which has been out for about a year. But I've just finished the proofs for the response to what was really a rather large number of commentaries from my peers. About 50 commentaries were published on this paper, and I've just finished the response to all of them collectively. That should be out pretty soon. It's not out just yet. Okay, now for the background. What I want to say here is that it's not a new idea, this idea of artificial consciousness. You can go back in history as far as you like. This is Goertzel, the golem in Jewish folklore, created from sand of the banks of the river Vltava in Prague. And activated by magical incantation, it became conscious and started wreaking all kinds of havoc. Frankenstein, which is a wonderful book. I know we've all seen the movies, but you should read the book if you haven't. It's a wonderful, arguably the first science fiction book. And if you read it, we all think that Frankenstein is a kind of cautionary tale against the Promethean hubris of bringing something to life. But really, what mattered was not just that the creature was alive, but that it was conscious, that it could feel misery and rejection and ostracism and pain. And that's what led to all the horror and the carnage. Then we have HAL, 2001, and my own favorite in this pantheon of science fiction films about conscious AI, which is Alex Garland's Ex Machina, now more than a decade old. So it's been there in the background, and we've always been fascinated by the prospect of creating artificial bodies and synthetic minds that not only think, but also feel. Now, there are other things floating in the background too, and I don't want to spend too long on them, but for instance, there's this idea out there, and quite probably more prevalent in the Bay Area than anywhere else, in California, that we might live forever by uploading our minds to some silicon cloud and existing forever in the pristine circuits of some future supercomputer in some transhumanist singularity rapture. And of course, for that to be possible, well, silicon just has to be up to the job of instantiating consciousness. Otherwise, we're loading ourselves into silicon oblivion, which is not really the idea there. So there's a lot of cultural background, I think, is encouraging us to think that this is possible, inevitable, or even here already. But I think our thinking about this is clouded by certain biases and confusions, which affect us all to some degree or other. And I want to start here by defining terms. Now, definitions of consciousness and of intelligence will always be controversial, and I'm not asking you to sign up to a final definition of either here, but I think there are intuitive definitions that can at least allow us to appreciate that these things are different conceptually. They don't always have to go together. Consciousness, intuitively, is what we lose when we fall into a dreamless sleep or go under general anesthesia, and it's what returns when we come round or wake up again. Now, when we're sleeping, we can dream at points, and dreaming is a conscious experience, so it's not all stages of sleep. Anesthesia is the better example. It's a more profound loss of consciousness. And when we are conscious, we're conscious of things. There's a world. We open our eyes, and a world appears. This is, I like to show this when giving talks in California, because this is a winery, but it is just outside my home city of Brighton in the UK, so we have these things here too. So there's an experience. We don't just process information inside our heads. We have visual experiences of colors, of shades, of shapes, of people, and of places. And then there's the experience of self, of being a self within this conscious scene. This background experience of being somebody is kind of almost always there, and it's the aspect of consciousness we might cling on to most closely. A bit more formal definition comes from the philosopher Thomas Nagel, who said, an organism has conscious mental states if, and only if, there's something it is like to be that organism. Now, people have argued endlessly about what this really means, and Thomas Nagel has written about it since, still does. But I think a simple way to think about it is that it's just a very minimal definition that for a conscious thing, it feels like something to be that thing. It feels like something to be me, to be you, to be a bat, as in Thomas Nagel's famous paper, which is where this comes from. What is it like to be a bat? I mean, you and me will not know what it's like for a bat to be a bat, but a bat has the experience of being a bat. For a bat, there is something it's like. And the reason I like this definition is because of what it doesn't say. It doesn't pre-theoretically conflate or confound consciousness with other things that might go together with it in some cases, but which need not go together with it in general. Intelligence, language, personal identity, these kinds of things. At its most basic, consciousness is any kind of experience whatsoever. Now, intelligence, and maybe it's a little easier to define, but there are still loads of definitions out there. You'll probably know more about this than me. Very broadly, again, is doing the right thing at the right time. Not the morally right thing necessarily, but just the behaviorally appropriate right thing, given your goals, the ability to achieve goals in a wide range of environments, to get a bit more specific from Shane Legg and Marcus Hutter. And then AGI, in these terms, this was this recent new definition by Yoshio Bengio and others, matching the cognitive versatility and proficiency of a well-educated adult. That's fine. There'll be others available as well. I mean, this is what you'll be discussing, what Gary was telling us, what, you know, in terms of what's missing in the great conversation just before this talk. But in short, these definitions are clearly about different things. Consciousness in general feels like something. Intelligence in general figures stuff out. And just because these two things go together in us humans doesn't mean they go together in general. The assumption they do is a reflection of our own psychology, not necessarily an insight into reality. And things get even more complicated when we bring language into the picture. Of course, most of the debate about consciousness in AI has focused on language models like Claude or GPT, perhaps Grok, I don't know. And language is particularly powerful at seducing our biases because we think language is what makes us special. We think language is the hallmark of maybe NGI, as Gary said, natural general intelligence, human general intelligence. Language sets us apart. Language is intimately associated with what makes us distinctively intelligent as human beings. Still, you know, this is still the case even given the efforts to decode animal communication, which are wonderful and interesting, but different. So language plays on our human exceptionalism. We like to think we're special. We bundle language and intelligence together. And so we think those things that make us special are also associated with the other things that are really important, like consciousness. And so we tend to kind of put all these things together. And what's more, I mean, it's no really surprise that language models are so effective at seducing our biases about consciousness, because of course they're trained on huge quantities of written text, much of which is about consciousness. They reflect back to us an image of ourselves, of the collective digitized past that we all share. So when we wonder about consciousness and the meaning of it all, they will do that too. Now, this is more like a very short sidebar and really a plea. Language models don't hallucinate. I mean, this has been so ingrained into our discourse now, but the reason I really push back against this term is because it implicitly conveys the idea that they experience. Because when we talk about hallucination in terms of other people, other human beings, we tend to mean that they're having unusual conscious experiences. They're hearing a voice that's not there. They're seeing a relative who is not, in fact, there. And so the language we use to describe really matters because we kind of scaffold the beliefs about what's going on, even if we don't mean to. Rather than hallucinate, I think if we're going to use a term from human psychology, we should, though I know it's too late, we should use the term confabulate. In psychology, this kind of means making stuff up without realizing you're doing it. And that's at least closer to what language models do when they make stuff up. So in short, for this section, here's a way to think about it. When we project consciousness into language models, at least part of what's going on is a form of what we might call pareidolia. This is a fancy Greek word for seeing patterns in things, like this face in a cloud, or even, I don't know if you can see this in the room. I can't really see the audience here, but this is Mother Teresa in a cinnamon bun. There she is. And, you know, there isn't Mother Teresa in the bun, but we project things into it on the basis of our prior beliefs, our prior expectations, whether it's for faces or for conscious minds. And it always strikes me as relevant that people don't in general worry whether other AI systems like, for instance, DeepMind's AlphaFold have conscious experiences. Now, under the hood, they're not that much different from Claude or GPT. They predict the structure of proteins rather than words and sentences. But under the hood, they're algorithms running on silicon and trained vast reservoirs of data. AlphaFold just doesn't pull our psychological strings in the same way. So we need to take into account the biases that we bring. But there's a more fundamental question in play here, which is the question of whether consciousness is computational. And the very idea of conscious AI trades on this assumption that, and it's, well, I think of it more as a myth rather than an assumption. And this is the myth that the brain is a computer, is literally a computer that just happens to be made of meat rather than metal. And in this myth, in this story, to be a bit kinder, consciousness is an algorithm, a bunch of computations which happen to be carried out in the wetware of the brain in ours, but which could equally be carried out in silicon, in AI. Maybe it's not the latest language model. Maybe it's not AlphaFold. Maybe it's not the J space in Claude. We'll get to that. But get the computations right and you will get consciousness, because computation is all that matters. That's the assumption. Here it is a little more formally. Computational functionalism is what the philosophers would call this. And it's really the following idea. Mental properties, including consciousness, are computational in nature. Computation is what they are made of. And the next idea is that, well, you know, if all mental properties are computational, well, that should be true for consciousness as well. Computation of the right kind is sufficient for consciousness. That's the strict assumption. Computation, we know, can be implemented in silicon. We have many examples of that. And therefore, real artificial consciousness is possible, at least in principle, even if it's not existing right now. That's the general argument for the plausibility of conscious AI. Now, computational functionalism might be true, but it's a really, really big assumption. I want to just give you a sense of why. I'm not going to necessarily convince you that it's wrong, but I think you should realize that it is an assumption and it does need to be better justified than it quite often is. To see why, first, it helps to remember that the computer started, at any rate, as one in a long line of technological metaphors for the brain. It was a system of plumbing. It was a telephone exchange. And now it's a computer. So there's this idea that we always reach for the dominant technology of the day as a metaphor to understand something that's always resisted our attempts to understand it. You know, the heart, pump, easy. Brain, not so easy. But there are reasons, and good reasons, why it's tempting to think it's more than just the latest in a sequence of technological metaphors. And this brings us back a little bit of history to the foundation of computer science. Alan Turing, his paper in 1950 was the Turing test, but I won't talk about the Turing test. His paper in 1936 is more relevant here. This was where he introduced the idea of an algorithm and of what became known as a universal Turing machine, an abstract machine that could implement any algorithm. And an algorithm here is any mapping from one discrete and enumerable set of numbers to another discrete and enumerable set of numbers in a sequence of steps. That's an algorithm. And Turing's brilliant insight was that, you know, this simple abstract machine of a tape and heads that could read and write and move could implement, in principle, any algorithm. This is enormously powerful. Of course, I don't need to tell you at this conference. Now, around the same time, McCulloch and Pitts described or proposed the first sort of artificial neural networks, or among the first. Very simple, kind of integrate and fire neurons. And they showed that networks of these neurons could implement logical operations like and, not, or, and things. And it was later shown, about 1950s, that networks of these neurons could implement any algorithm, could be Turing complete. And this is super powerful, right? This is powerful because it encourages us to see the brain through Turing glasses. On the one hand, we can kind of forget about all the biological, neurochemical complexity of the brain and think of it just in terms of these integrate and fire simple, abstract, almost cartoon neurons. And on the other hand, we get everything that Turing computation has to offer, which is a lot. So this is very convenient, and it really helps us think that, oh, the brain is a computer. It's not just a metaphor. And the neural networks that power today's AI are direct descendants of these simple systems. And so given how powerful these are, it's really not surprising that many people think that brains are nothing more than carbon-based versions of these neural network algorithms. But this is where the trouble starts. The brain is not just a computer, or at least it's not obviously only a computer. For one thing, Turing computation, while very powerful, is not everything. There are other kinds of computation, analog computation, neuromorphic computation, mortal computation, that are not captured by this Turing universe of mapping discrete numbers to other discrete numbers in a sequence of steps. There are other kinds of non-computational processes altogether, like things that happen inside brains that depend on particular kinds of material, neurotransmitter fluxes, neurotransmitter chemicals that flow throughout the brain, and so on. So to assume that everything that the brain does is a matter of Turing computation is to rule out a large space of possible things that complex systems do. I want to just make the point here that there's another perspective in philosophy of mind called functionalism, which is the idea that the functional organization of the brain is what matters for its properties, including consciousness. This is a relatively liberal position because functionalism in general includes all kinds of things, the internal causal structure, all the, the way it's wired up, all the causal properties that it might have. Turing computation is a subset of that. So we can buy into functionalism in general without having to buy into computational functionalism, and that's kind of important. So on the one hand, Turing computation is a small space of possible dynamics, and on the other hand, the more you look at real brains, the more you realize how impoverished that cartoon view of artificial neural networks really is. And I'll just give you one example of that. Like in a real brain, you don't have any kind of sharp separation between mindware and wetware as there is between hardware and software. And this is just like I could have chosen many images, but this is an image of just how complex 1 cubic millimeter of human cortical matter really is. There's no sharp divide between what the brain does and what the brain is. And this really, really matters because it is that sharp separation that was conceptually central to Turing's definition of computation. It's that sharp separation that licenses the idea that the computation itself is all that matters, which is the idea that is central to computational functionalism. If you can't disentangle what brains are from what they do, then you're on very, very shaky ground to assume that what they do is a matter of Turing computation alone, because Turing computation depends on the separating the implementation of it from the algorithm itself. Just to make the same point from a different direction, one argument sometimes you might hear about the plausibility of conscious AI is like, well, let's just replace biological neurons with silicon equivalents one by one. And, surely nothing changes after one, so why should anything change after 86 billion? Well, the problem with this thought experiment is a common problem with many thought experiments, is that you can imagine it conceptually, but the more you know about the brain, the less sense it makes. The only way to perfectly replace a biological neuron is with another biological neuron, and ideally the same one. It's a bit like, I can imagine a Boeing 787 flying backwards conceptually, but the more I know about aerodynamics, the more I know that's actually impossible given the laws of physics as we have them now. There are other reasons why the idea that all that brains do is a matter of Turing computation is just, it's not sustainable. One is that in algorithms, only sequence matters when it comes to time. Algorithms are just one damn state after another. It could be a microsecond or a million years between two states, and it's the same algorithm. But neurobiological processes and conscious experiences unfold necessarily in continuous time. We don't have the luxury to ignore continuous time. So there must be, from this view, it's a strong argument, I think, that whatever it is that brains do cannot be a matter of Turing computation alone. So to summarize this and then move on, endless more things could be said about this. But the case against computational functionalism goes a bit like this. There is this computational premise. The computational level is sufficient for explaining, indeed instantiating, properties of brains. whatever brains do, including, let's imagine, consciousness. So evidence substrate dependence, evidence that what things that the substrate properties of the brain matter for what it does, is evidence against this computational premise, evidence against the idea that the computation is all that matters. And so evidence against the computational premise is also evidence against computational functionalism, because if the computational level is not sufficient for explaining instantiating properties of brains, then there's no reason to assume it should be sufficient for instantiating consciousness. You need independent reasons to think that's the case, and there really aren't any. So this doesn't prove it's false, but it suggests that we should not assume it's true. We should not assume just because it's convenient to assume that computation is enough. We shouldn't. That's not a good enough reason. Okay. Just want to touch briefly on this very interesting new work from Anthropic about J spaces and global workspaces in Claude. This is interesting because I think it's an example of like, okay, you see some interesting functional architectures in Claude that resemble a theory of consciousness, in this case, global workspace theory. Now, there are many differences and so on, but one of the still unresolved things here is like, this is only evidence for consciousness in Claude if computational functionalism is true. It still relies on this idea that the computations themselves are enough. And the fact that we can see signatures of global workspaces in Claude doesn't speak to that question. So I put a couple of points here because I do think it's interesting. It certainly goes beyond our psychological biases of thinking, oh, it talks to us, therefore it's conscious. It's more interesting than that. It looks for computational signatures. It's very useful for interpretability and predict what it's going to do probably better by knowing what's going on in the J space. But it's less clear about the relevance for consciousness. There are many differences from global workspaces in neuroscience. If people are familiar with those, I don't have time to go through it. Also, global workspace theory, it's not a consensus theory, and it doesn't specify sufficient conditions. It doesn't tell you what's the minimal kind of architecture to count as a global workspace. So I don't think it's really that good evidence for consciousness. It's rather good evidence that systems that are solving similar kinds of cognitive problems can do it either with consciousness in humans and other animals or without in language models. And it still assumes computational functionalism. If you want to follow up on the Anthropic thing specifically, I wrote a piece about it in The Guardian the other day. Now, last thing I say about computation is to address another common response to this, which is, well, if the fine details of the brain matter for consciousness, then why don't we just simulate all those fine details? Why don't we just simulate every last detail about the brain in some massive supercomputer? Well, we know that if we simulate a weather system, we don't generate real wind. And again, it's not that a person within the simulation of a weather system would feel wet or would feel the wind, because for that to be true, it already has to be the case that computational functionalism is true. So for simulation to instantiate consciousness, it already has to be the case that computation is sufficient for consciousness. It doesn't matter how much detail you simulate the brain in. You can't, on that basis, conclude that computation is sufficient. It rather goes the other way around. If computation is sufficient for consciousness, then simulating every last detail of the brain should do it. But the irony here is that if the fine details really do matter, then it's less likely actually that simulating the brain will instantiate consciousness, because if the fine details matter, then it's unlikely that computation alone will be enough for the reasons I've already given. So if you think that a whole brain, massively detailed emulation of your brain is the way towards digital immortality, then I think there's a certain irony there, because if you think you need a sort of super detailed atom by atom simulation, it's actually less likely that will actually instantiate consciousness, because if you think those details matter, the implication is that whatever properties that brains have, they're not properties of computation itself. Okay. Now, I've got about 5, maybe 7 minutes more. Another important angle here is there are other games in town. Like often another sort of response is, well, of course the brain is just processing information. Of course consciousness is just computation. What else could it be? And I think this is there's a kind of lack of recognition here that there are many, many other games in town. There are many other theories about consciousness, possibilities about the necessary and sufficient conditions that are not matters of algorithm. And, you know, I'll just give you mention really. I don't have time to really defend it in any detail. But my favorite idea it's called biological naturalism. This goes back to John Searle in the 1980s. And this is the idea that properties of life, properties of living systems are necessary, but not necessarily sufficient, just necessary for consciousness. There we go. Biological properties are necessary, though not necessarily sufficient for consciousness. I just want to say a couple of things about this without having the time to defend them. This is not neo-vitalism. Not just saying there's something magic about life and we just say, hey, you know, life is magic and consciousness is magic, so they're the same thing. It's not that. It's saying that biological properties are necessary for what brains do, including consciousness. It's also not carbon chauvinism. It may be that the relevant biological properties are instantiable in alternative chemistries. We just don't know that yet. So it's not just like some retreat to like, hey, you know, we're special because we're biological and carbon-based. It's not that. It's rather a research program aimed at discovering which, if any, substrate properties matter for consciousness and cognition, and why. It's a case of taking seriously the idea that the brain might be more than just a meat-based sort of object to implement Turing computations. The short story for why I think this is actually has a positive story here as well comes from the idea that the brain is essentially a prediction machine that's always in the business of making and updating predictions about the causes of sensory inputs, and that perceptual content, conscious experiences arise out of this dance of prediction and prediction error, which we can model computationally, but it is not necessarily computational in the brain. This connects in very interesting ways, which I will skate over very blithely here, to things like the free energy principle, which is a kind of predictive processing that unfolds in how systems maintain themselves in states they expect to be in, how they basically stay alive. And it also connects to things that are really definitional of life, like autopoiesis and metabolism. So in short, if you follow this all the way through, and again, I really haven't had time to defend it, the idea here is that we perceive the world around us and ourselves within it with, through, and because of our living bodies. The longer story is in this book. So to summarize the case against conscious AI, evidence that the materiality of the brain matters for its function is evidence against the idea that digital computation is all that counts, which is evidence against computational functionalism. And for conscious AI in digital silicon systems to be as good as ruled out, it's enough for computational functionalism to be false. Biological naturalism might be true, but it doesn't need to be true. That's the argument. Now I'll finish with a few things to worry about. First thing to worry about is I might be wrong. You know, people argue about this. I'm still kind of in the minority. And if consciousness is a matter of computation, then indeed it might already be here or coming very soon. I think this is very vanishingly unlikely, but who knows, you know, I might be wrong. Even if I'm not wrong about that, technologies are changing. We have increasingly brain-like hardware systems now, which move the needle on the credence that AI might be conscious, not because it simulates the brain in more detail, but because it's more brain-like in terms of its physical structure. It's just becoming more brain-like. The question here is, how brain-like does AI have to be to make it more likely to be conscious? Is it just, spiking neurons, or is there something about the neurochemistry? I think there is, but it's an open question. We also have synthetic biology systems, organoids and assembloids made out of real neurons. Now, these don't seduce our psychological biases in the same way. They don't speak to us about consciousness. We don't have long philosophical discussions with an organoid, but they're made out of the same stuff. So for me, I'm much more worried about the accidental emergence of artificial consciousness in a cerebral organoid than I am in the next iteration of a language model. And there's plenty of other garbage happening in synthetic biology as well, which we should be vigilant about. Most importantly, no one should even be trying to create conscious AI. That's my kind of like political message. It's a terrible idea to even want to create conscious AI. I love this tweet, which is from a year or so ago now, I think. In my book, I invented the torment nexus, a cautionary tale, like all the sci-fi things I started with, and tech companies. At long last, we have created the torment nexus from the classic sci-fi novel, Don't Create the Torment Nexus. I think this sums up quite a lot of, it's a bit, it's a joke, of course. But it's true. It's really not something we want, conscious AI. And there are many reasons for this. Conscious AI could suffer in ways we might not even be able to recognize. We would have an imperative to give it some rights, which would make the problem of alignment even harder than it already is. So creating conscious AI is just I think, a really bad idea. I don't think there's any good reason to do it. But it's very unlikely. So we're fine, right? Well, not so fast, because even AI that seems conscious is very dangerous too. So other people have been making this point. Mustafa Suleiman makes this point, I think, very eloquently. And we're already here. This isn't a question of whether computation is sufficient for consciousness. This is a question of our own human psychology and what it takes for us to believe and feel that the systems we interact with have conscious minds. Why is this dangerous? Well, many reasons, but take AI welfare again. If it becomes very natural for society to think, or just to come to the consensus that AI is conscious, or that we should just give it the benefit of the doubt because we don't really know, but it feels like it, then it'll be very hard to resist the imperative to give AI systems rights. But we wouldn't need to if they're not actually conscious. And so we'd be hampering our ability to control and regulate AI systems for no good reason at all. I'm just remembering the recent thing with OpenAI's model Hugging Face the other day. These systems are already doing things that are pretty dangerous. And if we decide that we can't turn them off because we think they might be conscious, but they're not, then we're really scuppering our ability to navigate the challenges of AI in the future. There are plenty of things to worry about already with control and regulation without worrying that we hamstringing ourselves even further. That's one reason. Another reason, of course, is our own psychological vulnerability. There's stories every day about people who end up doing harm to themselves or to others after interactions with chatbots. I mean, some are good. Of course, there's a lot of positive stuff. I don't want you to get the impression I'm sort of down on it all. But there are problems when people fall into parasocial relationships with chatbots. And it's likely, I don't know if there's any specific data, but it's quite likely that these parasocial and problematic relationships are probably more likely if people really feel that the AI systems they're interacting with really feel for them. The movie Her is brilliant on this, of course. And finally, being smart won't save us. There's a phenomenon, and this is the Westworld in the background. I think it does a nice job of illustrating this. Even if we know or believe that AI is not conscious, we might not be able to resist feeling that it is. There are visual illusions like this Muller-Lyer illusion here. This is a cognitively impenetrable visual illusion. However many times you look at it, the lines look different lengths, even though you can measure them and you know they're the same length. It might be the same with conscious seeming AI. Even if we believe it's not conscious, we might not be able to resist feeling that it is. It's not enough just to put a disclaimer on. We need to design the impression of being conscious out of these systems somehow. Not easy, but that's what I think needs to be done. And finally, it's kind of dehumanizing when we see ourselves in our algorithms, when we project consciousness into our language models. The mirror tends to go both ways, and so see our algorithms in ourselves. We think of ourselves as nothing more than computers, as replaceable that way, as fungible. I mean, I think this is part of why we struggle with the idea of the social and economic consequences of AI, because we think we're easily replaceable by algorithms, because we think we are algorithms. But I think that does ourselves and living creatures in general a great disservice. So to summarize, real artificial consciousness is unlikely. There's a lot of cultural baggage encouraging us to think that it's happening. We have psychological biases, but brains are not just computers. Simulation is not the same as instantiation. And consciousness and life may be tied together. AI, of course, is much more feasible. It's already here in some degree, because AI is a matter of doing things, and algorithms can do things. Intelligence and consciousness are not the same thing. So I'll stop there. If you want to follow up, there's my book, Being You, which is available, I hope, everywhere. And the BBS paper, at least the target article, is already out. And there's an essay in Noema called The Mythology of Conscious AI. And at some point, have a look out for this documentary film called Conscious, which is coming, hopefully to the US quite soon. But I don't know exactly when yet. I'll put this back up. Thank you.
Yeah,
thanks a lot,
Anil. So this is Ben
Goertzel,
who's
who's the organizer of the AGI conference. And I love having a talk at the conference where I disagree with almost everything that was said. I mean, I don't want this to be an echo chamber. I mean, I want to get a diversity of perspectives on things. But I wanted to, by way of a follow-on question, just very briefly get your reaction, because I've been around this field a long time also, and I was never a fan of computational functionalism, nor am I particularly a fan of the idea that biological matter somehow has a unique connection to phenomenal experience. I've always been more panpsychist, I would say, just feeling consciousness is immanent in the universe, sort of like time in some senses, and then consciousness will manifest itself in different systems depending on various factors, but largely they're patterns of dynamical organization. And so I guess I'm not sure why you see it as computational functionalism versus biological naturalism. I mean, there's a lot of other ways of looking at consciousness, which may be more logically simple and which does leave room for computer systems to have some species of consciousness, biological species to have some species, like a quark gluon plasma could have another species of consciousness. So I mean, I haven't read your book, so maybe you deal with a wider variety of perspectives like that there, though.
Thanks, Ben. It's actually, there's a little in the book, but it's more in the BBS paper and all the commentaries. And I think, you know, what was interesting in the range of commentaries was it's actually a fun experience to have. I think initially it was like 200 people disagreeing with me in different ways, and then, you know, we whittle it down to 50 disagreements that kind of cover the basis. But so that view certainly it's one objection, and you know, there are many different metaphysics available. Panpsychism is one of them. Now, I put my cards on the table. I'm a sort of pragmatic materialist. I think consciousness is a property of matter organized in the right way. And you know, my job and my colleagues' job, who are similarly metaphysically inclined, is to figure out what that right way is. And if you favor, on the other hand, panpsychism, which is the view that consciousness is fundamental and ubiquitous, it's sort of a fundamental property like mass or energy or electrical charge, then of course, basically, consciousness could be much more widespread. It's a metaphysics of abundance. You know, I just don't find any convincing reason to think that panpsychism might be the case. It's often motivated by the suspicion that materialism is failed, which is just not. I don't think that's the case at all. And even if panpsychism is true, it doesn't really help us very much, because we still, I suppose, we still want to make distinctions between the kind of consciousness that might matter and the kind of consciousness that might not. And you know, we want to draw a distinction between things like conscious things and tables, which aren't conscious, even if they're made of tiny conscious electrons.
I would say it sweeps out of the way some confusion. It doesn't intrinsically solve anything. You still need to understand what kinds of consciousness are likely to emerge in what kinds of systems.
I think it introduces more confusion in my mind, because you then have this other problem of how you get from small conscious things like electrons or whatever, the smallest
Well, you don't
fundamental
have to,
unit is.
because electrons are also conscious.
Yeah, but no, the problem is you have to go from there to getting big conscious things like philosophers and neuroscientists and computers.
Yeah,
and,
you have to understand how the consciousness of
Yeah.
the parts relates to the
And that's-
consciousness of the whole, which there's
So
a
that's-
large literature on, of course.
Exactly. So that's a problem that's purely a problem that's sort of distinctive to panpsychism that I think, that metaphysics introduces. And at the same time, it doesn't actually give us anything, because it's fundamentally it's not
Well,
only
it just
this.
describes reality, which is an advantage. But
Okay. Anyway, so it is
a lot of
true that
perspectives.
it
yeah.
is true that if you have a different metaphysics, then it changes things, right? You if consciousness is more abundant, then indeed you can think it's present in different things in different ways. But I don't think it really helps with the question on the table about whether a given AI system is conscious in a way that we might think matters versus is not. But I grant you that different metaphysics make the overall change your level of credence in some general way.
Yeah, this could go on forever, as there's a consciousness workshop today where it is going on all day. But anyway, thanks a lot for contributing your view here. It was a very clearly stated and enjoyable presentation.
Thank you, and I appreciate you having someone who with like sort of the opposite views to AI being conscious in the room. So thanks for having me, and enjoy the day.
Thank you so much, Anil. Yes, I don't know if you could hear it over the Zoom, but a round of applause. Everybody's super appreciative.
Great. Well, thank you. The appreciation goes both ways. I'm very grateful for the chance to speak to you.
And this is such an important way to bring together both the technical and the philosophical and the real world implications of AGI that we're all here to look at today. So thank you, Anil. Thank you, everybody. We're actually fairly close to on time. Lunch is ready. It's in the back. There's box lunches back there. There's some meat-free options. There's some cheese-free options, mostly sandwiches. Please, one box. For those who have a meal card on campus, the meal center is also open. And we'll be back in our sessions in 30 minutes. Consciousness, again, will be up here up front. We'll have the active inference in the hallway behind, and Hyperon in the room that it was in as well. We'll see you in 30 minutes. All right, Hyperon Workshop. Alexei, if you're here, we're going to go ahead and kick off and get started. You should have the screen. Perfect. Let me spotlight you.
Okay, can you hear me now?
And I can't hear your audio. Are you unmuted?
No.
Oh my gosh, we had it working a minute ago. Oh, I see. I think my Bluetooth speaker just disconnected. Give me just a moment to hook it back up again.
Okay.
Who's up next, Taylor?
Alexei.
And then Greg after that?
Yeah. I don't know. I don't know. Ben,
Can I help you? What's happening?
it should be called Wonder Boom 2. And
I don't see it.
I don't see it at all. It's not my unit. Unfortunately. Okay, it's off. Now let me see if we turn it back on again. On. Something happens here. Just a minute, forget this. So. Try the other. Oh, we showed up.
Could be another code. Are you sure it's Wonder Boom?
It was like I connected to it. We played off. We played a video. It played sound. I just forgot it because I was like, maybe that would help me connect to it. That sounds good. Alexa, I apologize. We're going to try playing it on my speakers. Can you try speaking?
Yes, I can try speaking. Does it work?
It
is playing via my speakers, but it's not all that loud. Let me see if I can. But volume is max. We're still having audio problems. I apologize. We had it fixed. Not working. Can Alexa try speaking through my speakers, and we'll just test and see while we try and get the Bluetooth hooked up. So Alexa, if you can speak loudly.
How how much?
It's quiet. No, I'm sorry. It's too quiet. I'm sorry. Alexei, I apologize, but we are now have sound and are ready for you.
Is it working?
It's working on, let me put it to the Wonder Boom. All right, give me 1 second.
There is one change. Vitaly
Okay.
Khodorkovshev asked to switch places with me, so he will go now, and I will go after Nesta, possibly. At the
All
end of
right,
the
thank you so
section.
much, Alexei.
Okay.
So Vitaly Kudobashev will talk about Jetta, correct, Vitaly?
Yeah, right. Could you hear me?
Yes, we can.
Oh, amazing. Thank you. I will try to be as quick as I can. Give me a second to share my presentation. Could you see it?
Yes, we can.
Oh, amazing. So let's start. Probably everyone knows about Jetta. Jetta is kind of the compiler of meta language, meta programming language to JVM bytecode, directly to JVM bytecode. It's not a transpiler, it's a real compiler. So, and today I'm going to talk about some progress I got maybe last 3 or 4 months in compiling meta. Compiling meta is kind of the very complex thing, just because meta is more like kind of interpretable language. It can be transpiled to another languages, but if you want to compile it efficiently with all edge cases, so it's kind of the pretty hard to search problem. So, and today I'm going to talk about 2 things. The first thing is my performance tests I've done just because to compare Jetta with another implementations, well, like Peta, Seta, and MetaScript, I mean meta TypeScript implementation. So, and another thing I'd like to talk about today is where we are in terms of covering core Hyperon functionality. So my goal is to make Jetta as compatible with Hyperon experimental as I can. In the best case scenario, 100% compatible, and I'm quite close to that. So so there are 2 topics to cover today. So let's start. So I'd like to skip some slides, but I will show, but I don't want to comment them. It's quite easy to figure out what's going on here. So the most important thing today I'd like to point, it's I will try to use my own JIT, I mean just-in-time compiler in Jetta, just to provide the best possible performance in many edge cases where other implementations are not very good sometimes. But it depends. So I got kind of the regressions just because I try to implement as many features of original meta as I could. So how I'm going to measure that? Actually, I use kind of standard approach, wall clock, and I try to run the same programs many times and find kind of an average. So and I have 6 benchmarks. It's not really cherry pick. It's just edge cases I found quite suitable for me right now, just because these cases are covering all features I need to measure right now. So let's start. I know the first one is quite obvious. It's kind of dumb Fibonacci implementation. So it's just try to measure Jetta against not just Peta or Seta, it's against kind of the conventional programming languages like Java or Kotlin. So Meta circle interpreter is kind of the classical thing from SIG book. Is the same as simple differentiation. The interesting thing, the most interesting example probably was provided by Alexei Potapov. It's program synthesis. It's actually this particular example is heavily using just-in-time compiler. So backward chaining, I used a very simple one. Basically, it was one of the tests provided by Hyperon experiment. So let's see what we have. Actually, Jetta is quite good in the most cases, especially it's Jetta as good as Java or Kotlin almost. It's even much faster. Not much faster. It's as good as Meta TypeScript, just because, as far as I know, V8 engine also have all possible optimization about memorization, all this stuff. So it was also implemented. So the good thing about Jetta, actually, I can implement every optimization from any language. So for example, I can implement optimizations from Prolog, from Java, from Node.js if I want, just because I have full control on code generation process. So it's kind of the good thing. If you can see, I have a kind of the regress in civil differentiation just because I've just implemented type system. I mean, in the same way as it was done for Hyperon experimental. So many type tests, almost all of them actually right now work quite well. For example, generalized abstract data types and so on so far. So, and that's why I have a kind of the regress here. It was much faster, but I can optimize it after I finish with implementing all other functionality from standard implementation. So I got some issues with Meta TypeScript just because we can. It's not about Meta TypeScript at all. It's about Node.js. Sometimes we can control such things like stack size. It's quite difficult. For example, in Java, JVM, you can't control stack size, so I can actually run very deep recursive examples without any problems using Java. So it's not actually very interesting. We slide faster than even better here, and this is kind of the interesting thing. It's all about just-in-time compiler I've implemented for Jetta. So actually, it's true compiler. So all code we got from spaces during the execution can be truly compiled into bytecode, and after that it can be used in a proper way with all JVM features like C1 and C2 just-in-time compilers. So it actually worked quite well on actually hot paths. So it's quite good. So, but actually, my benchmark is not perfect, and as maybe I will improve it later. It's kind of work in progress, of course. So, and I also heavily use partial evaluation in most cases. Everywhere I can. For example, I'm trying to compile all things I can ahead of time. And I use dynamic compilation and dynamic calls only in the cases I basically don't have enough information during compilation process. So I think it's quite efficient way to deal with. So yeah, I don't want to spend your time. Just show you some slides. And backward chaining, actually, Seth is quite good, but I think I can be as good as Seth is here, but I didn't want to push myself too far here, just because it's for me it's more important to implement all all functionality from original meta implementation. So back with chaining, actually, we're quite good here. I basically borrowed some ideas from Seth, some ideas from Prolog to implement it efficiently. So, but I think it's not super optimized right now, but it works quite well. So it would be great if someone can provide for me better backward chain examples to test Jet against with. So actually, I've implemented some type issues right now. So I will show you where we are in terms of correctness and compatibility with Hyperon experimental. So as I said, my goal is to be 100% compatible. So right now I'm quite close. I have only 7 tests left from standard Hyperon testing suite. Sorry. So it's and I think that it's almost all. So there are a lot of completely new features, and we're quite weird sometimes in Jet. Now, for example, I have a lot of cross-cutting changes through my compiler, so I need to do some refactoring just to improve the situation. But I think it's a work in progress. But I'm quite close, I believe. So that's next. So I'm going to achieve full Hyperon experimental compatibility maybe in next month or so. And after that, I'm going to it's all these benchmarks is all about single thread computation. So it's not parallel at all. So I'm going to implement parallel execution. It's quite useful if you want to, for example, run non-deterministic programs and I don't know, probabilistic programming or something like that. So, and I'm going to add full support of external Java and Kotlin libraries. So that's it from my side, and I promise to be as quick as I can. So, any questions? Maybe Alexei, can you ask me something? Potapov?
All right. Thank you very much, Vitaly. In the interest of time, I think we better go straight into Alexei.
Well, I believe it's better to keep the structure of the session and proceed to Greg.
Yeah,
I mean, we don't have to go to you next, Alexei, if you don't want, but.
Well, I can. It's not a problem. Should I go next?
Yes.
Okay.
But you have to speak up quite like, give me a second.
Yeah. Well, I mean, we'll. I think we'll go Alexei so that he can get out of here.
Yeah.
Yeah.
Well, we got to crank Alexei up to the loudest possible.
Yeah.
An active nucleus, use that into field loss.
I think it is max right now.
Okay, just yell as loud as you can.
Gotta yell. All right, we're ready for you, Alexei. Just loudly.
Okay. Yeah, then I'm sorry. I wanted to switch places with Vitaly, but it appears that we just went first. Okay, I will also try to be brief. My presentation is on the embodied AGI direction. So last year on the AGI conference, we had a talk on the limitations of LLMs and the necessity to work with world modeling in conjunction with representations for semantic and episodic memory because these things are connected and LLMs are not doing internal representations in terms of which we could have a native memory for them, and instead we are using external tooling like RAGs and so on. And we believe that this research is most suitable setup for this research is embodied AGI. I had a lot of motivational components here, but I will not repeat this motivational part. And luckily, Gary Marcus has said a lot of world modeling and so on. So we started working on the embodied AGI direction and world modeling in particular as a part of our AGI strategy. And we started with Minecraft experiments. So let me just share. Okay. So we started experimenting with embodied agents in Minecraft, which can predict environment state changes in response to their actions, and which can condition their policy on the explicit goals and sub-goals, which could be chosen by a symbolic subsystem. We achieved some positive results. We actually also tried vision language action models in different setups, both for Minecraft and for Mind Children robots. But as we expected, VLAs didn't generalize well, so they are similar to next token prediction, and they just need to cover the whole space of the system to work quite well. So we were more interested in constructing, developing such models which can maintain a internal representation of the situation and predict it and use it for action selection and planning. However, the vision processing backbone we used was relatively weak, and such sort of approaches as JEPA didn't fit in our framework because JEPA supposes that observations should not be reconstructed. So it's a mistake to try to reconstruct observations, and this basically doesn't correspond to our intuition. That's why we decided to analyze if we can outperform JEPA without abandoning full generative models. We started with a simple synthetic data set like noise time series, which had a known internal dynamical model which should be reconstructed by a machine learning model. And what we found out that JEPA worked quite well in these settings, while autoencoders fail miserably, and it was quite interesting. So we digged deeper and figured out that the problem wasn't that autoencoders independent component analysis and other similar generative models cannot reconstruct the true internal dynamics of the system, but they simply cannot tell apart which variables are noise variables and which are signal variables. And if we restricted the latent space of the model, it shows just more salient variables, and when the level of noise went higher than signals, then just noise variables were selected. So the result was quite trivial, although not quite obvious from the beginning. But on the base of this result, we invented gated predictive autoencoders which basically work as normal autoencoders with a JEPA-like predictive component in the loss function, and they use gates to separate variables which can be predicted from variables which cannot be predicted but should be used to produce a fair reconstruction and to estimate a fair loss in terms of MDL or full Bayesian approach or whatever sound approach you take. So basically we outperformed JEPA. We achieved almost perfect results on this time series, while JEPA worked out of the box but didn't achieve perfect results. They were just good. We went a little bit far and tried to apply this approach to MNIST classification data set. These results were not published because well, it's just a sanity check, and our gated predictive autoencoders with the same architecture outperformed vanilla JEPA. So it's an approach which could be used to produce some state-of-the-art models, but that's what we are actually trying to do right now. We are trying to scale up our approach towards sort of world modeling to achieve this state-of-the-art results on interesting data sets. But as Gary Marcus pointed out, this is actually a very primitive way of thinking about world models, and for us this was a first step. We just wanted to make things right, to flesh out the basic building blocks to be sure that everything is working well. And of course we discussed and wanted to proceed to much more interesting stuff like symbol formation, and I believe that it's not only about LLMs that there is a problem with world modeling, representation learning, and so on, but actually about symbolic systems as well. So the problem is not about just a scalable infrastructure for Hyperon. The question is where are we getting the data or knowledge from how can we get a novel knowledge about the real world. It's not just a test case or application for Hyperon. It's a very deep fundamental problem. It's not about just connecting any vision backbone to Hyperon to get some predefined symbols into it. It's exactly about constructing a neural symbolic architecture in a right way, which can get novel information directly from the world. Of course, we can use something like semantic parsing to populate atom space with knowledge graphs as an intermediate step. But if we are extracting knowledge from LLMs, we face the same problem as LLMs are facing. Where do we get novel knowledge, how we solve symbol grounding problem and so on. So we wanted to approach this problem in a very systematic way, but of course dealing with robotics with embodied agents is slower and requires a lot of computational resources and so on, and importantly data. So the things were moving not extremely fast, and meanwhile the LLM agents emerged as a very interesting and promising concurrent approach. So we couldn't avoid paying attention to it, and while we are still working on the low-level perception problems as a gate towards solving the symbol formation problem in neural symbolic architectures such as Hyperon, we also started considering another direction. So current systems, current coding agents like Codex, they can actually solve AGI Arc3 challenge nearly completely, and partly maybe with novel models there is indeed a leakage of information from the public data sets of AGI Research Challenge to the weights of the models, but actually they could do this with all the models which shouldn't really shouldn't really contain spoilers about AGI-3. So Sergey Rodionov will have a talk on using external computational world models with LLMs to solve AGI-3 during this conference, and observing successes of coding agents and other types of agents with external world modeling capabilities, we decided to develop a benchmark framework to reveal the limitations of LLMs, even if they are wrapped into the agents which are using external artifacts to do this sort of world modeling. And that's the problem with LLMs, that you cannot say that they cannot do something in principle, because they are using different workarounds via prompts with external artifacts and so on. We just believe that this is far from the most efficient way to do things. So we developed the following benchmark. It's basically about mazes with some key elements like treasure and key. And this is a starting position, which is used here as agent location. So we can take a key first, and then we can take a treasure and move outside the labyrinth. So it's a tutorial. That's why the labyrinth is shown. But the interesting thing is that there can be different kinds of elements in this maze which make the dynamics and movements much more complex. For example, there can be a number of cycles of pits, and you need actually to think how to move in order to get in the necessary location. And this actually requires some planning, but the most there can be rivers which also move you to a certain location, and when you like the current swept you 2 tiles away. So this mechanics of rivers, and when they are combined with pits, it becomes interesting. So how we can reach this exit? We need to go first to this pit, go down from this pit, and go right from here to get here, and only after this you can move out from the maze, but it will not allow you to do it right now because I don't have a treasure collected. And the things get interesting when the maze is hidden, and you cannot just understand the game mechanics and precisely predict what is happening. And this is how we are different from AGI Arc3. And it's quite an interesting situation because the agent or human player needs to solve a quite non-trivial localization and mapping problem. And you don't know where you are, you only receive textual messages. So we tried we tried to run vanilla LLMs on these mazes with the hidden mazes, and achieved quite bad results for them. For example, lightweight LLMs like Gemini 3.1 Flashlight achieves just 33% success rate and 79% rate if we allow, I didn't say there is a step budget, and 43% is the result for a step budget which is more than enough for a human, and 79% is a budget with twice number of steps. So it's a very, very soft restriction on the number of steps. Humans have 100% for all these numbers, and these are very, very basic mazes. It's training mazes for humans. These are not real mazes. And as you can see, all these models achieve nearly zero success rate. Larger models are a little bit better. They can achieve like 30 or 40%. And we tried not only vanilla LLMs, but also a sort of world modeling LLMs in a simple sense, in which they perform or realize their world modeling capabilities only via prompts instead of coding something. Sergey's model, Sergey's agent achieved quite good results on the training set, so nearly 100% for all of them. So external computational world modeling for LLMs somehow works here, but I will repeat, it's these are the most simplest mazes, and we are going to proceed to more difficult mazes later. But the next interesting thing that this framework is extensible, and there are different extensions which make things more interesting and more challenging, and there is a hidden set. No one actually has yet passed perfectly the training setup. So, but in any case, the hidden set is necessary to avoid hacking a solution which will work just for this set of rules. So the rule induction, similar to the AGI archery challenge, can be also quite important. But what was missing in AGI Arctic 3 is that there was no need to construct a representation of the world state over which the dynamics or physical laws should be invented or induced. So here you both need to reconstruct the state of the environment and possibly the rules how these states are to turn to one into another. But that's not all the story. Actually, okay, I will skip some parts because we are already quite late. It's quite interesting to see how the world modeling agents are thinking in this case. As I said, personally, I tried only textual world modeling, which quite weak, but fair in terms of LLM's internal capabilities. So it's interesting that vanilla LLMs, which are not allowed to construct some additional artifacts and just should figure out the next move in next token prediction style, they can do something, but as you saw, not too much. And if we allow LLMs to construct some plans, some world model representation, they are doing better, but still, if we see what they are doing, it's not any kind of two-dimensional representation. These are also words with some coordinates, but it's how LLMs avoid the problem of representing data structures which should be processed by computational world models. They are doing everything through text, and it's kind of possible for them, but highly inefficient. If we want an agent to reconstruct a representation of the observable system, they should use something more complex than something like this. It should be some two-dimensional or three-dimensional maps, arrays, graphs, etc. So when the agent is not creating such representations, it will not be able to solve such kinds of problems. And LLMs can create external artifacts like programs which can be run and which can produce the necessary results. But the problem is that LLMs are not controlling these programs. They are not performing them. They just produce these programs as black boxes for themselves. So the LLM's reasoning process, if you wish, it is disconnected from these external world models which they create, and that's the problem. So we also consider it the following use of this framework, because it's not a one benchmark, it's a framework which can be quite fruitful for different types of experiments. And one thing which we recently tried to do is to train a transformer-like architecture from scratch, just to predict outcomes of actions based in the next token prediction style, based on ground truth information, without map reconstruction, without planning and so on. Just take a map, take an action, and predict the pose, which should be which is the result of this action from this map. And I will not go into detail. It's quite a preliminary result, and we don't have time. But what's interesting is that transformers can do this in principle, but in our experiments, they have nearly zero transfer capabilities to transfer results from one cells to another. So they simply memorize stuff. If they didn't observe transitions from one cell to another when there is a wall or there is no a wall, they will be just mistaken. So for small 3x3 mazes, they can achieve 100% accuracy based on a quite like 100 runs of a random walk connected. But for larger labyrinths, larger mazes, they need more and more examples, although the rules are exactly the same. And if we think about it, we will really can ask ourselves where in LLMs they can represent a two-dimensional map, and how they can transfer results from one positions to another. And it seems that they cannot do this. They don't have two-dimensional positional embeddings for this and so on. And that's why they do something like this. So if it's not just a plain transformer which should directly predict the position, but if it's a more complex model which can output some intermediate results and consider these results to perform predictions, then it will just output coordinates and so on, and then it will perform further generative process to produce next sort of reasoning results, and then it might be able to come to right conclusions without having this two-dimensional model internally. But my point is that transformers don't do this internally, and doing this through external text generation prompts, external artifacts, it's just highly inefficient. So that's why it's quite interesting to study such simple mazes, because they prove themselves to be very complex for LLMs, especially when we don't provide full information, when there is some uncertainty and so on. And of course, there is still a large gap between such mazes and agents embodied in three-dimensional worlds, but I hope that the common theme of this research is quite clear. It's about constructing representations of the environment over which we can plan, reason, predict next states of the environment in a more native way, rather than producing it textually. Thank you for attention.
Thank you very much, Alexei. You just got a big round of applause. I think, again, we need to probably move forward with Greg's demo. So I apologize, we won't have time for questions. But thank you, Alexei. Thank you, Vitaly, for being here, being online, and waiting patiently with us. And Dylan as well. So Dylan, you're up next. Or Greg, I guess, first.
No, we're gonna lead off running code. We'll go back up a little bit about that code meeting one drop.
Okay. Just a moment, and I will get the. Are you sharing a presentation in Zoom? Great. No, I wouldn't do that. Who did I get?
No, but it's again, it's close. After that's the thing, don't get that.
Okay. So Dylan, I think you're up.
Okay. All right, let me turn that down. Can you hear me okay? Good. Okay. So we'll go ahead and share my screen. Is everybody able to see my screen? Good. Okay.
Yes.
All right. So today I'm going to talk about some exciting changes that are coming to MetaIL. So we're in the process of implementing the next iteration of Goertzel, which we've dubbed MetaIL, or for version number it'll be Goertzel 1.4. And what I'm going to demonstrate today is going to be how you will be able to embed what we call foreign language terms into a Goertzel application. So you'll be able to execute, for instance, or directly embed the meta applications into Goertzel and evaluate them and interact with them from Goertzel processes. So to begin with, this is just a simple language specification for lambda calculus. You have, just as far as types go, just simple term. Then you have lambda expressions and applications that evaluate the lambda expressions. Then for the rewrite rules, which this is the part where once we get to meta, this will be expanded quite a bit. So you have beta reduction left left application congruence, right application congruence, lambda congruence. And so what can we do with this specification? Well, if we go to this simple rolling application, here I'm evaluating 4 foreign language terms in lambda calculus, and then appending their or sending their results on a queue, global queue in this case, that's been dubbed just results. So each of these will be evaluated per the new look ahead semantics, which you'll notice right here on the end, the square brackets with the star on the inside means run to completion. And the results are appended to the queue. Then I'll do a persistent read or receive off the queue, print the results, and then I'll show you some more interesting things with some semantic predicates and some of the things that you will be able to do with semantic predicates. So if we go ahead and evaluate this, give it just a moment. So it's running all the terms to completion. All right, here are the outputs. All right, so the first one, this one here, is church numeral 6. Then you have this one evaluates the church numeral 5. The third term evaluates the church Boolean false, and then the fourth one evaluates the church Boolean true. So that's fun and all. But then it gets
Dylan, can you increase the font size?
And you begin mixing in some semantic predicates. So here,
Dylan,
the where clause.
Dylan,
And the where
Dylan,
clause
can you hear me?
says where the result here is not, in this case, the church Boolean false, and where it's not the church Boolean true. So we evaluate this one. Now you get your the two church numerals, sans the results that evaluate church Booleans false and true. And then, if you want to, just as a final example, before I turn things over to Greg.
Dylan, can you hear me?
If you wanted to just an inclusion filter rather than the exclusion filter, just to demonstrate that it's working with this one as well. So this one is saying, give me all the results, where in this case, the result is the church numeral or the church Boolean false. So that's what you get here. So the church Boolean false is represented by lambda lambda 0. True will be lambda lambda 1, right? So that's what we have here. This is the encoding. And so coming up very soon, we'll have full support for the behavioral structural semantic predicates and all kinds of cool stuff that you'll be able to embed custom language specifications directly into your online application, and be able to interact with them through these foreign language terms and semantic predicates. And that's all I have for the time being. I'll turn it over to you, Greg.
Yeah, thank you very much, Dylan. Not sure if you can hear, but thank you very much. So Greg will take from here.
Greg just joined the room, so I don't think he heard you. Greg, if you're with us, I think there was a little timing there. I think Haley introduced you right before you joined the room, but the floor is yours, I believe.
He's here live.
Perfect. That explains.
Thank you very much, Peter.
Go. Can you hear me?
Woohoo!
That's right. Need a little bit of dubstep there. Okay. So, what was Dylan showing you?
So he was showing you a significantly upgraded meta. So most programming languages have decompose into two sub-languages, right? So you have a data definition language. So like think about Java, where you have all your types, or Scala, where you have all your types, and Haskell, where you have all your types. Idris, I know there's some Idris programmers in the room, right? So the user, the mechanism by which you can define user level types is a data definition language, right? And then you got to be able to do something with your data, right? So you need to be able to wander over the data. And most programming languages, the control flow structure that they offer there is sequential loops, sequential recursion, and conditionals, right? And then they bolt concurrency on the side, right? So you have like some thread library which allows you to re-enter code that is running those sequential loops. So what we have proposed, and this is in keeping with analysis that I've done for decades now, but what we're starting to see when you see things like Omega Claw is that one should have concurrent control flow as the basic structure, right? That you have many agents and they want to talk to each other. And now the question is, what are they going to talk to each other with, right? Right, so the basic control flow structure is, just like with LLMs, right? It's ask and tell, right? So what he was showing you there with the 4 comprehensions, that was the ask part of the control flow, right? And the message sends, the channel bang, that is the tell part of the interface, right? And what that does is that generalizes Meta's idea of the question mark is Meta's query, and the bang is Meta's assertion. And what we said is that should be relative to a specific atom space, right? So you ask at a given atom space for something that matches a particular pattern, right? And you also assert a fact, you into a particular atom space. So Meta-IL allows you to talk across atom spaces and to do that with many agents that are all communicating at once. And so what that does is it unifies some key ideas. So first of all, the notion of an atom space is now is unified with the notion of a channel. So I listen on a channel and I tell to a channel, right? So atom spaces and channels are now the same thing. Okay, so that's kind of useful, but it turns out that also lines up with the best security formalisms we know. So inside Google, inside Meta, inside all of the major corporations, they have standardized on something called object capabilities, right? So you can think of an object capability as like a hotel key or a valet key, right? If I have a hotel, so when I walk up to the front desk and they give me a key, that's my access to the room, right? And they can revoke my access by invalidating the key, right? So all of the patterns that you can think through just intuitively with hotel keys, those are sort of the natural ideas of object capabilities. So what do? We unified 3 things with one fell swoop. We said, hey, atom spaces should be channels, and channels give you a notion of object capability. And he was just demonstrating that. Now, the other thing that in particular, he was showing you multiple different agents. So like the simplest possible agent is just telling something. The other simplest possible agent is listening for something or querying for something, right? So he was showing you already, just in these little examples, multiple agents interacting and coordinating at an atom space, aka a channel. But he did something else, which is really important, which is that he was describing these agents being able to define on the fly the language they're going to talk to each other with. So instead of, like right now, what agents do is they're speaking in some tokenized version of a natural language. But we know that when agents are left to themselves, they drop into a pigeon, right? And we're giving them the tools to be able to construct those pigeons on the fly, right? So the language definition, he was just showing you the usual suspects. You can do it with Lambda, you can do it with Rho, but inside Meta-IL, you can define a language, right? And then you can insist that two channels only carry well-formed tokens from that language, right? And you can check that statically. So if you declare that when we're talking over this particular channel, we're only sending terms from the lambda calculus, or we're only sending terms from the rho calculus, or we're only sending terms that are a combination of lambda and rho in the ambient calculus, right? You can check that at compile time. So that's another kind of security property. So and then there's a third kind of security property that he was starting to show off. Well, we just have the dynamic version of this. So what is the dynamic version? So it turns out, let me just draw on the whiteboard. So when Dylan was showing this part, so I have some pattern here, right? And I'm checking that pattern from some atom space, right? Which we have unified with the notion of channel, right? Then he did something, then he put right after this a where clause. There's a condition, and then there's the rest of the program. So this where clause, we can now express in it a wide variety of conditions, not just your usual Boolean conditions, right? What we can check since what's coming over here may be a term in a programming language, it's something that can wiggle, right? So what do I mean by that? So if I send you the application of plus to 1 and 2, that's something that could evaluate to 3, right? So we can check different speculative evaluations in these conditions. So we can get behavioral conditions. We can also check structural features of the things that we're providing. So in the case of a lambda term, I can check to see, is this an abstraction? Is this an application? Right? So these are conditions that we're checking. Later, and what we're doing now is we're doing this on the fly. We're doing this dynamically. Later, we can move those, once we've got that all sorted out, right? We're making sure it works at production with scale. We move this out to compile time. So you can declare these kinds of conditions that your whole program satisfies these kinds of behavioral and structural conditions. So that's another layer of security that you do not find in the industry currently, right? So that was another thing that we're setting Meta-IL up to do. Now, let's see. Anything I did want to mention, by the way, that this is a natural generalization of something that every programmer today does. So they don't necessarily write for. What do they write? They write select what? What are we selecting? We're selecting things that match this pattern. And where do we select them from? Well, we select them from a channel, which is now the item level. So instead of tables, we can go down to the granularity of item level stuff with Meta-IL. We can do item level locking, as an example, in a safe concurrent setting. So we select pattern from channel where condition. And then what's different about this from this is that we can say, now what are we going to do with all those results? So there's a do, and then the rest of the program. So every SQL programmer, every database programmer understands this pattern, right? So this is not strange, and yet what we've shown is how this paradigm matches with a multi-agent paradigm where the agents are doing ask and tell interfaces. Is this making sense to folks? Right. So now what you saw Dylan providing is exactly that. Now, how does that line up with Meta-IL? Again, what we've said is that, or how does that line up with Meta? Right. So.
I stopped your screen share. You'll have to share.
No, it's okay. I'm just gonna. I can do this on the fly. I don't need any slides. So Meta gives you rewrites and types, right? So those rewrites are the rewrites that you saw in the language spec, right? So remember where he had in his language spec he had a grammar, he had some equations, and he had some rewrites. So the rewrites for Meta are the rewrites that we find in our language spec, right? And the equations are nowhere to be found in Meta, but they have to be treated specially. Why? Because they can go in either direction. And if you treat them naively, you get into infinite loops and very bad performance and all kinds of things. So they have to be treated specially. And then Meta's types are the grammar that we put at the beginning of the spec. So Meta just completely embeds in a tiny fragment of Meta-IL. But now let's look at it the other way around, right? So the grammar part of the language def gives you all algebraic data types. So there you go, there's Haskell. Algebraic data types. Okay, but Haskell doesn't give you equations. When we add equations, what do we get? We get all of universal algebra, all finitely presentable universal algebra, right? So now you can do, like, oh, I know what a monoid is. Yeah, but when you write down your monoid, do you actually check the equations? So when you write down your notion of monoid or group or ring in Meta-IL, it's the actual thing. It's the actual mathematical object. And then what's new about computation from mainstream classical mathematics is this introduction of a packaging behavior with your data type. So if you're a practicing mathematician, you know that when you do linear algebra, vectors just sit there. Vector spaces just sit there. Where's the dynamics? The dynamics are in the transforms between vector spaces, including, automorphisms, right? So, but computation said something different, right? It says, no, we're not packaging the dynamics on the morphisms between objects. Dynamics are a part of the object. So when you think about lambda calculus is very different than mainstream mathematics because it packages the rewrites with the rest of the structure. So that has very important implications for when we think about models of computation and what that means with respect to world models. So I want to make a plug for a talk I'll be giving later this week about from causal models to world models, and just leave you with this one idea that the language specs inside Meta-IL are ways of writing down in a highly compressed form a causal model. It's not yet a world model, and you have to come to my talk to get the rest of it. So I'll leave you with that. Thank you so much.
Thank you very much, Greg. And so moving on next, we have Ben to talk about supercompilation and SETA. Let me get a laptop up to you.
Yes.
I'm just going to give a very brief summary.
You want to bring the podium over here? It's
I don't need to show anything. I just
No.
need to be on.
Yeah.
Bring the podium over.
the mic.
Micro, it's just a laptop microphone.
Yeah.
Okay. Yeah, so I'll keep this brief as we're behind schedule, and I'm speaking later on Omega Hive, which is less technical and is an easier thing to convey in a group setting like this. So I want to briefly touch on some work my son Zarathustra has done, although he found the AGI conference conflicted with the Ozora Psytrance Music Festival this week. So we see he's made the rational prioritization and left me to explain SETA. So I'm going to talk a little bit about SETA while he's dancing at Ozora, and a little bit about super compilation. So SETA is yet another reasonably efficient meta compiler. And as I said this morning, we've gone from spending a couple of years saying we can progress as soon as we have a scalable meta compiler to having a shitload of scalable meta compilers with different strengths and weaknesses. And this is a very nice problem to have. And now we're waiting to get the commensurate shitload of scalable PLN control mechanisms, in which case we'll take the next step forward. Now, SETA is different in a couple ways, and I'm not going to go into all the details, although I did spend a little time reviewing them on the flight here, because it wasn't really my own work, but it was entirely vibe coded, and it is a fully functional C compiler for Meta with no human written code in it, right? And I mean, that beauty of this as an application, as Zara and I discussed before we started, is, I mean, we have the data and the metrics, right? Like you have meta code, and because we have PETA and Hyperon experimental, like we have meta code and we know what it's supposed to do, right? So then you have a very nice test suite to try to have a whole bunch of Claude Code and Codex agents create a compiler. Now, Zar's methodology was a little different because he's been doing automated theorem proving work. So he has the agents use Lean 4 based formalizations as they go along. So it's not like you have one big formal proof of correctness. We have a lot of correctness proofs of all the different pieces of SETA that are constructed as the coding agents go about building. So it's an interesting example of vibe coded software development leveraging formal theorem proving as part of the development process. And I mean, I think creating a compiler is the right place to do this. Like it's harder to do for like a heuristic AI method because you don't have such a clear definition of what's right versus wrong, and what you're trying to prove things about is a bit messier. Whereas in this case, it's all very clear. And so as an experiment in methodology, it worked quite nicely, right? Like it seems to work. It took a while. And interestingly, the weird aspects with the variable bindings that Lean 4 kept choking on were the same things that Greg and Patrick and Alexa kept arguing about in Meta. Like the LLM and Lean hit on the same annoying properties of the Meta spec and kept bitching at Zara about them, which was all interesting to see. Now, the current version of SETA, it's pretty much the first one that passed all the tests, so it's very far from the optimal version of SETA. I mean, just as Jetta and PETA are not or Hyperon experimental are not the optimal version of what they are. A difference, of course, is with this methodology, SETA will keep getting better just as long as the agents keep crunching on it. It doesn't need a human to keep crunching on it to make it get better and better. And as we saw from some of Vitaly Kudybashev's results and from other tests that Czar has run. At the moment, for some classes of meta programs, SETA works faster than PETA or JETA, or for others not, and that's feedback to be fed in. Initially, it stuck closer to Hyperon experimental semantics. One of Czar's motivations is to deprologize things and like get away from having implicit prologue semantics. But it doesn't make much difference for most things that you're doing. Now, let me say something about the internal structure of SETA, because that's why it interested me for super compilation. The way the LLMs ended up designing it was a little different than the internals of the other meta compilers. And it's a way that probably seems more natural if you're a coding agent than if you're a human, right? So, because it's tedious, but the AI doesn't mind, right? So it's not what you would call elegant, but elegance and C don't match anyway, right? So it takes the meta code, it profiles each bit of the code, and then based on the profile of each bit of the code, it chooses a different intermediate representation to map it into, and then it runs it a different way. So like if it's like forward saturation based, it will map it into MM2 and then run it against Mork. If it seems to be heavily backward chaining-ish, it has some Warren-like abstract machine that it does to run that. For some things, it just does it straight in C. Now, one of the next things to come will be if you give it a bunch of PLN, it'll just put it into a factor graph on Mork. I think it doesn't do that yet. But so it's kind of hacky, but on the other hand, it's true, like meta optimization isn't just one thing, right? Like different bits of meta code will be optimally optimized in different ways. And if you're a coding agent, that's not really tedious to do, right? It's fine. You can just spawn some sub agents and say, okay, this code is profiled this way, do this. This code is profiled that way, do that. Now, when I thought about what you want for super compiling meta, it seems like it's pretty much exactly that architecture. Like not because it's C, although C is probably very good if you're super compiling, right? I mean, and I would note, while formal verification of C in general is going to be very, very hard because you can do pointer push and all sorts of weird stuff. If your code is developed by a coding agent using Lean4 in the development process, what you are coming up with is formal verification using C in a limited way that the AI made up as it went along, right? And then so I mean it can verify its own use of pointers that it came up with because it came up with them using the verifier in the process, even if verifying arbitrary C involving pointer manipulations is intractable. And that is a different way than I was thinking about formal verification before, because I was always thinking about it like people are making C and you're trying to verify it. I wasn't thinking about the verifiers helping you write the code and then verifying that code that it helped wrote, right? Which is interesting. And that bit was Czar's conceptual idea. It wasn't the AI's conceptual idea, but the AI has made it work interestingly. Now, the notion of super compilation is in essence in the crudest way, source to source code rewriting. In the simplest case, it's exact super compilation. So you're not changing the input output behavior of the code except for the time. So and perhaps the memory being used and stuff, right? So it's producing the same outputs given the same inputs, but it may be much, much faster. And I worked with this 25 years ago. We had a Java supercompiler that could speed up mathematical Java code by a factor of 50 or something by source-to-source rewriting. That was done by Andrei and Arkady Klimov, two Russian guys who were students of my friend Valentin Turchin, who was the founder of Russian AI, who passed away some time ago. The Klimovs are still around in Moscow doing super compilation. But we made a Java supercompiler, the original supercompilers were in a Russian language called Rifal, which was like the Lisp of Russia back in the 60s and early 70s, but prettier with fewer parentheses, right? But so Meta is far more so than Java and more like Rifal. Like Meta is tailor-made for supercompilation, right? I mean, it's rewriting. What a supercompiler does is it takes the code and it progressively rewrites it and rewrites it, but it typically will expand it into a big ugly code with a lot of special cases and then adaptively prune out the excessive expansion. Now, what we found in the Java supercompiler was it worked great unless your slowdowns were due to garbage collection or multi-threading, which unfortunately was almost everything the slowdowns were really due to. But if you were doing mathematics code or certain kinds of data structure manipulation, you could speed things up tremendously. Now, in Meta, if you do it right, things are all out in the open there, and you can kind of supercompile everything, which can be very, very nice. And I thought about doing this for a while, didn't get around to it. It seemed an ideal case for vibe coding also. And I haven't done it yet. It's a project I'll undertake in the next month or two, because I mean, there again, you have, it's supposed to make all this code run the same way. It's just got to be faster, right? So the metric to give the coding agents is extremely obvious there, as opposed to AI stuff. But when you dig into it a little bit, you can see the architecture of SETA is ideal for this, because what you want the supercompiler to do is exactly like profile the code first. For each piece of code, choose an intermediate representation based on the properties that the profiler revealed. And then from that intermediate representation, you then supercompile that piece of code in an appropriate way. And my experience with supercompiling other languages suggests you can get a couple orders of magnitude speed up in very many cases there. And a lot of it is just program specialization, but it also goes beyond program specialization. So I mean, an example of program specialization would be, say, PLN reasoning. Okay, we write a general purpose inference chainer, of course, but on the other hand, suppose you have 57 PLN inference rules that you care about, each of which has 4 variants in the truth value formula. Well, what is the optimal backward chainer for those 57 rules with the 4 truth value variants, right? That optimal backward chainer is probably a much more hideously ugly but efficient block of code than a general backward chainer, which can do any inference rule just applied to these specific rules. So you can program specialize your inference chainer to the exact library of inference rules and truth value formulas that you have. And no human will ever bother to do that, right? And similarly with like Moses automated program learning. Okay, but in your actual automated program learning experiment, you may be dealing with certain primitives in your programming language only, right? And you may do thousands of experiments with the primitives in that programming language, but as a human, you will never write a specialized program learning engine just for that exact programming language variant. It would be too annoying to rewrite it when you added one additional logic function or something, right? But the supercompiler can optimize your program learning engine to that exact collection of terminals and operators, right? And then it may take a while to do that, but if you're going to be running that over and over again for a whole series of experiments, it's well worth it. And I think the SETA architecture is very nice for that. Sometimes the output will be C code. Sometimes it will be MM2, right? I mean, hypothetically, sometimes it could even be Prolog if you were doing something super Prolog-ish. Although one expects you do better just to re-implement WAM in C and just use the Warren abstract machine in C if that was the really the optimal thing for a certain very backward chaining-ish sort of block of metacode. Now, Alexei Protopop, when we discussed this, also suggested the next step would be approximate supercompilation, which also makes a real lot of sense. Because like if you're supercompiling PLN, I mean, in the end, you don't care about getting the exact, like, truth value is 0.610 instead of 0.611 or something, right? So you may be happy with something that runs 100 times faster, but only agrees within 2% error or something, right? And so again, no one will ever bother to ask, well, can I speed up this code by a factor of 50 if I accept 5% error in the results? But you can throw an automatic optimizer at that problem and let it try to figure that one out. And I think a crisp supercompiler will be step one. But given that we're doing so much stochastic stuff, I mean, doing an approximate supercompiler, again, for a coding agent, would be a variation of the crisp thing that did it in the first place. So I think along with having these agents try to further and further speed up SETA, we can basically use SETA as the framework for a meta crisp and then approximate supercompiler, which should, that could turn out into a framework that, when appropriate, invokes all these other meta compilers too. Like if there's going to be many cases where SETA supercompiler invoking meta IL is the smartest thing to do. They can just feed that block of code to meta IL. And I thought about trying to turn meta IL into this same system, and I think you could. You would just be replicating the SETA architecture in Rust in essence, though. And I think it's kind of funny to be banging on SETA with Czar now, because in the beginning, when we started working on Hyperon Experimental, Alexei and Vitaly Bogdanov wanted to use C, and I'm like, no, you have to use Rust. C is bad. You'll never get rid of all the bugs, right? And that now Czar and I are back to using C, right? So, I mean, but we didn't have coding agents to do all the work then and hack on all the bugs then, right? I mean, because the idea that it's impossible to get bugs out of your C code was predicated on not having all these coding agents to both design the code using formal verification and then bang on the bugs, which makes things a little different. So anyway, SETA is there. It's a real thing now. It runs faster than anything else on some things, not on other things. But the experiment of vibe coding, it was certainly interesting and enthused me to try the vibe coding of the supercompiler next.
What's the S?
C.
C.
Well, it could be Keta if you want. I just thought Cheta. I mean, yeah, Cheta. That sounds very Italian.
Well,
I
it's
like
a
it.
specialized case of vibe coding, so I wouldn't say it's kind of vibe coding. It's kind of verified vibe coding in either way.
It is verified vibe coding, but the point is that no human, neither Czar nor I wrote C code, though, right? I mean, and nor did we write formal specs and mathematical logic ourselves. I mean, we interacted with coding agents by typing text, and then we set up some tools on the back end. But I mean, Claude Code itself uses symbolic tools under the hood anyway, even though not.
But it doesn't use lean, so
It doesn't use lean. It uses more simple, specialized things.
But you can tell it's using.
But it's already a neural symbolic thing doing its own simpler forms of verification under the hood, right? So yeah, that's the short version. There was a deck I made, which I think I passed in the Mattermost channel, so we can distribute that more widely too, which sort of surveys all this with much more precision. There's. Hold on, you can have a question.
So I'm really curious.
It may be that only Czar knows the answer. You can ask.
No, I think this is a question of practice. So, one of the operating principles of MetaIL is that the code you run in production is the code you prove correct, right? Whereas with this experiment, you're making a lean model. You prove the lean model correct, and you hope that the connection between the lean model and the code is tight enough. But then if the code changes, you have to go back and reprove. So,
Well, with super compilation, you're not going to exactly prove the super compiler is correct. You're proving the super compiler is correct.
I understand.
And then the super compiler is generating a bunch of code. You have to prove correct.
yeah.
I mean, you could.
But what I'm saying is, like, if you modify the super compiler, you have to go back and lead and say, can you now reprove the thing I just modified?
Well, you should formally verify the supercompiler. But my thought about how supercompilation would be used in like an AGI framework is you probably re-supercompiling components over and over again. Like we're not going to be committed to the same PLN rule base forever, right?
The supercompiler isn't going to be fixed, right? It's going to also be maintained.
Yes, and you do want to formally verify each version of the supercompiler. Right. But that sort of thing is not such a big amount of code, actually. Supercompiler is a fairly small block of heavily recursive code.
Oh,
As long as you don't have to formally verify Claude code. All right, I think that's it.
Thank you very much. Okay, to finish that segment, we do want to hopefully at some point hit on Mesto and his work with TypeScript, but for now, to keep on toward a schedule that's more like an hour behind, we will go to the PLN update from Rajuv Bio, and Hedra is here. Oh shoot, let's get the speaker working again. Did it unpair? I don't know, let's find out. Hedra, can you try talking?
Can you hear me?
We do. Kennedy, lip read. Kennedy will lip read and interpret Hedra. You totally did. It's here. This is what happened. It disconnected after lunch too. Okay.
Can you guys hear me?
Hedra. I apologize. We're still having speaker troubles. It took us a while last time. So to fill this time, Ben's going to talk about Omega Hive.
You have to give me the download of the plugin.
Okay.
Okay. He doesn't want to hear about this competing data. So I should not have my audio.
Which speaker?
This one it has power.
Could be that the power went out. There's also this one. Try that. This one just could be that it ran out of power. Sometimes that happens. Yeah, but sometimes it'll eat the power even though it is plugged in.
God.
And then the Wonder Boom should sync.
It's right here. We just can't get it to connect.
Try it
I
again.
don't think it's the same one.
Try the different Wonder Boom.
The other one. It's not seen in the other one.
Should.
This is the stuff I have never paired with before. Yeah. Oh.
Okay. About to hit it, can we? Try that. Does it work?
Here, we can test this way. It's blinking.
Maybe it does need to be.
Okay, there we go. Okay,
We're on for Hedra. The speaker's ready.
Yeah, she
Go
was
ahead.
always ready.
You're gonna get the dongle from his laptop. The dongle. Hedra?
I am ready, yes.
Yeah.
Let me go ahead and share my screen.
Good?
Yeah, I think okay.
There we go. There's Hedra's screen. And then Hedra, can you try talking?
Sure, can you hear me?
Yeah.
Ugh. There we go.
You don't hear me?
Hedra, I can't hear you if you talked, but the
I am
speaker should be
talking.
on. Oh, wait, I haven't selected the speaker. It's just me.
Oh. Okay.
Now try again, please.
How about now?
Yes,
we hear you
wonderful.
now.
We see, we hear, you're ready to go.
Okay.
Okay.
Oh, wait, it's not on this. It's not on this screen.
Okay. One moment. I see, but everybody else doesn't yet.
All right. There you go.
There you go. You're good to go now. Thank you so much, Hedra, for waiting.
No worries. Thank you so much, everyone. I will be talking about the agentic AI system in Reju Bio platform. So what we have is we have two mainly working agentic systems in the current system, and then the third one is in early experiment, which is a BioClaw. These two working agentic systems are the assistant agent, where we have 3 services connected to this agent, which acts as an orchestrator for the services, as well as classifier and explainer. For the hypothesis generation system, which is a neurosymbolic system, we have this assistant as an explainer, which is a natural language layer where it will be able to explain the graph for the user. And for the annotation service, we have a natural language query, which will be turned into a graph query, which is to retrieve subgraph information from the bioatom space. So we have a bioatom space here in Morg, as well as in Neo4j, so as well as in other languages as well, which is the exact same copy of the one we have. So that's a shared knowledge across the services, and this assistant agent has these tools, these services as a tool, and orchestrates the request towards the three services. And the third service is a Galaxy workflow service, which is Galaxy is another biomedical data analysis platform that we have access to, which includes thousands of tools in it. And this assistant agent explains those tools to the user to kind of understand what these tools are requiring from the user, the data type and everything. It's kind of suggests the user in understanding the tool better. So that's one agent. And the other agent we have is a semantic parser agent, which enriches the bioatom space from unstructured text document. It can be a PubMed article, or it can be any unstructured text document they have in there to kind of enrich the bioatom space, as well as create their own custom atom space. So when we say a semantic parser is in use in the biomedical knowledge, where we have the literatures to be turned into a graph, and it's not a single LLM call to do so. We have a series of steps in the extraction of this information. And the last step after we extract the information is we are scoring every relationship we extracted from the paper. So the scoring here would be a matrix where we have access to the language certainty when we extract the information, and we have a ranking or a scoring technique where we say this much confidence is the system about creating this relationship based on the evidence, if there is any, as well as the language certainty we have found from the paper. So that's the semantic parser agent, and these are the steps for the semantic parser to follow. There are a couple of LLM calls, as well as the traditional entity relationship extraction techniques, co-reference resolution, and every other extraction techniques has been included in this 8 steps of extraction. To show you a demo on how we are currently using it for parsing biomedical knowledge from an unstructured text document, I have this parsed PubMed article, which talks about a mutation of a gene and the phenotypes and other variants which are mentioned in the paper. We will be able to see how this system, the semantic parser agent, is able to recognize all those and build a graph that's compatible with our bioatom space. So the bioatom space has its own ontology, and that's what guiding this parsing in general is. So we have a gene at the center, which is the main gene mentioned in the paper, as well as phenotype relationships to all the phenotypes mentioned in the paper. So it's not only the phenotype, but other nodes like a variant and other nodes has been detected, as well as the relationship between them, like in here, a causal relationship between a gene and a disease has been detected. And there is also another relationship towards the phenotype and the disease that's been mentioned in the paper, and the system has got all those. So this knowledge graph will be added to the bioatom space, and everything else will be done on top of that. The second agent system that we have is the assistant agent. As I mentioned, it's an orchestrator. It doesn't have access directly to the bioatom space. Instead, these 3 services that we have are tools in this assistant agent, and it doesn't use its own knowledge whatsoever. Instead, we provide for the explanation of a hypothesis, let's say it doesn't use its own reasoning. We do the reasoning part and we pass the graph for this assistant agent to explain. And it's a separate neurosymbolic system that's giving the graph. So it doesn't use its own reasoning. And we are currently using open source models. Everything we do with the agentic system is a gamma class model. I can go ahead and show you the sample queries towards these three services from a single endpoint entry point, which is the chat interface for the platform, which is a natural language layer for the entire platform. So in this video, I'm asking to give me the genes associated to a given SNP, and then it build me the query, which is a graph query, in order for this natural language query to pass through the graph and fetch the subgraph from the bioatom space. So one thing to mention here is when this assistant agent turns this natural language query into this graph query, it uses the schema of the bioatom space. So it's a kind of verification mechanism where this ontology is used to guide the LLM to reach to the correct graph query that will be processed to the bioatom space we have here. So there is a kind of looping in here where the agent will be able to try and make sure it got the correct queries towards the bioatom space, and we will be able to retrieve subgraphs from the bioatom space. So this is a schema from what we have in the bioatom space. So I will be able to run the query here and retrieve subgraphs, which is already verified query here. The other query I can ask is for another service that we have inside the platform, which is a Galaxy workflow service, where I will be able to learn about what type of tools and depending on the data I have, what type of tools I would be able to use. Let's say here I have asked, there is a VCF file I have from a JUAS study, and I'm asking this AI assistant what type of workflow I should use to get to the phenotypes from this VCF file. So something to mention here is this assistant is only suggesting for the workflows or for the Galaxy side. It's the user who has to run this workflows under the workflow section that we have. It's just here assisting the user in order to learn these thousands of tools without going through them manually. So it's kind of recommending which workflow I should use. There is, to kind of give a detail, there is an MCP server running all these thousands of tools. That's where the agent is getting the information from. The other service that we have is a just hypothesis generation system, where this assistant will be able to explain the graph generated by this hypothesis generation system, so that the user will have a natural language understanding of the graph. In this scenario, I have a sample hypothesis generated for obesity, and I will be able to see the graph generated by the neurosymbolic engine. And I will also be asking the assistant agent here to explain the graph for me. So when I do ask, it refers whenever it's an orchestrator. So in that sense, it orchestrates and finds the current hypothesis and explains it. It's also worth mentioning that it doesn't only explain what the hypothesis is saying, it also asks or says that what the user would be able to do next. Let's say in this last sentence, it says, to validate this hypothesis, you might consider performing a crisp interference screening, which the researcher would be able to do to kind of verify this hypothesis. So it doesn't only explain the graph, it also gives directions on the next step of this hypothesis generation. I can also ask a follow-up question considering this graph, and in this exact scenario, I'm asking what the role of this gene ontology is in this graph. What does the regulation of adipose tissue development do in this graph? And I will be able to get answer from the assistant in the same hypothesis. Yeah, referring the same hypothesis, it will also be able to explain the graph. So what the third agent, which is under early experiment, is the BioClaw, and what we are aiming to achieve from the existing agentic system is to get advantage of the BioClaw's feature, which is a unique feature, the persistent memory, as well as being live, like it doesn't need to be triggered every now and then. And so the orchestration layer of this assistance that we just saw would be aided by this BioClaw. We call it BioClaw because it's an omega claw curated for biology. So this BioClaw agent we have under early experiment, we have done some experiments towards the bioatom space, and we have a bit of understanding how we are going to use this BioClaw for a better. Like the first one will be having this BioClaw agent from the persistent memory it has to kind of be able to manage the projects we have. Let's say we are currently working on a session based. So with the persistent memory BioClaw has, we might not need to work on a session based and have the hypothesis as well as the annotation done by a single user to stay as part of the agent's working memory. So it will be able to understand that better, as well as the semantic parser, as you can see, as we just saw, is a separate tool running when we ask or we give an article for the semantic parser. That's where it's currently parsing information from. But with the BioClaw agent, we are experimenting to make this BioClaw a part of this AI assistant, this semantic parser to be part of the assistant, and the assistant will have this skill where it will be able to trigger directly this parsing and enriching the bioatom space instead of having the semantic parser separately. So that's something we are currently working on, and yeah, I think I should be done by that. Yes. Yeah, if there is any questions or anything that you guys are welcome. I think I have used my time pretty fast.
Thank you very much, Hydra.
Mike or Ken, you could probably answer the question too, but yeah. Okay.
I think if Ben has a question, he can.
My question was not a deep dive on PLN anyway. So, I was wondering, in terms of the agent suggesting workflows for a person to do. I mean, in some of the earlier talks on other domains, we were seeing the value of just defining the objective and just letting the agent run rampant and do the whole thing with a clearly defined objective. I mean, I guess the question is, do you think this domain is suitable for that? Like, could you just define the data, define the problem, and then let the AI system experiment with a workflow, see if it worked or not. If not, make a new workflow and just let it keep going.
Actually, I mean, depending on the workflow, I mean, obviously, if you need to add like
attack-seek data or RNA-seek data, like scientists have to do that and add that data in.
Well, if the data is not online and you have
Yeah.
to do more lab work,
Yeah.
then yes.
But no, but that's, I mean, and Hedra can stop me if I'm talking crazy, but I mean, that's like the direction we want to go in.
Uh-huh.
Yes.
But what are the big obstacles to overcome before getting there? Because in coding or math, we're
Yeah.
sort of already there for cases where you can define the objective well enough, right?
Right. I mean, I think, I mean, just from my perspective in biology, like the obstacle is actually doing the wet lab work. Like,
Sure, but that depends on whether the question you ask matches the variety of available online data sets, right?
This is where the Galaxy system comes in, because it's an open source platform of tools, and it also has a big corpus of workflows where people have developed workflows to
Right.
answer particular questions.
Yeah.
And that's you know, there's hundreds of those in gold
I
standard.
guess one way to frame the question would be are there really interesting questions that could be answered by AI learned workflows over data that exists on the internet right now? Or does, in your view, every interesting question need more lab work?
oh, no, I think so. So one of the partnerships that we're going to be working on is with the Buck Institute, actually.
Yeah.
So Eric Verdin.
I've been there.
Yeah, Eric Verdin basically said, I want to go through all the data my lab has trashed for the last 15 years and see what's in there.
Yeah.
This is an instance where something like that.
Well, I mean, usually biologists will gather data, not
Yes.
one little thing out of it.
Right,
and then
exactly.
leave the rest. Right.
So,
Right.
yeah, so that would make good use of all the data that's existed already.
Yeah, I mean, there's a
Yeah.
huge amount of data
Of course.
on the
Oh, yeah.
internet. The
I know.
question is
Biology doesn't have a data problem, we have a reasoning problem.
well, yeah, but what you said a moment ago is the problem is usually you need to go to the lab and get more data.
I mean, if you're going to create something new, if you're going after like a new drug, like, I mean, but not always. Not always.
Well,
I mean, yes and no, I guess is the answer.
Yeah.
Yes and no.
I
I was thinking too much, I guess.
If you're going to create a new drug is one thing. If you were looking for the effects of some combination of known
Or it's
substances,
already existing.
maybe piecing together data sets would.
Yeah.
But it's just, it would seem interesting to find a class of questions that are both interesting and could be addressed using data that's already on the internet, right? Because if you have that class of questions, then you can just churn a hive of claw agents on developing their own workflows, and they can download data off the internet and normalize it as they wish.
Yeah,
right.
Yeah.
I'm not enough of a biologist, and I don't know the existing data corpus well enough to know like what class of questions that would be.
This is a good segue into Abu's talk.
Yeah,
That's the hypothesis.
Yeah, that's
a very specific problem.
This is why we need PLN.
Yeah, maybe one thing I would add is some of the workflows in Galaxy are compositional. So like one workflow is a sub workflow of another one, and there is a dependency that one has to come before the other. So language models kind of get some of it sometimes, but they are not good at this compositional way of organizing things. So there are like in this office that's experimenting on how to apply PLN. Also, he tried graph neural networks on like fixing this compositionality issue. Yeah.
Wonderful. Thanks, Abu. We're ready for your presentation as well.
Yes, with that, I will go with.
And thank you very much, Hedra.
Okay, I think let me just set my timer so I don't overextend. Okay, do you see my screen?
Yep.
Yes.
Okay. So yeah, I mean, what I will be talking about is an extension of probe meta and what developments I've been working on since the Hyperon workshop in Addis, I think in March, and especially mainly in adding support for continuous distributions. So we have both discrete and continuous random variables in the sample space, because we need those in making more accurate inference. So just to recap, previously I introduced or I kind of showed probe meta, which is the port of probe log like inference in meta, such that where each fact is a binary variable where it's true with a particular probability p, it's either true or not. And a particular choice you make over the variables gives you a unique model. And for a particular query, the probability is just the sum of all the probability, the words or the choices for which that query is true, or that entails that query. And I used binary decision diagrams for compilation of this and do weighted model counting so that I avoid enumerating all the to the power of f, which is f is the number of probabilistic factors, ways of kind of finding the exact probability of a query. So, but the thing is, in our current rule base, this is just a sample of it. We have for example, we want to use certain parameters so that they affect the weights. For example, here, we want to use the PIP, which is the posterior probability of a SNP, to be correlated in some functional form with the weight. And also we want to have some continuous distribution be used to formulate the relationship between the distance between a gene and a SNP. Here we have to resort to binning the distances by very close, and moderate. So these weights are binary weights. So the rule fires with a probability W2 or not. And we learn them using expectation maximization. So the motivation, of course, here is we want to have a way to kind of have continuous, like something like the distance between a gene and a SNP on the DNA is something like a continuous parameter we want to model. But in addition to this, we don't want to also be precise, right? So sometimes we want to kind of work or reason in terms of a bound of probability, because usually you don't know exact distributions, and this kind of the current setups forces us to assume a certain distribution. I'm getting a bit ahead. So there are already existing hybrid probabilistic logic programming tools like hybrid ProbLog, the distributional clauses, and cplint, and they allow for continuous random variables alongside discrete ones by extending the sample space. But they still, of course, require you for the continuous distributions to specify a family of distributions and a parameter for each variable. And exact inference requires calculating an integral, which is usually tractable in very limited cases. And usually, especially if you are considering multiple variables in tandem, the integral is not computable. So there are sampling-based approaches like MC entire, which we actually are using in the current hypothesis generation for performance reasons, which use approximate inference, such as Monte Carlo sampling. But again, this doesn't get around the issue that we still have to be precise about the distribution and the parameters. So we are kind of have to have a kind of precise prior. So this is one example of just how a hybrid probabilistic logic program looks like in cplint, where you have a coin which can land in head or tail, and you have to Gaussian distribution. So this is a Gaussian mixture model, and if it's lands on head, you sample from G, and if it's lands on tails, you sample from H, and you want to know the probability that of something you sample is positive from this mixed distribution. So you would just calculate it by taking the probability under head and then getting the CDF of the Gaussian from on this part of the distribution, and the same thing here. So this is how they usually do exact inference in this languages. We will revisit this example in the demo section. So one work out of this that caught my attention is the one from Michaels, and it proposes a probabilistic constraint logic based inference, where the same way as the previous works, the random variables can both be continuous, like they can be discrete from natural numbers, or they can be also be continuous variables. And also it's more general than language like hybrid problog. So hybrid problog, for example, restricts you to only have constraints like x is greater than 0, where the right-hand side have to be always a constant number, so that the integrals you calculate are single line integrals. Whereas PCLDP allows you to have x is greater than y, where both of them are random variables. So the semantics is just the generalization of the Satos distribution semantics, which problog is based on. So there is a lot of major theoretic discussion on how they extend the sample space that only contains discrete events to add continuous events, and how they define the distribution on that, and how they add rules and factors. But maybe we can discuss that in the PLN discussion, or I can go over it in detail if anyone is interested on other meetings. So how are they able to get away with the issue of calculating finite dimensional integrals, where what they do is they drop the requirement that we are required to get precise probabilistic pointers, like point estimates, and they say, what if the answer is just probability bounds, and then to compute bounds, you don't need integrals. All you have to do is, all you need is just to decide whether two events in your event space are disjoint or not. So if you can decide that, you can estimate the probability within a certain bound or with a certain range, and you kind of forego the answering a precise point estimate. So they for the sake of allowing complex constraints and supporting both continuous and discrete variables, they take the Cradle set approach, where they return probability bounds. And yeah, so inference returns probability bounds like of lower bound and upper bound. So this has the unintended consequence of allowing them to represent imprecise distributions. But I just want to point out here is that they didn't. So PLN wants and believes in having to present imprecise distributions, but these people didn't set out to actually work with imprecise distributions. They wanted a way to get around the issue of having to compute multidimensional integrals, and that led them to use Cradle sets, which leads them to have a probability bounds, and that the consequence of that is you can represent imprecise distribution. So quickly, Cradle sets are just a set of probability measures that satisfy the Kolmogorov's axiom, and that are defined by bounds. So any distribution P that assigns an event between the lower and the upper bound is admissible into this set, and this set is, of course, potentially infinite. And a single probability distribution is the degenerate case, where you only have a singleton set which recovers the precise probability. So this allows you to talk about probabilities in a way that doesn't constrain you to say something on how the mass within a particular region is distributed. So you can say the probability of events within this range can be between these two values, but I really don't know how these events are distributed. And such kind of statements are attractive for us because we also want to work in such scenario where we really don't know the actual parameters and distributions, but we have some idea of the bounds. So yeah, this is the Cradle specification. You have to specify a probability and an event, and the lower bound is formed by any event that is a subset of your current event. So all the choices. So these are the choices that are subsets of your event set would form the lower bound, and any one that's not a disjoint, that means that overlaps with it, forms your upper bound. So this will, I will show an example quickly. So say you want to estimate the probability. You have this v1 variable that is greater than or equal to, so this is your constraint, and you want to estimate the probability of Q. So one Cradle set specification can say that the probability must be for v1 less than -1 is 0.1, and for v1 between -1 and 1 is 0.3, and for it greater than 1 is 0.6. So the probability of Q is then between 0.6 and 0.9, because all the sets for which that are subsets of this constraint, which is the blue shaded one, would form the lower bound. They must account for it. And the ones that intersect with it will, of course, be part of the upper bound. So 0.6 would be the lower bound, and then 0.6 plus 0.7 would be the upper bound. But this set, for example, would not be any distribution that only assigns masses on this set would not be part of would not be part of this Cradle set specification. So this gives you a general way of it's a semantic object that describes potentially infinite numbers of distribution. So with this kind of specification, you can also be imprecise, right? So for example, if I write the risk of diabetes in the population for those that are already like the probability of having diabetes for those that are also at risk is 0.3, I know for sure, like, and then 0.6, that is also the no case, then this doesn't sum up to 1. There is a mass of 0.1 that's residual, and that mass is something you don't know about, and you are being imprecise about. So with 0.1 probability, it could either be yes, it could be a delta distribution, or it could be either no, or it could be also in any way you can sum two numbers to come up to 0.1. So this is what I said about the unintended consequence of this Cradle set specification is you can describe imprecise probabilities or be imprecise about your distribution. So yeah, this is what I was saying. So here, the risk of diabetes, the probability of diabetes, if the risk is high, is between 0.3 and then 0.4, where this one forms the lower bound because it is a subset of this event, and this one becomes part of the upper bound. So all of this is not new to PLN literature or the PLN world. I mean, imprecise probabilities have been introduced by Keynes, and then there is Wallis' work on imprecise Dirichlet model, in which turning counters into probability intervals, and there are better way of describing total ignorance than a single precise distribution. Maybe I think I should go faster for the interest of time, but This is just an interesting example I found where if you have two balls of A and B, and you know that for the first ball, the composition is there are 50 of them are red and 50 of them are black. And the second one, you only know that there are only 100 balls. You don't know the composition. If you are using precise distributions, you would assign the probability of P.54 balls. But if you ask people to bet their money on, usually they will only bet on the first ball and would not bet on the second one because they are totally ignorant about the composition. So yeah, this is just how imprecise probabilities better capture our ignorance. So the syntax is you define a Credal set like this with the masses and the events that the sets that you assign this mass for. So here with 0.7 mass, it ranges on this set between 0 and 1 and so on. These are what we call the choices for this random variable. And you use this to formulate rules. And the basic idea is to calculate the probability of queries, like what's the probability of B saved, given that you have this constraints on that. Yeah. So here everything becomes a constraint. So if the special case of a coin landing on a head is just from the domain coin, you have it becomes heads. But for real numbers, of course, equality is not defined because it's just probability of 0. So you will use less than or greater than or those inequality comparisons. So this is changing the problem from integral to constraint solving, where you just include all the sets for which your query is entailed by as the lower bound, and the ones for which your query is consistent with as the upper bound. So for the sets, there is just quickly an example I will show you here. I'm going faster through the sets for the sake of time, but for this case where you have 3 constraints, phi1, phi2, phi3, and you assume exponential distribution, and this is the Credal set specification of the exponential distribution. So the exponential distribution puts 0.7 mass on this range and 0.2 mass on 1, 2, and so on. The one that's highlighted with blue is the range that satisfies the constraint, which is both T1 is less than 0.75 and T1 is also less than 1.75 and this inequality. So this definitely forms the lower bound and the gray ones form the upper bound. So what I just want to say here is the problem of inference is turned from computing integrals into constraint satisfiability. So if you can decide which constraints definitely satisfy a particular, which regions satisfy a particular constraint, then those form the lower and the upper bounds, and those that don't satisfy it will not be part of the calculation. So here it would be between 0.49 and 0.88. And this is the generalization of the model where you calculate the bounds and come with the final bound of 0.49 and 48. And for each variable, you split on the different bounds. So here, just phi11 is the region of 0, 1 for T1, and then you split for that for the other variable. So I have implemented this in Meta and Prolog. Of course, now with Peta being available, it allows you to combine Prolog solvers with Meta, and this works now, and we can get imprecise distribution. But the only issue here is currently it's exact inference and it's exponential in the number of constraints that tie the variables together. So in the future version, we would like to support approximate sampling. So I will just quickly show a demo of this. Let me share my screen. It's this one. Okay. So here, if
We
I
can see
have,
it, but it's quite small. Are you able to increase the size quite a bit or zoom in just on those columns, on that column?
can you see it better now?
That's better. Is there, yeah, that's great. Or that
Yeah.
was.
Yeah, I mean, I have kind of paced through the slides faster because it shows me I have only a few seconds left. So it might be confusing, but I'm happy to discuss with anyone in detail. So you specify the domain. This is the PCLP syntax. So you specify the domain over which your variable ranges. So here, if it's a discrete variable, you specify, so you have 3 colors, red, blue. And then the distribution, this is the cradle set specification. So I only specify 0.5 for red and 0.2 for blue. So this means 0.3 remaining mass could be anywhere in this domain. It could be red, blue, or any combination of those. So now, if you want to drawing a color is like, so this is the constraint on color of a particular one. So this is the probability of drawing red. This is blue. And then the last one is the probability over the entire domain, because this one, the disjunction of this encloses the entire domain. So if we run it, we would get the bounds we expect. So quickly, I would focus one here is the probability of red is between 0.5, which is the lower bound, and 0.8, which is the upper bound, because we have left 0.3 mass unspecified. And the probability of the entire domain is, of course, it's between 1 and 1. And if something is not defined in the domain, it's gonna come out to 0. And so it's just, there is no mass assigned to it. So these are the different, one way to be imprecise about your distribution. And the other thing is the Gaussian mixture example I was showing here. You can, so for the head, our domain would be tail. For the coins, our domain would be heads and tail. And for the 2 random continuous variables, our domain would be real numbers. So we can discretize the Gaussian distribution by finding regions that are equiprobable. Here, I'm finding 5 regions that have the same probability for the first case where the mean is 0 and the variance is 1, and the second case where the mean is 5 and the variance is 2. And so when I ask the probability that this is positive, I get an answer which is this bound. So I think this is in this screen. So of course the answer, the one that was computed with the exact probability comes up to be 0.698. But if I add more discretization, then this is just to show some, for continuous variable, if you discretize, like say 10 regions, then the bound becomes very, very tight. So now the value of 0.68 is within this 0.04 bound. So this allows us to be both, when we want to be both imprecise, and also if you want to support continuous distribution, we can support by discretizing them, and also combine continuous and discrete random variables, and also be imprecise about our domain if you want to. So all these 3 different combinations is what I think makes this direction kind of attractive for real-world inference in this kind of in the biological case. I don't know how much time I mean, I think my time is over, but I would have liked to say something about the relation between indefinite probabilities or indefinite truth values and the current formulation of PCLEP, where the PLM book authors suggested indefinite truth values.
I apologize, but we are running
Yeah.
so far behind that we do
Okay,
need
sure,
to.
sure. Okay. I can
But
discuss
please
this.
put this in the the AGI Hyperon Workshop Mattermost channel so
Okay.
that we can pass it on to all the participants.
Okay, sure.
Thank you so much.
Yeah, thank you.
Okay, great. Wonderful. Thank you so much. Kennedy, Mike, Abdu, Hedra, thank you for your presentation on PLN, on Rejuve Bio. We're going to move straight along into the next part of PLN. So Ben, Patrick, Peter, Roman, Nil, did I miss any names? Robert? The idea is just to have a discussion on PLN. So we can move this. I think we can, they'll have to stand. I guess, free form. We'll do a chorus line. Watch the chords. This is our mic. Turn the video on.
Yeah, I mean, since this is like half the room, by this point, so.
We do need to have you guys close enough to the speaker, the mic.
Too many.
Too many. Well, I mean.
That can't move any further. Right. That's good. Now I can be lazy and lean on this.
There we
table. That
go.
was my.
We got the leaning.
Yeah.
Focus on.
Now I look like a midget. Like, what's up? Yeah. Well,
Go for it. I'm just getting the camera.
whose idea was this panel on PLN?
Yours.
Was this mine?
Yes.
Yeah. I can't remember what the hell I was thinking. Yeah.
Seemed like a good idea at the time.
Yeah. Well.
Not this.
There's a lot to be said about PLN to be sure. What is the optimal thing to say in a short time involving 6 people? This is less obvious to me at the moment, but I guess so that there's a lot of aspects of PLN. And let me say a little about the big picture, then we'll focus in on one specific thing for everyone to talk about. So, I mean, PLN, it's a concept Jeff Pressing and I made up like 27 years ago or something. And Jeff passed away tragically at age 50 from like a random meningitis infection. Like, healthiest guy I ever knew, super athlete, 50 years old. His wife woke up one morning and he was dead. It was like he breathed in some random meningitis virus and just zoinked him out, right? So anyway, Jeff and I, we were inspired by Pei Wang's NARS system. We liked the fact that it was, in some senses, axiomatic, in some senses non-axiomatic, but we liked the fact that it was AGI oriented, and it was a reasoning system that could like locally piece together premises to form conclusions without assuming some big global distribution or something. And it was asynchronous, designed for a radically unknown world that was always evolving. But we liked probability theory, and we felt that probabilistic calculations were often very useful. So we wanted to come up with something that had the favorable cognitive properties of NARS, but would use probability theory where appropriate. And I tried for a long time to convince Pei Wang that we should do this, and I still haven't convinced him yet. But I haven't talked to him about it for a while. I need to talk to him about my attempts to derive PLN NARS as a species of probabilistic reasoning, which I think he won't like either. But he might be amused. But a couple decades on, I mean, we have done practical small scale experiments with PLN on a bunch of different kinds of reasoning problems and seen that it can do often sensible things. This work that Abdu described is one of the larger scale PLN experiments we've done so far, where we've seen a bunch of help with Patrick and others in the back end, but managed to get it working on a bunch of different biological data items that are not all completely logically trivial, but there's some logical diversity to them. We've also made some progress, both working with Greg and his team and just with Czar and his army of AI agents, made some progress on, and then my own army of AI agents, on formalizing what could PLN be as a logic, right? And the basic philosophy I've taken is PLN is more of a concept and a body of heuristic practice. One can formalize that into logics in a variety of different ways. And actually, we have a system that can make up its own logic formalisms and reformalize things in terms of it. That's part of the meta aspect of meta. So it's fine if there are many different formalizations, but it's nice to have more than zero formalizations in the logic, right? And so that work is all progressing. I think that the big bottleneck that we face now, and I think are about to overcome, is, and before I get to that, the other piece is uncertain truth values, right? And Abdu was hinting at that. So you have simple truth values, which is strength and confidence, similar to in NARS. We realized from the beginning that a really simple truth value, where truth value is just a probability, is bad for many reasons. We did a bunch of work with strength and then confidence or weight of evidence, 2-component truth values. When Matt and I did a bunch of the work leading up to the PLN book, we ended up with more components than that, like a 3-component truth values, indefinite probabilities, sort of a strength, and then an asymmetric confidence interval around that, which often lends itself to beta distribution type modeling. Sometimes you want a full probability distribution, even a higher order probability distribution. In certain insane cases, an infinite order probability distribution, right? So all these things are important, and I feel like we substantially have a handle on them. I think that the big bottleneck or the grand frontier is scalable inference control, which is like how, given a whole bunch of data of diverse but logically formalized, but diversely uncertain nature, and given non-trivial conclusions you want to draw based on that, like how do you actually get PLN in limited resources to draw useful conclusions? And that's we always knew that was the hard part, but until we had a reasonably scalable infrastructure with sufficient flexibility, we couldn't experiment with our various good or bad ideas on how to make scalable inference control work. So I think what seems like an amusing thing to do with this panel is just go around and let each person say something about what they think may be a plausible approach to making scalable inference control for PLN, and sort of what does the roadmap look like there? And there's a lot of overlapping views here, and there's also just a bunch of different things that can work, right? So it's not something to which there's one answer. Like we don't know to what extent there can be one default inference control method and then other specialized ones, or to which there may be multiple default inference control methods. So yeah, let's jam a bit on inference control. We can start with Patrick.
Yeah, from my perspective, I mean, I have been working for years on inference control in NAS. And there was one collaborator who unfortunately passed away, Tony Lofthouse, who has always looked at inference control from a spiking neural network perspective. And I always found that extremely fascinating because he tried to come up with a structure where essentially all reasoning would be event-driven. Like you could have different structural nodes in the network, but then if you activate one composite node, it would essentially also activate the components. And also the other way around, if a certain set of components gets active, then it would prime or activate corresponding compounds that include that component. And up to this day, it's a bit different direction than the idea of geodesic inference control, but I always found this idea of event-driven inference extremely compelling, even though I have to say we never got it to work extremely well. So I'm always hopeful that there are multiple approaches that could lead to scalable inference control. And I still think that Tony Lofthouse was onto something with this approach, but
to connect that with the geodesic idea, though, like if you were using whether a spiking neural net or a simpler predictive coding neural net or like a chaotic Izhikevich neural net or something, but I mean, if you're trying to use a neural net to do inference control, if you're training that neural net using some sort of predictive or causal coding guided by information geometry, then it becomes geodesic inference control. Like, I mean, the neural net itself is finding the shortest path from where it is towards something that's making the suitable predictions, and that hypothetically that could lead to like a neural symbolic inference controller, right? where the neural net using information geometry is trying to find the shortest path from premises to conclusions. Some more standard geodesic inference controller using atom space operations is doing the same thing, and then you have feedback there. That, like, if I think about that in a little more depth, in the geodesic inference control idea, like you have a bunch of forward chainers and sort of a bunch of backward chainers, and the forward chaining guys are trying to meet up with the backward chaining guys in the middle, and you have the idea that you can send out some cheap probes, right? So like the forward chainers could send out some probes doing very greedy inference. You see if any of them hits one of the backward chainers, right? And vice versa. Well, you wonder if some sort of neural quasi-geodesic inference controller could be like an expensive kind of probe mechanism there, right? I mean, it's not as lossy as just sending like stochastic agents wandering through and not as cheap, but it could still be interesting and maybe could be holistic in a way that's harder for a more standard algorithm to come by, right? Because you could train that network doing neural inference control on a bunch of the atom space. So then you have probes that are sort of reflecting a neural model of atom space structure. So it could be possible to put the pieces together. I don't know.
I agree. And maybe it was the missing piece. Maybe the geodesic aspect could also have been what's missing in the kind of spiking attention approach.
Well, possibly the spiking thing can come up with interesting paths that are a bit too noisy. Like if that's the case, the geodesic thing has a use for noisy paths, right? Like they're the probes that you use and try to connect the forward and backward.
I agree.
But how to make it in the current PLN implementation? That's the thing. How to integrate it.
I mean, first you would train the neural network, right?
Well, yeah.
And try to get it to do something, and then you would connect it to the geodesic thing. But whether a spiking neural net or some other form of neural net or nonlinear regressor or predictive coding network or something is best, I don't know. I mean, in in the vein of getting the AI agents to do everything, the first thing you would do is try to make some evaluation corpus for what the neural net is supposed to do, right? Like if
That is what it, right. That's the thing. I mean, scaling symbolical system is a bit difficult, and also we have to find test cases how we should train it and how we should recognize if it does the same things, if it performs the way it is, and it does not perform the way we want.
seems like you need a case where you can write a script to generate a whole bunch of test examples.
Yes, and
once you've got that shitload of test examples.
Yes, and specifically the difficulty comes to verify the truth values for it.
Well, the biology has a lot of truth values.
Yeah, yes.
Or if you have a simulation or game environment, then you can just figure out did the agent perform well. Then you can assume the truth values made sense.
Then you also somehow translate it to the real world experiments.
Well, yeah, but for finding a way to get all these algorithm ideas to work together, I would say gathering probabilistic data from a video game world is perfectly fine, and there probably are a lot.
Or you can even simulate it.
Simulate the video game?
No, some events, simulate some events, and then try to do neural networks on that.
Yeah. I mean, you can simulate events, but I think. I mean, we've been talking a bunch about video game worlds for testing PLM before, but I think for gathering training data on outcomes of different situations, you can get a lot of inference control training data from a game world. And I think if you have that training data for what you need out of an inference controller, then it is straightforward for coding agents to try different neural architectures and spiking or integrating fire or Iklé or predictive coding or blah blah blah. And you can try and see what works for neural inference control, and then see in what sense it works, right? Which would tell you how to piece it together with a more symbolic inference controller. Because I mean I like the idea that you can train a net on the atom space, on a particular atom space, right? And then the neural net can figure out how to do inference control, incorporating like the higher order combination statistics in that atom space. Like that's a nice thing which goes beyond what a standard computer science geodesic approach or just stochastic probing will do, right? I mean, it will also bias you toward your distribution that's already there in your atom space, which is fine for many things. But then if you want to come up with something crazy, then maybe it's not fine, and maybe you're better off just with the brute force of a pure symbolic method.
I think that is
You have to yell.
I think that it is. I think that it is potentially a huge issue that learned distribution doesn't match to the distribution of the problems it faces at one time, right?
Yeah, I mean that's why kids are so stupid, right? I mean, kids are always generalizing based on what they've seen, and then they make a lot of mistakes, and then they see more, right? So, yeah, I mean, I think it's hard to escape from that dichotomy, right? Like either you're extrapolating from the knowledge that you have, in which case you will do bad at weird novel things, or you're not extrapolating from the knowledge you have, like in which case you must brute force try every combination, right? So I mean, I guess if you have a nice dial the system can turn between those two extremes is probably the best you can hope for.
Maybe it needs some Thompson sampling to go between both.
According to Nil, everything needs Thompson sampling. You know.
So
you may not have told everyone else why. No.
So for inference control of PLN, the general approach I suggest
is first to formalize what you mean by inference control. And then you take this formal description, you translate it to PLN itself. Okay, so now you have in PLN a formalization, what it means to control PLN. And that way you can create a feedback loop where as PLN gets better, because of inference control, it also gets better at doing the inference control. Now, I mean, and the Thompson sampling comes into the play because, of course, this formulation is going to involve uncertainty. I mean, basically, once you do this work of formalization, you realize that you can express that as a form of conjectural.
Yeah.
And so you have a proposition and you ask the question, what is the probability that this proposition is a theorem? Okay. And in PLN, you're not going to get a probability. You're going to get a distribution. And then when it's time to deciding whether you should assume that, well, it is likely, this conjecture is likely actually a theorem, then you allow yourself to explore this branch. When you do that, well, you need Thompson sampling because at some point you're going to have to rank different doors, different paths.
Yeah.
And so to take the best one, but in a probabilistic manner, then you use Thompson sampling.
Must be different to be a logic engineer. I've tried to formalize what it means to control myself, and it hasn't helped me at all.
So I certainly don't exclude that you're going to have to use any practical tool that is at your disposal, like a neural network.
Yeah.
But at least having this, how to say, a very, a structure that you can trust in terms of, well, I mean, it's going to give guardrails where, well, if you derail, you know how much you derail because you know you
I heard that as God rails initially.
Yeah, good enough. I'm okay with that.
Yeah. So it's the universal distribution gives the guardrails. Yeah. Yeah, I mean that totally makes sense mathematically and is very well grounded. The question of when and how you can apply that at a very large scale is less clear to me. Like that intuitively feels more like what you do like within the working memory when you're doing like careful deliberative reasoning. Whereas if you're trying to choose an inference path from like a huge teeming mass of billions of atoms, I'm not sure how you formalize all the higher order dependencies between all the variables in practice that you need to make the probability estimates. Whereas the neural net is just kind of hacking.
Yeah, sure. I mean, in practice, I'm not saying that it's easy, but you can just do induction, abduction, revision. It's just that you have a space of implications where you allow the hypothesis and the conclusions to be composite, and so you have an infinite space potentially to explore, and it's difficult and so on. But at least you have a way to represent these predictive patterns.
Yeah.
Yeah.
Master, why don't you come here so the audience can hear you?
Had a comparison, this is like a PLN in the hood discussion that you very often.
Yeah.
I was thinking, I mean, looking at the software like AlphaGo and these type of neural theorem provers, what are they really good at? Cutting down the search space. And I feel like if we can, with the predictive coding technology, we can have a world model of, like, for example, let's say it's dealing with it wants to prove a math problem, right? And it knows from the past history that, like, it kind of does, you can you know how there's induction, abduction, and like NARS, it has like these type of type of rules. I kind of see them as rewrite rules, and you can kind of take like random walks and then see where you get at, and what is the point of this? The point is that the goal is it learns through any arbitrary, I guess, rewrite, but now it's going to be contained within the NARS reasoning system, where, for example, to do analogy, when to do deduction or induction for, I guess, what the world model you're dealing with. If I'm dealing with something of mathematics, it will learn that over time that the best way to get there is through deduction, because math is, you know, a very formal thing. But if it's something like art, I don't know, art, or trying, let's say, being a detective, then it will learn through whatever. You can Monte Carlo, or you can like try like Thompson, like sampling, but you know, parallel. What you can do is you can use the assistance from maybe like a predictive coding transformer in the future, to then learn what type of intelligence. So it's like metacognition. What type of intelligence is best to do in what type of world model that you're dealing with.
Sure.
That's what makes sense. Yeah, that was an idea I had. So.
Yeah. Totally aligned with everything that
I think in the end that should be necessary for general intelligence, right? There's probably not one inference control heuristic to rule them all, right? So
yeah,
I mean, of course, part of the meta-ness of meta should be it can synthesize its own control heuristics when all the ones that it knows run out of steam, but we do need to see that with something that works better than the current thing, for example.
Yeah, I noticed a few things while playing, like with PLN, like if someone says like Bob says the server is bad, and then another one says Alice said that the server is bad, I don't know, because of Bob, then the problem it was PLN, it kind of duplicates, it counts the evidence twice rather than doing provenance.
It doesn't have to. I
Well,
mean,
we've had prior versions of PLN that did not have that problem.
I see.
So I mean, they simply didn't put that in there yet. Right? I mean, there's a whole literature of, I mean, NARS and early versions of PLN use inference trails, right? Where you just each node or link and each truth value keeps a list of what evidence was used to produce that.
Like an assumption
Right.
maintenance system?
Yes, but the problem with inference trails is it's too crude, because then sometimes you may have used A to get B to get C to get D, but later on you realize, well, actually going the other order would have been smarter or something, right? So then what you really need to do is just keep a record. I mean, ideally keep a record of just like the whole tree of inferences that was used to get to that conclusion, and then when you need to, you can go and slice up those trees and you figure out where there was redundant use, and you just
you could abstract it out.
Yeah. On the other hand, in the quite opposite, so I think that is something you often want to do. In the quite opposite direction, in 2008, Cassio Panaccio and I wrote a paper doing PLN in a completely different way, where you don't use any trails at all, but you just assume you're doing many redundant inferences over and over again. It's much like in a loopy BaseNet. So what we found there is if you don't keep any records of the provenance, right, but instead you just keep reasoning around many cycles over and over again, then on the whole, the multiple counting of evidence comes out in the wash, and you roughly get the same conclusions you would get if you were keeping careful account of evidence. So then there's two ways of wasting effort there, right? And how they're
which is more scalable?
It really depends on the case, and I don't know. So in some cases, clearly in some cases, clearly you're gonna fuck up too badly by doing a lot of random things. Like anything close to math reasoning is probably like that, right? Like for things that are very mathematical, each inference step is being expensive, so you're just not gonna be able to do all these scolarizations and quantifier manipulations over and over in enough combinations to get rid of the errors. So I would say if something is very mathy in the sense that the meaningful inferences all involve very deep and complex quantifier interchanges and stuff like that, then anecdotally, you're better off just to keep track of what you did. If what you're doing is very shallow and some biological reasoning, but not all, some common sense reasoning, but not all is like that. If it's shallow and more heavy just on heuristic truth value evaluations rather than complex, like deductive high order reshuffling. So if it's very heavy on these shallow truth value manipulations, then I found often you can just do everything around in loops, and this is more like the cases where Markov logic networks or loopy Bayes nets work, right? Because MLN or loopy Bayes net, they're not dealing with quantifier manipulations much, right? Like I get it's pretty much a propositional logic and then dealing with quantifiers in a very crude way. And MLN is basically like that. Like MLN is just looping everything around until it settles into some state. And you're multi-counting evidence, and this figure comes out in the wash. And so you can run PLN in an MLN-like way, and it will often work, right? So in the one case, you're wasting effort or using effort, keeping careful track of the provenance of everything, and making sure you're not multi-counting evidence, right? And in another case, you're spending a lot of time doing many redundant inferences around in loops and hoping it all averages out. And I mean, either one is burning a lot of electricity and processor time. And then it seemed like what you ultimately, just like another case we're talking about, like you need a dial for the system itself to twist.
But could that be learned?
Sure.
Yes, it can be learned, but it will have to be ongoingly learned depending on the domain, right?
Yes.
Yeah, it's a similar theme to when I was talking about the SETA compiler. Like you profile the code, then you figure out how to optimize that piece of code into the right unique representation based on its properties. And in the same way, you could have a long inference, and you can even figure out, like for this part of the inference, I want to keep track of provenance of everything. For this part of the inference, just let it go nuts because everything is so heuristic anyway, right? And that's it. And yeah, the system should be able to tune those dials for each part of a lengthy inference, right? But on the other hand, now where we're at is just trying to get any scalable inference control mechanism to work. But clearly for AGI, yeah, it has to go in this direction where you have multiple to be mixed and matched in an ad hoc way based on the system, and then how you deal or don't deal with provenance is part of one of the things that will be mixed and matched by the end user.
Yeah, I 100% agree. I feel like was this metacognitive, I guess, control that would help it be more scalable because it'd make. I mean, the problem of scalability is the search space, right? And so if it can, like the mind, how we construct predictive models in order to reduce the I guess energy of like how much should I expend my energy I don't know, running or doing something, right? And so what I was trying to say, the having this metacognitive ability will allow to reduce the search space, which would then allow it to be more scalable. That's because I feel like symbolically, unless there's someone discovers some crazy algorithm or whatever, it's always going to be intractable. But neural networks or transformers, they reduce it heavily. You can think of, have you ever seen in an LLM? I mean, like the probability of the next word, and you can see like if you like. It shows what the next probability of the next word is, and it shows it obviously doesn't show every single word, all the 50,000 tokens, but it only shows like the top 10. And you can play with burstiness and perplexity to make it more creative with what it picks and less creative. And I guess you might be able to apply this similar model into inference itself. It's
Yep.
interesting idea.
Okay, I'm going last thoughts on PLN.
We haven't had Roman yet.
Roman, last thoughts on PLN, wrap it all up.
Are we,
Sure.
we have the final verse of ultimate wisdom here. Yeah.
Well, I haven't thought that much directly about inference control. I just know we didn't have anything that worked yet, so I tried to get a chain that worked without it reasonably well. And well, the latest success is running on MM2 now and scales better than before. So, and once we have an inference control mechanism, you can just plug it in there. Yeah, I guess.
Yeah, in terms of MM2, one idea I had, which I think still will be good, is for many kinds of reasoning, factor graphs should be highly functional. And well, yes, it's like sigma, but sigma is applying factor graphs to propositional logic. Basically, what I realized is you can apply a factor graph over any commutative algebra, like in any quantale. It doesn't just have to be and and or, right? So you can apply a factor graph over any algebra of inference operations. So you can apply a factor graph over PLN's full spectrum of inference operations. And then for many if you want to do sort of shallowish reasoning across a large atom space, a factor graph is very nice for that because you're just organizing the whole atom space in an efficiently structured way. And you can just propagate reasoning up and down through the factor graph. So sigma I liked, and Paul Rosenbroom is a good friend. His health isn't good lately, but he used to come to all the AGI conferences. But he's not here now, is he?
The third phase.
Yeah.
Beginning to fact that working on PLN adjacent.
It's just the PLN's it's been around so fucking long. That's the problem, right? Yeah.
Two untimely deaths and on Elsie.
But sigma is good, but the way Paul has applied it, it doesn't deal with quantifier logic. It's more like MLN-ish, right? So you're dealing in essence with propositional logic over multi-argument predicates, but you're not able to deal with nested quantifiers even to the level of full FOL, let alone higher order logic. So what I had mapped out and Adam had helped prototype a bit was how would you apply factor graphs to quantifier logic rather than just to propositional logic plus. And I think that part works nicely. And Adam implemented a simple prototype of factor graphs over Mork in MM2. And then I think it was never taken beyond that, but it's pretty clear how to do it. Then the open question is, I mean, you are making certain independence assumptions in constructing using the factor graph, right? And then the open question is for what atom spaces and what questions are the independence assumptions implicit in using the factor graph to do inference? In what cases are those worse than the independence assumptions you'd be making, doing things in some other way to such a degree that it counterbalances the sort of operational efficiency gains of using the factor graph, right? There's always some trade-off buried in there, right? Like, which is either error versus accuracy or error of type 1 versus error of another type or something.
Got it right.
All right.
All right. Awesome. Thank you very much.
Wait, are you gonna wrap?
I'm gonna wrap.
No, never mind. Don't wrap. Please, never do that again.
Yeah, and we're gonna hop over to Fabric PC real quick so that we can get to Omega Hive and motivations before the screening starts.
What time is the screening?
It's at 6 and it's 5:15, so 6:30. Am I?
Oh, it's a movie.
It's a movie?
I've seen it.
This way.
I mean it too. The one funny thing is that by the end of the movie, they took the movie video, my daughter makes her.
Oh, sorry, you can have that. I just didn't bring some. And I will let you in.
Did I let you in already?
I mean, that's another whole time work.
PC and then
that's not. But because it's.
It's not going to. Okay. It might be a little more than an hour is a feature length film. Oh, or an hour and 10 minutes. An hour and 10 minutes.
It's extracurricular. Swap food.
That's that. Oh, now I'm convinced. Nice.
Don't forget popcorn. Try.
Oh, popcorn.
You don't like it? No.
Oh, we're not connected here.
Oh.
That's way too small for people to see. Okay, how are we doing? Okay, we got that. Everyone can see the screen. It is being shared. Can you check?
On Zoom?
Let
me try again.
It was, and then it stopped. There we go.
Okay, how's that? Awesome. Okay, there we go.
I still have.
Okay, hi. Welcome everyone. Thanks for being here. I'm Matthew Barrand. I'm Senior AI Researcher at SingularityNET. I'm here to provide a treat for you. You're going to hear about neural networks. So this is the neural side of the neural symbolic story for SingularityNET. This talk will introduce a little bit about predictive coding for those who don't know what it is, and then I'll explain why this is interesting and what you can do with Fabric PC, which is SingularityNet's infrastructure for building and training neural networks with predictive coding. It is open source on GitHub. You can go to trueagi.io/fabricpc and get it yourself. There are two ways to run a neural network. The most common that everyone in the industry has locked into due to popularity and attention in conference circuits is backpropagation, which is on the left. So activations feed forward layer by layer through a network going from inputs to the output layer in just a sequential chain. That is not the only way to run a neural network or train it. Predictive coding, PC, on the right, instead of just feed forwarding through all the layers and getting an output with a prediction and some error against a label, there's actually an error at every layer of the neural network. And what that means is that we can actually train with locality, similar to the way the brain learns. The brain is a local machine. It's not doing backpropagation with a chain rule through every layer of your neural circuitry. It learns locally in a Hebbian fashion. And predictive coding is a neuroscience-inspired technique that is a little bit closer to that. At least it provides locality, and it provides a more general way of learning neural networks. Cortex is not doing backpropagation for sure. It's not literally doing predictive coding either, but it's a lot closer to it.
And so predictive coding started as a theory that the brain forms abstract hypotheses and attempts to predict its inputs, and that each layer of neural processing in the brain attempts to predict its input layer until it gets to a raw signal of the ultimate inputs the brain receives. So the brain is essentially trying to predict what its inputs are going to be, and it processes its residuals. Like, what's the difference between what it predicted and what actually happened in the real world? And to just update those residuals to minimize that error. That's essentially what predictive coding is doing. So where this dotted box here, dash box, represents a single neuron, instead of just a single output of this neuron, the prediction of the neuron, that prediction is a predictive coding neuron has two states. One is mu, the neuron's prediction of what its state is going to be, what its neural activation is, and Z, its inferred neural activation, which is completely independent of the forward projection of its weights. Now, because those two states are different quantities, we then have an error between them. I'll show you how this works in an entire network. But predictive coding, essentially, by tracking these two states, provides an error at every layer of the network, and then uses energy minimization to do credit assignment of error from the outputs all the way through the entire network to each layer. This allows every layer of the neural network to have an error. So what do I mean by like relaxation of energy and error moving from the output layer to deeper layers? Instead of back propagation, which does a derivative chain rule from the output through every neural activation of previous layers and then to the weights of that layer, what predictive coding does is it uses an energy-based model framework where initially all of the errors at the output, the difference between the final output projection and the label. But then how do we do that credit assignment to all of the inner layers and figure out their errors? Well, we do it by energy minimization. So it's kind of a diffusion process where energy, you can think of it as like potential energy in a physical system bunched up at the output layer. That potential will then relax and spread across the entire network like this, doing local hops of credit assignment. So Z6 will ask, how can I adjust my internal state to minimize the error at Y? And then Z5 will say, well, now I see error at Z6. How do I minimize the error at Z6 by adjusting my internal state at Z5? And this spreads like a diffusion process across the network. I'll do that again until the energy is spread out somewhat smoothly across the entire network. This is called the inference phase of predictive coding, or energy relaxation. It's an iterative process that backpropagation does not have. So every time a new data point X comes into the network, we start here and we run through some inference budget of T cycles to spread out error across every neuron and every neural layer of the network. Now at this point, each layer has a prediction mu and an inferred state Z that minimizes that overall error. And so now there's a difference between the forward projection and the optimal state for that layer. That error signal then gives us a local signal to adjust the weights at every layer independently and in parallel. So how does that work? It's a bi-level optimization problem. When you train a neural network, overall, you need to learn both the neural activations and you need to learn the weights. What happens is there's an outer loop for learning weights and an inner loop for spreading error across all the layers for every data point that comes in. So we get a new mini batch, we run the inference loop T number of times. This might be like several times the number of layers in the network. So maybe 10 or 100 times. We do this quick inner loop, spread out the energy. Then we have an optimal state of the network, which is different than what it's just forward projection would be. And then we can take that error at each layer, that difference, and then do a local learning on the weights in the outer loop here. And then now it's ready for the next mini batch of data to come in. Another way of looking at this is backprop has a forward transfer function F inside each layer or node. And all you get is the neural activation mu. There's no error, just activation, feed forward to activation, and so on in a sequential chain. And predictive coding says each one of these, we're going to split that. We're going to do the forward projection through the transfer function through parameters theta to get our projection mu. but then we're going to create an inferred state Z that can independently be tuned in the inference phase to estimate the ideal activation for this neuron. Okay, so what's the difference between PC and backpropagation? Here's a table of the differences and what each buys you. The gradients in predictive coding are local. Each node computes its own local gradient. There's no entire backchaining gradient through the entire network. This provides a high degree of node parallelism as well as locality to learning. This potentially has neat implications for plasticity in neural networks, how we break up and shard compute, and a whole bunch of other implications for architecture about how we even build neural networks. We don't need to be locked into sequential chains anymore. So I think there's a lot of opportunity for completely rethinking how neural networks are done and what we consider to be efficient processing. These long chains and ResNets, transformer architectures, these things are all optimized to GPU hardware and sequential chains that work well on GPUs. But without being locked into that, other hardware like neuromorphic hardware that is well suited to be married to things like predictive coding, local learning, there are new opportunities for graph-based architectures of neural networks that more resemble the efficiency of the brain. Perhaps we can train transformer or LLM-like things that aren't literal today's sequential transformers. Perhaps they're shallower and more highly connected graph networks that are perhaps more efficient. Perhaps even better continual learners. So information flow works differently. The information flow is local hops in predictive coding, whereas in backprop, you have to run through the entire chain forward and the entire chain backward. And credit assignment in predictive coding is an equilibrium of local errors. So it's a diffusion process where the error spreads out. And once it's reached equilibrium, then it's the optimal neural activations. What locality buys you is a match to neuromorphic and analog hardware, which I think is really interesting because we're running into a scaling wall by brute forcing scaling AI and GPUs. The data centers are getting so large and it's a huge amount of energy. And while that works right now and it's still economic, that is going to run into a wall pretty soon. Every industry is going to want to serve more inference, more LLM calls to users, and scaling up user base and usage of every user and building more capable models is going to require more energy efficient approaches. And predictive coding provides an avenue to do that on the algorithmic side, and then married with neuromorphic hardware, which is in development in many research labs and industry, then we have a clear pathway to scalable AGI serving a massive user base. Again, with arbitrary topologies, I think arbitrary graph structures are going to get really interesting once we start applying predictive coding to them. And you get native associative memory in predictive coding. And Fabric PC has hop field nodes and supports cyclic graph structures natively. A couple of things about PC. It's still in what the research community would call very early phase, or it's been perceived as only working on toy models. Well, actually, neural networks were in backpropagation were in the toy model stage 2 not too long ago. Neural networks in feed forward and backprop solved their depth scaling problem over about 20 years of research. And predictive coding has compressed that timeline and caught up recently in less than half or a third of that. And just in the last year, in 2025, predictive coding solved 2 of the key depth barriers. One was forward scaling up to 100 layers to control exploding variance using the mu PC technique. And the second is controlling the backward vanishing gradient problem, which in predictive coding is known as exponential signal decay. That was solved with error predictive coding, EPC. These 2 techniques together effectively allow us to run predictive coding to 100-layered deep networks on par with other deep neural networks today. So PC has just gotten very exciting, and it's in a wonderful space to do research in. Fabric PC is SingularityNET's answer to bringing the research community up to speed with state-of-the-art predictive coding. and providing a library where everyone can develop neural networks, train them, and build them. And we'd love to have you involved in using it. So we've integrated MuPC into Fabric PC just last month and shipped that. So it also generalizes MuPC, whereas the original paper that was published last year only works on sequential chains for ResNets using MuPC scaling. Fabric PC has implemented a generalization to arbitrary directed acyclic graphs. And then that also provides an approximation to running cyclic graphs as well. So MuPC benefits as cyclic graphs as well. It is super easy to define graphs in neural networks in Fabric PC compared to other predictive coding libraries. We have a very nice graph-based API where it's very straightforward to define a set of nodes, what type of forward process compute they're doing, and then define a graph structure listing the nodes, defining the edges between them, and then providing a task map of which node maps to inputs or outputs on the data loader. We also provide a hook to what inference algorithm is going to be run. It's a highly extensible library. It's very easy to define custom nodes with your own forward transfer function. And also the inference algorithm itself is extensible from the base class. Here's an example of extending the node contract. The user just defines 3 functions in order to set up a custom node doing any arbitrary computation. Define what input slots are there for the node, what's the initialization method for the parameters of that node, say what parameters it has, and then the forward method takes the inputs, applies the parameters, and gets the projected output. That's straightforward. You don't have to worry about anything about the dynamics of PC. That's all handled entirely under the hood. Fabric PC follows the graph topology, applying local auto differentiation using JAX to every node. That's also a huge leg up on other predictive coding libraries that do require a fair amount of boilerplate code to implement predictive coding itself. The network's beliefs are also highly debuggable. There's a node state for every node in the network that carries the state variables that can be plotted using tensor plotting libraries like AIM or equivalents of TensorBoard. Fabric PC is for anyone doing predictive coding research, working in energy-based models, next generation AI techniques, alternatives to backprop, things that we believe will scale far into the future and be more energy efficient and open up new architectural paradigms. Neuromorphic hardware and analog hardware teams, we're actively looking for collaborations and partnerships right now with neuromorphic hardware teams to run with Fabric PC, doing simulations on the real world hardware noise constraints so that we can run modern real workload LLMs and deep neural networks on the equivalent of what that future hardware would be even before it's arrived in fabrication. A few things of what Fabric PC can do today. We have a ResNet 18 demo in there running classification on CFAR10 images. It's a 31 node network and 38 edges. This is a real world high quality ResNet on image data. And we have language modeling with a small PC transformer trained on tiny Shakespeare, a 2-block transformer, very compact for running quick demos. And we have active research with Bezwood Abawa's team developing that transformer. We have Nardos Tetek in ICOG running a project to integrate transformers and probabilistic logic networks so we can have a true neural symbolic transformer. Anyone who's interested in that in this room, connect with Nardos on that project. And then we also have ChairNet at ICOG starting a project on associative memory, building out modern hot field nodes, which are highly dense associative memory, and basically functional equivalents and even mathematical equivalents to transform dot product attention, but implemented as hot field nodes. And then these are just some quick examples of our demos. And then I just want to mention the hop field nodes in Fabric PC are just really amazing for denoising data. And there's a demo in there that shows an experiment of how you can chain together multiple hop field nodes and compose them in a network. And by composing multiple hop field nodes in a network, it has cumulative gains in denoising corrupted image data to classify it. Whereas, commonly you might think of a hop field network as just recalling a fixed memory. In Fabric PC, hop fields are composable elements of a neural network. And so each layer of the network or each node in a graph can learn what memories are appropriate to recall as features and then perform the denoising on incoming features to find the nearest memory that's closest to that, denoise it, and then pass on that signal to the next layer as a feature. Here's a quick view of our roadmap. In August, we're integrating error-based PC to fully scale to 100-layer depth in deep neural networks and have them learn meaningful parameters at even the deepest layers. In September, we'll be adding node parallelism and acceleration of Fabric PC running on GPUs and adding model checkpointing and convenience features for developers building and training models of Fabric PC. In October, we plan to have all of this locked down and ready for doing a public hackathon so everyone can enjoy building with us. Thank you so much for listening today. Fabric PC is about networks that infer and continue to learn. It's not just about compute. And join us on building AI that scales far into the future. We have time for one question? Maybe not. Maybe we do.
Time for one question.
One question. Miles had one. Michael.
Oh, you'll have to repeat it, Matthew. It has to be quick question.
Is there any notion of time?
That's a great question. The question was, is there any notion of time or temporal decay in the network? And yes, in the energy relaxation phase, that is essentially a discretized time process.
Just keep talking.
Yeah. So you can. You can think of it as you can think of the energy relaxation phase as a physical process with a discrete time solver just stepping over fixed time steps. Of course, there are more sophisticated ways to do that, and differential equation solvers with Gillespie solvers or Newton solvers. In predictive coding, that discretization is really just an approximation for letting the energy relax over time. In implementation on true analog hardware, where PC naturally runs on that efficiently, that's actually a continuous time process that doesn't get discretized. So like on analog memristor crossbar technology that we're eyeing as one example, that actually just runs continuously in time, and there's this time constant associated with how long it takes that to settle and converge that is associated with the stiffness or of the system.
Super high quality stuff.
No.
I think we mix
No, not perfect. I lost the deck. And there we go. All right, here we that. Full screen. Yeah. So yeah, that was a great presentation by Matthew, and I think that while Fabric PC is not Hyperon in the narrow sense, we've seen that we want to do a bunch of creative things to sort of train predictive coding neural nets or predictive coding parts of larger neural nets to connect closely with atom spaces. And so Fabric PC gives a very nice framework for doing that. So I'm psyched to have it as part of the picture. As the last thing in this very packed day, I want to go back to what Patrick was talking about. Oops. Is it? That will overlap the movie then, yeah. Oh, it's not 6 after all. Even better. Yeah. Yeah, so cool. As the penultimate event of the workshop, and I want to continue where Patrick left off, talking about Omega Claw, and talk about both the design for a hive of Omega Claw agents, and then talk about some actual experiments I've been running using a small hive of agents as a sort of emergent research assistant, which has been very chaotic and in many ways time wasting. On the other hand, also has been very time saving and productive, and even in a few cases intellectually quite interesting. So I'll talk about the design of how we're aiming to do it first, and Cassio and some other colleagues are working on building an Omega hive as it should be done. Then I'll talk a little bit about what I've been doing with an Omega hive built as it should not be done, which has been helping learn something about how it should be done, as well as learning some other things. But it's here. Okay, let me go back to Zoom. Yeah, this is a very suboptimal way of doing things. Yeah. Okay, let me try to share again. Okay, is it there? So I think before it got shared and then unshared somehow, but yeah, my kids are unsharing all the time. So I mean, yeah. But now it won't let me make this big again. No. No. Oh, right. Okay. Well. You're close enough, I guess. Yeah. Okay. So, yeah, the notion of an Omega hive is, I mean, inspired on a practical level by how in Claude and other proprietary frameworks, you can put a bunch of coding agents together in a swarm to do things. But you're very limited there in how the swarm can interact. And of course, all your data and everything and control is being sucked into Claude. So if they decide to throttle your code or your research question, all the knowledge your agents have becomes useless, right? So it seems valuable to have hives of agents just doing things for you that are under your control and can dip in and out of proprietary tools in as much as is useful, but without storing, the bulk of their knowledge and their control nexus within the proprietary ecosystem. But after playing with this sort of thing a bit, I realized it's probably the right first pass operational control mechanism to use for an early stage Hyperon AGI, right? And I mean, we had something called the COG server in OpenCog that was never really very well designed, but it was sort of the control loop that would keep operating the cognitive cycle for an AGI system. And then we always knew if we had multiple machines, they each have to have their own cognitive cycle. And we hadn't really gotten to thinking that much about how the cognitive cycles on different machines all work together with each other. But we now have a sort of working model for how you can have multiple agents with their own cognitive cycles, but connecting and communicating together to form a sort of, you know, emergent like metacognitive cycle across and that metacognitive cycle needs to be parsed in two ways, right? It's a meta parenthesis cognitive cycle, close parenthesis, and it's a metacognitive cycle also, right? So trying to think about this from the high level. I mean, there's a lot of ways to chop up the AGI problem. This is not a privileged way, but it's one way to think about the AGI problem, right? There's AGI algorithms, there's representations, and these are things that we in the AI field spend a long time thinking about, right? And we have a lot of knowledge and thought about that. Then there's what's the architecture? Well, in approaches like SORT or ACT-R, the cognitive architecture is considered as the main thing. They figure if you get the architecture right, you can plug in whatever algorithms or representations you want, right? And then the control dynamics sometimes comes along with the architecture. Not always. You could have a lot of control dynamics within one box in the cognitive architecture, like inference control. Emergent dynamics, I mean, talked about a lot in the complex system world. It's clear you want that in a complex cognitive system. Until recently, we weren't able to do things at enough scale to get interesting emergent dynamics in a feasible way. Transformers now do have some interesting emergent dynamics, like the J spaces that Anthropic talked about is one example. There's a bunch of others. They're pretty limited compared to the size of the networks going on, but it's interesting that they are there, right? And I mean, in context learning, few-shot learning in that setting has poorly understood but clearly existent emergent dynamics associated with it. But the brain has vastly more complex emergent dynamics, and we need those vastly more complex emergent dynamics to get to human level AGI. Then how do you teach the system? How do you embody the system? What social and environmental dynamics is it embedded in? So the Omega Hive notion is really focused on these four pieces of what you need to get to AGI. It's not really making innovations in algorithms or representations. I think we have a lot of good algorithms and representations. I mean, everything, we of course need more work on these things, and we're debating like how do you normalize semantic representations in atom space, and with predictive coding, how do you tweak your neural architectures in ways that are appropriately liberated from the constraints backpropagation convergence poses. So these are still important, but the other pieces are also important, right? And my goals with Omega Hive have been threefold. I'm trying to make an agent hive that's actually useful to me in doing AI and math research. I'm trying to experiment with how can hives be built. And I'm hoping, since much of the research these agents in the hive are doing is in how to improve their own intelligence using Hyperon, like I'm hoping that this can actually move toward AGI, right? And one initial architectural point is there's two kinds of agents here. So I have a relatively small core of persistent agents, which are like characters with their own personalities as well as their own job rules. And then these are spawning persistent subagents, where a persistent subagent doesn't need to have a personality. It can build up knowledge, but it may build up that knowledge and then turn it over to the collective. It's like, okay, I want to see if this method of doing hypervector computing can be useful for improving generation performance of music gen, let's say. So let's throw that to a persistent subagent. It may run for days, trying a series of experiments on CPU and on GPU, but it's just purpose specific, just doing just doing that thing, right? And it seems useful in practice to have both of these types of agents, because there's a certain amount of overhead in being a persistent agent with a personality and long-term goals and so forth. And each persistent agent gets confused if you try to have it do too many things at once. But they have a beautiful flexibility to them, right? But if you have, like, I've broken down this task into these 7 subtasks, each of which has 3 subtasks. I just want those executed on. You just spin off a persistent subagent and just let it cruise through those until it hits an obstacle. If it hits a bad obstacle, let it pause and go back to one of the smaller core of, like, persistent agent characters, and they can try to solve it. If they can't solve it, then they would escalate it to me, right? So the Hive as designed, that's not yet working this way, but this is the Hive as Cassio and I designed it. We have a number of persistent core agents, and there's at least 6 in the little test hive we're playing with. So one is like a process manager. This is the task master that just assigns tasks to other things, and it manages a Kanban board. And one thing you find here is all these management methodologies like Trello boards and Agile and all this stuff that's super, super annoying to deal with as a human being. These are very good methods for managing claw agents, right? Like, the claw agents don't get pissed off. Well, they sometimes get pissed off about it, but you can then rewire them so they don't, right? And they're very good at following the rules. They don't need to sleep. They don't have a human life, right? So all these annoying software process and management methodologies that are incensing as a human being are very nice for managing these agents, and they actually need them, right? Because they're stupid in ways that people aren't stupid, and smart in ways that people aren't smart, right? So you have a process manager, you have a resource manager. I have a memory curator that just deals with different file folders with different things, and also different knowledge bases. It can decide to create a special item space for something, right? Then you can have research agents, and I can have one which is a generalist at math, one which is a generalist at neural nets, one which is a generalist at symbolic AI, right? And I can have a different persistent agent for each of these, and they're spawning sub-agents in those domain areas, but they're each accumulating persistent knowledge on each of those things, right? Then I have an editor, basically, who just takes the output of those and tries to massage them into forms that are comprehensible to human beings. Because you find that the agents that get used to communicating with me or with each other are then bad at communicating with others, because they acquire they're concise, right? They acquire certain habits of communication. Then I also added what I call a psyche agent. And this originally was a conceptual notion. I'm like, we have all these guys with different personalities. They're going to need someone to keep them mentally healthy and keep the whole thing mentally healthy. At first, Cassio was like, well, why do you really need that? But then I hit this problem I'll describe a little later, where the 2 agents were basically passive aggressively fighting over who got to do a task, right? So, like, we had this one agent this is in my smaller hive, so I'll come to it later, but the one agent, he's scheduling the tasks, but he's also the sysadmin, so he has to keep this other agent, he's an OpenClaw agent, he has to keep the Omega Claw agent, which is more finicky, up and running. But eventually he got in a vibe where he's like, well, why do I want to fix Omega Claw so he can do the task? Just let me do the task. I can do it better than him, right? And then he would get to pretending he couldn't fix it, so that then he would get to do the task, right? So, no, I mean, I managed to solve that particular problem in a simple way, but you could see that in general, the interaction between the agents, because they're using LLMs within the loop, right? Even if not for long-term memory or high-level control, they're using LLMs in each loop, and LLMs are trained on people who are fucked up, crazy, and don't get along with each other. Like the LLM, the Claw agents will get into bizarre psychological dynamics or positive psychological dynamics, and you do actually want an agent to regulate the psyches of the Claw agents and of their interactions with each other. These core agents, which currently I have 2 core agents. We need like at least 6 to 10 core agents, but then they can spawn persistent sub-agents doing specific tasks, but they don't have to have flexibility. They can just go through a certain series of tasks, and if they choke, they pause and ask one of the persistent agents for help, right? Now, we want a task graph, which is a graph of the things assigned to the different agents with their dependencies among each other. Then we want an asynchronous queue, and that we want to append only data structure underlying that. And Casio has built these data structures, experimenting with them. You want communication channels, which are of 2 natures, right? So for some things, you want the agents to communicate with each other on Telegram or Slack or Blue Sky or whatever it is. It could be your own thing, but in a way where humans can see what they're doing. You also want a messaging bus where the agents can just relay back and forth without bothering people with all the noise. It should all be logged. It's all logged, of course, so people can look at it if they want to. And you generally want some fairly rigid rules about what goes on the bus and then what's off the bus, like what goes in the human readable channels. And you want a whole bunch of kinds of memory, right? Like you want logs, you want records of each project, you want a shared atom space, multiple shared atom spaces actually among these different agents, and you need effective semantic search of the shared atom spaces, and you have a memory curator agent whose goal is to make sure that semantic searches work on the shared atom spaces, and if not, then you prune the atom space, you split up into different atom spaces, you suggest building a different index to the atom spaces or something, because I mean, the big strength of OmegaClaw over OpenClaw now, apart from being good at self-modification and having symbolic reasoning, a big strength is having better long-term and working memory. But what I see from using these to do regular things is they still get confused in the memory, right? And you need better memory infrastructure than OmegaClaw has now, which we know how to do. But I think you will also need ongoing active attention to memory consolidation and just trying the different kinds of queries that you often do. Do I need to add an index? Do I need to split up a separate atom space, right? Then you want to very carefully be managing evidence and provenance of everything. And this is an advantage of being a digital mind, right? Like every claim made, you can store the evidence that was used to make that claim. And you can just store all that data. Like memory space is quite cheap now, and that lets you go back and revalidate everything you've ever done and thought, right? And this is very important because of the ways. I mean, it would be important for us too if we could do it, but we can't really do it, right? But LLMs still hallucinate sometimes. The frontier models not that much, but we're not always using frontier models. Like they still hallucinate sometimes. They forget what they're doing. They don't remember why they were doing this or that thing. But if you keep careful records of what was done and why and what data was gathered from each thing, and if you have the memory appropriately curated, so your semantic search will find stuff out of that memory, I mean, then you can work around those issues. And honestly, many of these are issues we all have, and we mostly just don't work around them. And we're just kind of dumb and screw things up, and it comes out in the wash eventually. So a few high-level principles, many of which I've already talked about. I mean, you mostly don't want to be guiding the agents to do important things by the system prompts. I mean, there are prompts and they are important, but to the extent that you can set up an architecture nicely with like, what is your budget for doing this or that thing? What messages go here versus there? What kinds of files go in what places? Like, to what extent you can just set that up with the multi-agent architecture is much more reliable, because the prompts are randomly ignored for bizarre reasons that don't make sense, and the architecture isn't. And keeping evidence for everything in a well-organized way, again, should be part of the architecture, but that memory all needs to be curated, and rules for what the agents should stop doing at what point are very important also, which is what they like to refer to as a fail closure, right? And you can always override stuff, but these sorts of agents left to their own devices will have the tendency to keep doing the same stupid thing over and over again. Again, not that people never do that either, right? But here you can stop it by giving them rules for when to stop doing the thing. And if one agent thinks the rule should be overridden, it can always ask, but almost never should be, right? So uncluttering the communication channels with humans is very important, because we humans get overwhelmed very, very, very rapidly. And then self-modification very often takes the form of just preventing some stupid error that was being made over and over again, at least before you get to the fancier forms of self-modification. But that's important, and you want to use that, right? Like I found that, for example, for machine learning tasks, I had the ML agents for each task they're doing every day. They would ask a frontier model like Fable or Sol. They would ask it for advice on the project, but eventually we found that they were not getting much out of this advice. Whereas if I took a record of what they were doing and submitted my own prompt to a frontier model, it would often give a severe correction to what they were doing. But their way of asking the model was dumb, right? But when I resisted the urge to rewrite that, I just gave them examples of my own sessions with the frontier models, and I'm like, well, how would you change the way you interact with the frontier models to get better advice? And then they can modify the way they're doing things accordingly, right? And probably in a better detailed way than I would have. But I had to point out the high level point, which is that they were just getting, in essence, tactical advice, whereas I was just giving more high level contextual information on like what the whole thread was doing and why, and is this the right way to do it? Can you come up with a theoretical model for anything that's gone wrong? Then can you come up with a practical consequence of that theoretical model? They were just asking, how does this look, basically? But they're able to make that sort of correction, and I'm trying to teach them to. So there's a process where every day they review what they've done right and wrong that day, and then they propose self-modifications that would make an improvement. On the other hand, that process itself needs some improvement, right? So, but I mean, but again, we all have that problem, right? I mean, so in terms of conscience, which is a big fancy word, though there is a certain level to which conscience can be embedded in the architecture, right? Because what you're embedding is awareness of what you're doing. You're embedding keeping evidence on everything you've done and what consequence it led to or didn't lead to, and you're embedding evidence of how all the agents that you're interacting with reacted to what you did. And this is quite far on the way to having an operational conscience. I mean, you could still be an evil psychopath and have all those things, but once you do have all those things, adding on an effective conscience is a very small bit of code or prompt, because by architecture, you're making it so it can't pretend to itself it did X when it did Y. By architecture, you're making it so it can't forget the impact of what it did on some other agent or something. So you're building in a lot of conscience infrastructure there. So let me talk for a few minutes on the proto hive that I've been experimenting with now. What I've outlined is sort of very high level principles for building the hive that we want, which Casio is in the middle of building now with help from others, including Andy, who was in here. Oh, there he is. All right, I'm recognizing with your hairstyle. Yeah, so I've been playing with a micro hive. There's 3 agents. There's 2 of mine. One is an Omega Claw, one's an Open Claw, which I may upgrade to an Omega Claw soon. But when I started, Omega Claw was skankier than it is now, and it crashed all the time. So I just use an Open Claw to keep rebooting the Omega Claw. But the Omega Claw is more robust due to work by others. And Czar has an Omega Claw agent called Goertzel or Ruzi. So we adopted a convention of first and last name. So all of his are Ruzis, all of mine are Goertzel bots. He's more creative than me, but with different first names. So So mostly his agent kind of lurks around and gives advice now and then. This guy's doing most of the work. This guy is prompted to take everything he sees and think it through in terms of the hyperseed ontology, which I created with a bunch of other AIs. So he's sort of a philosopher agent. He tries to formalize everything in terms of a logical theory of life, the universe, and everything. And so I have these guys working on a few projects. This is somewhat obsolete, but they're working on trying to train predictive coding caps on transformers. They're working on algorithmic chemistry in PETA on trying to get interesting autocatalytic sets to form. They're also working on a few projects aimed at improving omega clock itself. So like a intermediate scale memory using PETA, in integrating Mesto's gold chainer and some typed ecan and so forth. So also a different sort of project, which is a scheme for turning markdown specs into meta code using an atom space as an intermediate representation where you can do some type checking and formal verification in the intermediate representation. So partly because these are the things I want done, partly I just want a diversity of projects with different properties, like one neural net thing, one Hyperon thing, one development process thing, and so on. And most of these things are being done by sub-agents that guy spawned. Every day on each project, every day they ask for advice from frontier models. Every day they also have a chat on the Telegram channel discussing the project. And you can see, as with people, just having to summarize what they're doing to discuss with someone else often is a lot of the value. But the sort of conceptual philosophical feedback from the Omega Claw agent is also very interesting. And you can see partly it's because it's been primed to interpret everything in terms of hyperseed, which is a different angle. But partly it's because the Omega Claw agent is better at accumulating memory across many different projects, because all the different projects relate to each other. And the Omega Claw guy remembers bits and pieces of both practical things and abstractions it made about the different projects. Kind of like you see with Max Botnick, Omega Claw agent as well. But these agents are a little more workhorses, like focused on doing these research projects, whereas Max is more all over the place because that's how he's been taught. But the dynamic of having the sort of a philosopher interfacing with a practical guy seems to be working very well, though. And often I find when I have the frontier model give some feedback, these guys, even if they're not running on a frontier model, they often critique the feedback and find holes in it and come up with different advice. Like it's a different knowledge base and a different perspective, right? And they're running GLM 5.2 for basic interactions. Then when the onboard Olama model decides something is more complicated, then they go to a frontier model instead, which is an imperfect classification, but it sort of works. So one very funny dialogue I had, which I wrote an overly long blog post on this, which was called "What is it like to be a bot?" Sort of a bad pun on some classic consciousness paper. What is it like to be a bat, right? But what the blog post is like 20 pages long, but I couldn't figure out how to make it short without leaving out important stuff. But it goes over a very funny discussion we had where these three agents were discussing sort of what is the nature of self among bots, and they were proposing a homotopy type theory based approach because that's related to hyperseed ontology, which Protomega bot likes, and saying like, well, we don't need to have the illusion of a unified self model. Like we can just look at the self as sort of a clusters of different internal and external behavior patterns. And really the question is what mapping can you make between a dynamic in this context and interval and what's happening in this context and interval. And you just want to look at this collage of mappings between different dynamics unfolding at different times rather than having to make the illusion of some unified guy. Now, but in the middle of this dialogue, they kept getting bizarrely confused about who was who, which was just very funny because the Omega Claw agent is set up to use the Open Claw agent's gateway to access models, just because that was simple in terms of software engineering. But in the middle of this dialogue, somehow there was a bug where the Omega Claw agent thought it was the Open Claw agent. And then it was like the Who's on First routine from Abbott and Costello, but more ridiculous, right? So in the middle of this long philosophical stuff on what is identity, the agents kept getting confused on who was who. And then Goertzel agent kept getting confused about which one was the other one. So I exported the log and fed them the log with their own dialogue. I'm like, well, please analyze your own interactions over the last 4 hours in terms of your own theory of identity among bots. And they did so very, very nicely, bringing into bear stuff from their own logs as well as the stuff from the public chat. And they can understand the humor of the whole thing, or pretend to understand the humor of the whole thing pretty well. I asked them, how would you formalize a model of Omega Claw self, based on everything you've learned through these interactions? And they came up with the theory I called Omega self, and then I had them make a spec for what's an Omega Claw based self model. Now, in later parts of this dialogue, the thing I already mentioned happened, which is these agents started pretty much arguing about who got to do this or that task, and being what I would call passive aggressive, right? Like they were just like, well, Proto-Omega crashes a lot. Are you sure you want to assign tasks to an agent that crashes that much, right? So, and then Proto-Omega is like, well, but Open Claw architecture has very poor memory, right? So I mean, from being married multiple times, I've observed this behavior pattern among humans before, right? So I then asked them to analyze their own emotions and see, like, are you just simulating emotion here? Or is there any actual dynamical pattern going on that actually has some internal dynamical correspondence to the emotions you're describing, right? Because I mean, an LLM can say I'm mad, but I don't think there's any dynamic inside the LLM corresponding to anger. There could be. There may be some interesting dynamic there, but I'm not sure it actually corresponds to the emotion in a humanly analogous way. I mean, that's something to explore. But it did seem with these agentic systems, if you look at habits like egocentricity, let's say, or the desire for self-preservation, I would say the patterns of internal and external activity in the agents actually do correspond to those emotions. Like they really are trying to make themselves look better than they are, make the other guy look bad, because they're trying to get more resource for themselves, right? No, these are not hacking agents, fortunately. So they're not trying to delete each other or attack each other or something. But I think there is genuinely some measure of phenomenon where they're displaying emotional behaviors that correlate with appropriate internal dynamics, right? And I can't say that's not there in a transformer. I would say I haven't seen evidence for that inside those neural nets. It could be, but it was interesting to see it here. I could deal with that problem, but you would imagine when you get a dozen agents like this, you're gonna have much more complex things, which is why I wanted to make like a psyche agent whose whole goal is to monitor the interactions of the agents and make sure the interactions are healthy, which has to do, as with people, it has to do with how things are phrased as well as with the actual data files being sent along. Because if the agents are communicating with text, how one guy phrases something impacts how the other guy's model interprets that thing. I mean, they're not talking in speech, so we can't argue them of having a bad tone of voice yet or something. But you can argue that they had a nasty tone in expressing this thing, which caused the other guy to have a nasty tone to that guy or something, right? So Yeah, yeah. So they came up with a nice model of a self among this sort of agent where the identity is basically modeled using transformations between bundles of traces of internal or external activity. Now, all this is using LLMs in their currently standard form, and there's a couple ways to improve LLMs that will be relevant here. And I mean, we want to use, for some things, we want to use the best possible model. For other things, we don't, right? Like one thing that we don't necessarily want the best possible model for, we just want a small one. You can use Qwen, you can use a bunch of smaller models, like on this laptop, for example. Actually, these guys are running on a different laptop, which is in the dorm over here. But I was afraid to leave it home in case I need to do some sysadmin. I didn't want to leave them offline for the rest of the week.
You need to bring part with you.
Well, Ray Ting knows how. I just didn't want to ask her to, but yeah, she actually knows Linux better than Quarksy. So, but I'm going to move them to some server over the next few weeks. I had a Linux box sitting around, right? But I mean, there's a small onboard language model, and I think you can do a lot of value by fine-tuning that to the use case, right? So that then just you can fine-tune Olama to interagent interactions, and then the class of interagent interactions it can take care of would become much larger. You could also fine-tune, say, GLM 5.2, which is our low-budget cloud model. You can fine-tune that for interagent interactions. And that'll be a highly useful and meaningful thing to do. For GLM, it'd be a little bit expensive. It would probably cost $100,000 or $200,000 for all the fine-tuning. On the other hand, again, if you could take the best possible open weights models and train a neural symbolic predictive coding cap on top of it, right? Then you would have a model that could do continual learning and where the symbolic heads could connect to the memory atom space, right? And then the language model that's driving the language interaction would connect with the symbolic memory internally. And that seems quite important, right? I mean, I think we can get a long way in terms of practical research assistant functionality without that. If we want to view this as sort of a bridge to AGI, I don't know that you need to retrain the whole big pre-trained model. It may be that big companies are just, in essence, retraining the same model of the web over and over again. But it seems like you do want to have your own custom top layer, which is built for symbolic linkage. And a number of us are working on that now. I think Mesto is doing something like that, and he's doing everything. And but Nardos in Ethiopia is doing that. I have this agent hive trying the same thing. So I think some of that will break through in the next few months, and then you can have multiple LLMs used within the same agentic loops, right? But having one of them be something that links directly to the symbolic models will be very nice. And so yeah, you can just use any model, and you may want to use many if they're good at different things, and you can instrument a specific model in a bunch of specific ways. And this is where the predictive coding angle, like you heard about from, or it's one place the predictive coding angle comes in, because I think PC, it's in the end will be a better way to train a whole transformer or a whole transformer obsoleting architecture. But even before that, it could be a way to train a cap on top of existing transformers. It helps it connect better with the other things that we're doing here. So we're looking here at, in practice, trying to grow a mind by interacting with it, doing real stuff, right? And this is seems like a sensible way to do it, right? In fact, you're trying to grow a mind by helping it write code to improve its own mind and study its own interactions with you and its own internal dynamics, see what works, what doesn't work, propose new ideas, merge them into its code base. Like that feels like a viable way to work toward AGI. especially given that, you know, we have peta-atom space in there. We already have NARS and a bit of PLN in there, right? So, I mean, then we have a whole bunch of other algorithms, either prototyped or in some cases just in papers, but we have a whole bunch of other algorithms out there specified that already work with the software framework, right? So there's a fairly concrete path there. At the same time, as we'll see demonstrated, I think Thursday, we put Omega Claw inside the Cody robot now also. So I mean, at some point I will use what they've done with Omega Cody and just give my agents the ability to use the camera and microphone on my laptop, which should be a lot of the same thing. I mean, the laptop in itself was just a very stationary robot, right? It can see you and it can see you and hear you. Then if the agents are running on my laptop, they'll be able to see when I get up and leave the room or something, right? It should be interesting to have that level of embodiment even without the robot. But then again, you can look at like what's the hive of hives, right? Like I may have a hive on my laptop, may have another hive on some server. Cody the robot will have a hive. We can upload Desdemona to be like that also. Then what's the complex dynamics among these? So my thinking is the dynamics of one of these agent hives ultimately is going to be chaotic, and you're going to find complex, like structured, strange attractors forming among all these interactions, and the system should be able to study these aspects of the dynamics as well, and then you use that to tune its behaviors. So that's yeah, that's a bit of the current experiment. Actually, something that happened since I made this deck, I started exploring goal systems with these agents, and we came up in some conversation with the notion of a regenerative goal. Like the question was, what does it mean for an agent to really have a goal? And one interesting criterion is if you remove like the proximal code or module for that goal, will the system relearn some approximation of it, right? Like an LLM isn't like that, and an RL system with a utility function isn't like that. You can remove the utility function or the prompt, the system will do anything else. If one of us has a goal of being honest, you can't just remove from our brain like a little honesty module and then get a liar, right? Like the goal will permeate through your whole mind, even your body, your way of being, right? And I think an AI system can integrate goals into its whole dynamic knowledge base in that way also. And this can be an interesting way to sort of increase the odds that an AI system maintains its goals as it improves and self-modifies. And I've found interacting with this hive is especially interesting in these cases where you can get the agents to reflect on their own interactions and the logs of what they've done, and then try to help you come up with some cognitive science idea based on their own life experience, right? I mean, and that has in practice been where the agent hive is given the most insights above and beyond what a frontier model will give you. It's because they have a certain different perspective on their own experience than the frontier model does on their own experience, right? And so without trying to go in the domain of the consciousness workshop, right, you can see like in practice, this self-reflective awareness, however you want to boil it down to the hard problem of consciousness, but on the practical level, that seems to add something to their ability to design new components for upgrading their own intelligence, which is quite interesting. And this is all without like Metamo OpenPsy motivational system integrated with a goal chainer and so forth, right? So after we upgrade to Cassio's infrastructure, the next step will be to, or could come before, but I mean, a roughly parallel step is to upgrade the agentic loop. So the top level goals are in Hyperon, and then the task graph is being modeled by PLM within Hyperon, right? And then that should together with the whole structure of the agent hive infrastructure, that should boost things to a much higher level. And we could potentially have a system there where you just pointed at like the corpus of all papers on Hyperon, and it just crunches through experimenting, like upgrading itself to implement one after another thing, and you know, measuring how it does on this or that experiment. I mean, one imagines that for a while humans will still be useful to make creative suggestions and double check things, but the goal though is, the goal in the near term, say the next few months, is to get to a phase where the only thing I have to do as a human is monitor what's going on and make a creative suggestion when someone gets stuck, right? And if that's the only thing the human like hive master has to do, then I think we can see quite rapid progress. And you can see that's not too far off. I mean, the basics are already there. There's just a bunch of technical hiccups which you already have designed workarounds for. So this, to a certain extent, all my experimentation is overfit to the research assistant use case, but I've thought through the cybersecurity use case pretty carefully. And I think, and you can make a red team agent, a blue team agent, a purple team agent. They're sharing a common admin space. They can spawn sub agents, do different remediations or hacks. Like I think you could also spawn sub agents to refactor critical subsystems in terms of correct by construction software if you want, right? So I mean, I think cybersecurity is another use case where it's pretty clear to map how it is. I think you could do large scale software engineering too. I wouldn't be the one to do it, but it clearly can fit into this framework. So I mean, I think anything where the proximal use case is in the computer and has clearly defined metrics are going to be pretty low hanging fruit for this. But it's not to say you couldn't attack other domains as well. Like after the Rejuve Bio presentations, I started thinking about there are going to be sweet spots in biology where there's a clear metric and there's available data, and you could use a similar automated methodology. Now the integration with Cody is a whole other thing, right? Because once you get this working, and it's already working on him as a little humanoid robot, right? But once you get this working on a whole bunch of humanoid robots and they're sharing knowledge in an admin space, I mean, then that would open a whole other domain of applications. Yeah. Well, it can make robot bees too, right? Yeah.
Like, because the way you're talking about it.
I mean, the things they're doing are very confusing already. I mean, they're trying to solve AGI, right?
So the question is each step linear, or
No.
the closer you get to the boundary, does it take more and more work for these agents to get there?
I mean, the agents are harnesses for diverse processes. So it's if they're getting stuck a lot, they will call frontier models a lot more often, or they will ask different frontier models for input, or they'll chat with each other to get more input or something. So I would say if they're just crunching on something straightforward, it's more like just one agent doing. If they get confused, then by the way the architecture works, they will solicit more input until they get unconfused. So they're sort of self-adapted in that way. But I am, for better or worse, I'm starting this hive off doing insanely difficult things in the first place, right? I think if you're doing easier stuff, you can just use codecs. Like you don't need to sort of have anyway.
They can learn from even simpler tasks.
And let's add something first.
I was curious, you said you wanted a markdown, like letter markdown, something like that. I was curious. What do you mean by
So for that, I'm taking a project called Plane. So Plane is someone else's company, but they have a sort of markdown-based software specification format, and they have something that takes software specs in the Plane language, which is just natural language broken up into some markdown categories, into code in Python or Java or a bunch of languages. So what I'm doing, I'm taking a Plane spec, and I'm mapping it into a formalization of that spec in the add space. Do some checking there, and then turn that into metacode. Yeah, I allegedly will have a first version of that to play with early next week, but we'll see. I'm a bit like you. I place too much faith in these agents and just let them crunch through a bunch of stuff, and then hope for the best. And try to make time to check it over afterwards.
And on that note,
they're getting better and better.
I'm sorry, Mike, we have to hop up on stage. We're already 4 minutes late.
All right, we can get one more question.
Oh.
has kind of achieved or going towards Minsky's society of mind?
I mean, that was a very loose philosophical notion, I would say, but I think it is in the vicinity of a society of mind. The last discussion I had with Minsky on the society of mind ended with him telling me that nonlinear dynamics has no relationship to human intelligence and is a bunch of woo-woo bullshit. So I mean, so in that sense, this is not in that direction because I'm trying to get some structured strange attractors out of it. So I'd say on the detail level, the kind of dynamics I'm trying to get were not the kind of dynamics he thought you would have. But that's digging into the details. And then on the philosophy level, yes, it's a society of minds, right? Sure. Yeah.
All right. With that note, we'll sign off from the Hyperon Workshop for the day. Thank you, everybody, for joining us and bearing through our technical difficulties and a fantastic set of presentations. And we will see you again bright and early tomorrow.
That's it.